there are things happening in the universe that no one is watching. Black holes spinning in regions of space so remote that their light will never reach us. Clouds of gas collapsing under their own weight, beginning a process that will take millions of years to complete. And particles moving through the void at speeds we can measure, but never truly comprehend. None of it requires our attention. None of it waits for understanding. The universe simply continues. It has been continuing for 13 billion years, through processes so gradual that even geological time seems brief by comparison. Entire star systems have formed, lived, and faded in regions we will never observe. Galaxies have merged in slow-motion collisions lasting hundreds of millions of years, reshaping structures on scales too vast to hold in mind. And throughout it all, the fundamental forces that govern everything have remained constant, predictable, and utterly indifferent to whether anyone notices. We know more about the cosmos now than at any point in human history, and yet the list of unanswered questions grows longer, not shorter. For every mystery we resolve, new ones emerge, deeper ones, quieter ones, not the kind that announce themselves with drama or spectacle, but the kind that sit patiently at the edges of what we know, waiting without expectation. Questions about why space has the properties it does, why time moves in one direction only, why matter exists in the forms we observe and not in countless other ways that seem equally possible. These aren't questions that demand immediate answers. They don't press for resolution. They simply exist, the way distant stars exist, present, observable, but requiring nothing from us. Tonight, across 9 hours, we'll drift through some of those questions, not to solve them, not to arrive at answers, just to let them exist, the way they do in the universe itself, unresolved, unhurried, undemanding. We'll begin with the largest mysteries, the ones that stretch across the entire observable universe, the ones that ask why anything exists at all and why it's structured the way we find it. We'll move through questions about dark matter and dark energy, invisible components that make up most of the cosmos, yet remain almost entirely unknown. We'll consider the nature of time itself, why it flows forward, why it can't be reversed, and whether it's even a fundamental property of reality or something more subtle. And we'll explore the forces that shape galaxies, the processes that form stars, and the quiet mechanisms that have been operating since the beginning of everything. Then, gradually, we'll move inward, toward our own galaxy, toward the Milky Way and the puzzles it holds within its spiral arms, a galaxy that contains hundreds of billions of stars, each with its own history, its own trajectory through space. Some of those stars are ancient, formed when the universe was young, carrying within them traces of the earliest elements. Others are newly born, emerging from clouds of gas that are collapsing even now, in regions we're only beginning to map. The Milky Way itself is moving, rotating, evolving, interacting with smaller galaxies that orbit it, slowly consuming them over billions of years. And yet, from within it, from our position halfway out along one of its minor spiral arms, we can barely perceive its full structure. We map it slowly, piece by piece, through indirect measurements and careful observation. And what we find is not a simple, orderly system, but something far more complex, far more layered, far more filled with unanswered questions than we expected. There's no rush to get anywhere tonight, no moment you need to catch, no detail you need to hold on to. This is meant to carry you through the night without interruption, whether you're listening closely or barely aware of the words at all. The ideas will drift past at their own pace, some lingering, others fading quickly into the background. You might find yourself following certain thoughts for a while, then losing track of them entirely. That's exactly as it should be. You don't need to follow along. You don't need to understand. You don't even need to stay awake. The questions will remain exactly as they are, whether you hear them or not. They've existed for billions of years already. They'll continue to exist long after this night has passed. There's no test at the end, no information you need to retain, no moment where your attention will be required. This is simply a space where the mysteries of the universe can exist in the background, quiet, patient, and undemanding, where your mind can wander freely without needing to arrive anywhere, where rest is not only allowed, but intended. So settle in now. Let your shoulders drop. Let the weight of the day begin to drain away. Let your breathing slow to its natural rhythm, without effort or control. The universe has been here for 13 billion years. It will be here long after tonight has passed. The stars will continue burning. The galaxies will continue turning. Space will continue expanding, silently, steadily, at its own gentle pace. And for now, you can simply rest. Let the questions drift. Let the night unfold. Let sleep come whenever it's ready. Everything here will still be true tomorrow, and none of it needs you to stay awake. The universe is mostly empty. This is one of the first quiet mysteries. When we look out into space, what we see is not crowded or chaotic. It is vast and calm and almost entirely made of nothing. Between the stars, there is space. Between the galaxies, even more space. And in that space, there is mostly just darkness and distance, and the faint hum of radiation left over from the beginning of everything. If you could stand in the middle of intergalactic space, far from any galaxy, far from any star, you would see almost nothing. A few faint smudges of light in every direction, but mostly just black. Deep, quiet, endless black. And yet, even in that emptiness, there is something. There is a faint glow, a whisper of light. It comes from every direction at once, and it has been traveling through space for more than 13 billion years. We call it the cosmic microwave background. It is the afterglow of the Big Bang, the leftover heat from the moment the universe began, and it fills all of space, evenly, quietly, like a memory that never fades. When the universe was very young, it was hot. So hot that atoms could not form. So hot that light could not travel freely. Everything was a dense fog of energy and particles, glowing white hot, packed together in a space smaller than we can imagine. But then the universe expanded. It cooled. And after about 380,000 years, it cooled enough for atoms to form, for light to finally break free. That light has been traveling ever since. It has stretched and cooled as the universe expanded. What was once visible light, bright and blazing, is now microwave radiation, invisible to our eyes, but detectable by our instruments. And it is everywhere. No matter where you point a telescope, no matter where you look in the sky, you will find it. The same faint glow, the same ancient light. It is the oldest thing we can see, the earliest snapshot of the universe. And it tells us that the cosmos was once much smaller, much hotter, and much more uniform than it is today. But it also raises a mystery. The cosmic microwave background is almost perfectly smooth, almost perfectly uniform. The temperature is the same in every direction, to within a fraction of a degree. And that shouldn't be possible, because the universe is very large, so large that light from one side of the observable universe has not had time to reach the other side. So, how did both sides end up at the same temperature? How did distant regions of space, regions that could never have communicated with each other, end up so perfectly balanced? This is called the horizon problem. And the answer, scientists believe, lies in something that happened in the first fraction of a second after the Big Bang. Something called inflation. Inflation is the idea that the universe, in its earliest moments, expanded faster than the speed of light, much faster. In less than a trillionth of a second, the universe grew from something smaller than an atom to something larger than a galaxy. This rapid expansion smoothed out any irregularities. It stretched space itself so quickly that everything became uniform. And then, just as suddenly, inflation stopped. The universe continued to expand, but at a slower, steadier pace. And the evidence for this is written in the cosmic microwave background, because even though the background is smooth, it is not perfectly smooth. There are tiny fluctuations, tiny variations in temperature, regions that are slightly warmer or slightly cooler than average. These fluctuations are the seeds of everything that came later, the seeds of galaxies, the seeds of stars, the seeds of planets and moons, and eventually life. Gravity pulled matter toward the denser regions. Over millions of years, those regions grew, they collapsed, they formed the first stars, the first galaxies, the cosmic web of structure we see today. But the pattern of those fluctuations, the way they are distributed across the sky, matches exactly what inflation predicts. It is one of the most elegant confirmations in all of cosmology. A theory about the first instant of time, confirmed by light that has traveled for more than 13 billion years. And yet, we still do not know what caused inflation. We do not know what force or field or phenomenon could make space expand so fast. We do not know why it started. We do not know why it stopped. Inflation solves the horizon problem, but it also opens new mysteries. And that is how science works. Each answer leads to deeper questions. Each solution reveals new puzzles. The universe does not give up its secrets easily, but it does give them up slowly, quietly, one discovery at a time. Another mystery, quieter still, concerns the nature of time itself. We experience time as a flow, a river moving in one direction, past to present to future, always forward, never back. But the laws of physics do not require this. Most of the equations that describe the universe work just as well if time runs backward. If you filmed a planet orbiting a star and played the footage in reverse, the motion would still obey the laws of gravity. If you filmed particles colliding and reversed the tape, the physics would still hold. And yet, we never see time run backward. We never see a broken glass reassemble itself. We never see heat flow from a cold object to a hot one. We never see the past change. This is called the arrow of time, and it is one of the deepest mysteries in physics. The arrow of time is not a law. It is a tendency, a statistical inevitability. It arises not from the fundamental rules of the universe, but from the way those rules play out over large numbers of particles. It is connected to a concept called entropy. Entropy is a measure of disorder, of randomness, of the number of ways a system can be arranged. A broken glass has high entropy. There are many ways the pieces can be scattered. A whole glass has low entropy. There is only one way for it to be intact. The second law of thermodynamics says that entropy always increases. Systems move from order to disorder, from low entropy to high entropy, never the reverse. And this is why time has an arrow. When you break a glass, you are increasing entropy. The pieces scatter, the energy spreads out, and the universe moves toward a more disordered state. To reassemble the glass, you would need to decrease entropy. You would need to gather all the pieces, all the energy, all the vibrations, and put them back exactly as they were. This is not impossible. It does not violate any fundamental law, but it is extraordinarily unlikely. So unlikely that it will never happen by chance. And so, time flows forward, because entropy increases, because disorder grows, because the universe is moving from a state of low entropy to a state of high entropy. But this raises another mystery. If entropy always increases, then the universe must have started in a state of very low entropy, a state of very high order, and we do not know why. Why was the early universe so orderly? Why was everything so smooth, so uniform, so finely arranged? This is called the past hypothesis, the assumption that the universe began in a low entropy state. And it is one of the most important assumptions in all of physics. Without it, the second law of thermodynamics would not work. Without it, time would have no arrow. Without it, the universe would make no sense. And yet, we do not know why it is true. We do not know what set the initial conditions. We do not know why the Big Bang began with such low entropy. Some scientists believe the answer lies in quantum mechanics. Others believe it lies in the nature of gravity. Still others believe it is simply a brute fact, a boundary condition that requires no explanation. But the mystery remains. Time flows forward. Entropy increases. The universe grows more disordered with every passing moment, and we do not know why it started any other way. There is a place in space where time behaves even more strangely. Near a black hole, time slows down. Not for the person falling in. For them, time feels normal. But for someone watching from far away, time near the black hole appears to stretch, to crawl, to nearly stop. This is called time dilation, and it is a consequence of Einstein's theory of general relativity. General relativity tells us that gravity is not a force. It is a curvature of space-time. massive objects bend the fabric of space and time around them, and the stronger the gravity, the more extreme the curvature. Near a black hole, gravity is so strong that space-time is bent almost to breaking, and time, as a result, slows down. If you could watch someone fall toward a black hole, you would see them slow down as they approached the event horizon. Their movements would become sluggish. Their clock would tick more and more slowly. And at the event horizon itself, they would appear to freeze. But, from their perspective, nothing unusual would happen. They would fall through the event horizon in a finite amount of time. They would continue falling toward the singularity at the center, and they would never see themselves freeze. This is one of the strangest features of black holes. The event horizon is not a physical barrier. It is simply the point of no return, the boundary beyond which nothing, not even light, can escape. And yet, from the outside, it looks like time itself has stopped there. This leads to a paradox. If you watch someone fall into a black hole, you will never see them cross the event horizon. You will see them slow down, redden, and fade, but never quite as disappear. And yet, from their perspective, they do cross. They do fall in. They do reach the singularity. So what is the truth? Do they cross or not? The answer, according to general relativity, is both. It depends on your perspective. It depends on where you are and how you measure time. This is the nature of space-time. It is not absolute. It is not the same for everyone. It is relative, flexible, dependent on motion and gravity and the path you take through the universe. And near a black hole, this relativity becomes extreme. Time is not a river, it is a dimension, a part of the fabric of reality. And like space, it can be stretched, compressed, and curved. Black holes are the places where this curvature is most severe, where time and space become so warped that our intuitions break down, where the rules of everyday experience no longer apply. And yet, black holes are not rare. There are millions of them in our galaxy alone, perhaps billions. They are a natural consequence of stellar evolution, the final stage in the life of the most massive stars. When a star runs out of fuel, it can no longer support itself against gravity. It collapses, and if it is massive enough, it collapses all the way down to a point, a singularity, a place where density becomes infinite, and the laws of physics, as we know them, cease to function. Around that singularity, space-time is so curved that nothing can escape, and the event horizon forms. From the outside, a black hole is invisible. It emits no light. It reflects no light. It is a hole in space, a region of absolute darkness. But we can detect black holes by their effects, by the way they bend light, by the way they pull on nearby stars, by the way they heat up gas as it spirals inward, glowing brightly just before it disappears forever. And we have even taken a picture of one. In 2019, the Event Horizon Telescope captured an image of the black hole at the center of the galaxy M87. It showed a dark circle surrounded by a glowing ring of light, the shadow of the event horizon, the boundary of no return. It was the first direct image of a black hole, and it confirmed what general relativity had predicted more than a century earlier. Black holes are real. They exist, and they are exactly as strange as the equations said they would be. But they are also quiet, patient, waiting in the darkness, slowly consuming anything that comes too close. They do not explode, they do not shout, they simply exist, warping space-time, bending light, slowing time, and they will be here long after the stars have burned out, long after the galaxies have faded, long after the universe has grown cold and dark, because black holes evaporate very, very slowly. This evaporation is another mystery, another quiet puzzle. Stephen Hawking discovered that black holes are not entirely black. They emit radiation, a faint glow of particles that leak out from the event horizon. This radiation is called Hawking radiation, and it arises from the quantum nature of empty space. Empty space is not truly empty. It is filled with virtual particles, pairs of particles and antiparticles that pop into existence and annihilate each other almost instantly. Normally, these virtual particles have no lasting effect. They appear and disappear too quickly to notice. But near the event horizon of a black hole, something different happens. One particle of the pair can fall into the black hole, while the other escapes. The escaping particle becomes real. It carries energy away from the black hole. And because energy is conserved, the black hole loses mass. Over time, very slowly, the black hole evaporates. For a large black hole, this process takes an unimaginably long time, longer than the current age of the universe, longer than the lifetime of the stars. But for a small black hole, the process is faster. And in the far, far future, when all the stars have died and the universe is cold and dark, black holes will be the last sources of energy, the last points of light. And then, one by one, they too will fade. This evaporation leads to a paradox, a mystery that has puzzled physicists for decades. When a black hole evaporates, what happens to the information that fell into it? In quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must always be preserved. But if a black hole evaporates completely, where does the information go? Does it escape in the Hawking radiation? Does it remain inside, somehow encoded in the final burst of energy? Or is it lost forever? This is called the black hole information paradox, and it is one of the deepest unsolved problems in theoretical physics. Some scientists believe the information is preserved, that it is encoded in the radiation in a way we do not yet understand. Others believe the paradox reveals a flaw in our understanding of quantum mechanics or general relativity. Still others believe the answer lies in a theory we have not yet discovered, a theory that unites quantum mechanics and gravity, a theory of everything. But for now, the paradox remains. Black holes keep their secrets. They swallow information. They warp time. They bend light. And they do it all in silence. Silence is another feature of space. Sound cannot travel in a vacuum. There is no air to carry the vibrations, no medium for the waves to move through. And so, space is quiet. Perfectly, utterly quiet. The explosions of supernovae, the collisions of galaxies, the roar of gas falling into black holes, all of it happens in silence. We see the light. We detect the radiation, but we hear nothing. This silence is part of what makes space so peaceful, so calming. There is no noise, no distraction, just light and darkness, and the slow dance of gravity. But there is one exception: gravitational waves. Gravitational waves are ripples in space-time itself. They are created when massive objects accelerate, when black holes collide, when neutron stars spiral together, when the fabric of space is shaken by violent events. These ripples travel at the speed of light, spreading outward in all directions, and as they pass through space, they stretch and compress everything in their path, including us. When a gravitational wave passes through Earth, it changes the distance between objects, very slightly, by less than the width of an atom, but enough to detect. And we have detected them. In 2015, the LIGO Observatory recorded the first direct detection of gravitational waves. They came from two black holes, more than 1 billion light-years away, that had spiraled together and merged. The signal lasted less than a second, a faint chirp, a rising tone, and then silence. But in that chirp was a wealth of information: the masses of the black holes, the distance to the collision, the shape of space-time as it rippled and settled. It was the first time we had heard the universe, not with light, not with particles, but with gravity itself. Since then, dozens more gravitational waves have been detected, from black holes, from neutron stars, from events we are still working to understand. And each one is a voice, a signal, a message from the distant universe, carried not by light, but by the fabric of space and time. Gravitational waves are silent in the traditional sense. They do not vibrate air. They do not make sound. But they do vibrate space-time. And when we convert their signal into audio, they make a sound, a chirp, a whistle, a hum. It is the sound of the universe itself, singing. And it is one of the most profound discoveries in modern science, because it opens a new way of observing the cosmos, a way that does not rely on light, a way that can see through dust and gas and darkness, a way that lets us listen to the universe, not just look at it. And what we are hearing is beautiful, quiet, steady, the slow collision of massive objects, the merger of black holes, the spin of neutron stars, all of it happening in the deep, dark silence of space, all of it sending ripples through the fabric of reality, ripples that travel for billions of years, that cross unimaginable distances, that arrive here, faint and fading, just strong enough for us to detect. And in those ripples, we find answers and more mysteries, because the universe is full of both. One of the quietest mysteries involves something we cannot see at all: dark matter. Most of the matter in the universe is invisible. It does not emit light. It does not absorb light. It does not reflect light. It passes through ordinary matter as if it were not there. And yet, we know it exists. We know because of the way galaxies move, the way they spin, the way they hold together. When astronomers measure the speed of stars orbiting the center of a galaxy, they find something strange. The stars at the edge of the galaxy are moving too fast, much too fast. According to the laws of gravity, those stars should be moving slower, or they should fly off into space. The visible matter in the galaxy, the stars and gas and dust, does not produce enough gravity to hold them in place. And yet, they stay. They orbit. They remain bound to the galaxy. The only explanation is that there is more matter there, matter we cannot see, matter that provides the extra gravity needed to keep the galaxy together. This invisible matter is called dark matter, and it makes up about 85% of all the matter in the universe. We do not know what it is made of. We do not know what particles compose it. We have never detected it directly, but we see its effects everywhere. In the rotation of galaxies, in the motion of galaxy clusters, in the bending of light around massive objects, in the structure of the cosmic web. Dark matter is woven through the universe. It forms a scaffolding, a framework, upon which galaxies form. It pulls ordinary matter together. It shapes the large-scale structure of the cosmos. Without dark matter, galaxies would not exist. Stars would not exist. We would not exist. And yet, we do not know what it is. Scientists have proposed many candidates, exotic particles with names like WIMPs and actions, primordial black holes, modified theories of gravity. But so far, none of these ideas have been confirmed. Experiments deep underground search for dark matter particles. Detectors in space look for signs of dark matter annihilation. Particle accelerators try to create dark matter in the lab, but the universe keeps it secret. Dark matter remains invisible, silent, undetected. It does not interact with light. It does not interact with ordinary matter, except through gravity. It is a ghost, a shadow, a presence we can infer but never touch. And it is everywhere. Right now, dark matter is passing through you. Billions of particles streaming through your body, through the earth, through everything, without leaving a trace. You cannot feel it, you cannot see it, but it is there, and it has been there since the beginning. Dark matter was present in the early universe. It clumped together under gravity. It formed the first structures. It pulled hydrogen gas into the first galaxies. It is older than the stars, older than the planets, older than anything we can see. And it will be here long after everything else has faded, because dark matter does not decay. It does not burn out. It does not evaporate. It simply exists, patient, invisible, eternal. There is another invisible component to the universe, something even stranger than dark matter: dark energy. Dark energy is the name we give to the force that is causing the universe to expand faster and faster. For most of the history of the universe, the expansion was slowing down. Gravity was pulling everything together, trying to halt the expansion, perhaps even reverse it. But about 5 billion years ago, something changed. The expansion began to accelerate. Galaxies began to move away from each other more quickly. The space between them began to grow at an increasing rate. And this acceleration has continued ever since. Scientists discovered this in the late 1990s by studying distant supernovae. These exploding stars are so bright that they can be seen across billions of light years, and they have a predictable brightness, which makes them useful as distance markers. When astronomers measured the distance to these supernovae and compared it to their redshift, the amount their light had been stretched by the expansion of the universe, they found something unexpected. The distant supernovae were farther away than they should have been. The universe had expanded more than expected. The only explanation was that the expansion was accelerating, that some unknown force was pushing space apart. This force is called dark energy, and it makes up about 68% of the total energy in the universe. We do not know what it is. We do not know where it comes from. We do not know why it exists. It could be a property of space itself, a kind of energy that is built into the fabric of the vacuum. Einstein called it the cosmological constant. Or it could be a new kind of field, a dynamic energy that changes over time. Scientists call this quintessence. Or it could be a sign that our understanding of gravity is incomplete, that general relativity needs to be modified on the largest scales. But we do not know. What we do know is that dark energy is causing the universe to expand faster and faster, and this has profound consequences for the future. As the universe expands, galaxies move farther apart. The space between them grows, and eventually, distant galaxies will be moving away from us faster than the speed of light. Not because they are moving through space, but because space itself is expanding. And when that happens, their light will never reach us. They will disappear beyond the cosmic horizon. They will be lost to us forever. In the far future, billions of years from now, the only galaxies we will be able to see are the ones in our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies, all bound together by gravity. Everything else will have vanished. The universe will appear empty, dark, quiet, and eventually, even those nearby galaxies will merge. They will collide and combine into a single, giant, elliptical galaxy. And then, there will be nothing else to see. No other galaxies, no other stars beyond our own. The universe will still be expanding. Dark energy will still be pushing space apart, but we will be alone. This is called the Big Chill, or the heat death of the universe. It is the ultimate fate of a universe dominated by dark energy, a future where everything grows cold and dark and still. The stars will burn out. One by one, they will exhaust their fuel and fade. The smallest stars, the red dwarfs, will last the longest, trillions of years. But eventually, even they will die. And when the last star goes out, the universe will be dark. There will be no more light, no more heat, no more energy flowing from one place to another. Only black holes will remain, and even they will evaporate slowly over timescales so long that the current age of the universe is less than a blink. And then there will be nothing, just empty space, cold, dark, expanding forever. This is the fate predicted by our current understanding of dark energy. A quiet end, a slow fade, a universe that does not end in fire but in silence. But we do not know if this is truly what will happen, because we do not understand dark energy. We do not know if it is constant. We do not know if it will change. Perhaps dark energy will grow stronger. Perhaps it will tear apart galaxies, stars, planets, atoms. Perhaps it will end the universe in a big rip. Or perhaps dark energy will weaken. Perhaps the expansion will slow again. Perhaps gravity will eventually win, and the universe will collapse back in on itself, ending in a big crunch. Or perhaps something else will happen. Something we have not imagined. Something that depends on physics we have not yet discovered. The future is uncertain. The universe keeps its secrets. But for now, the expansion continues. Dark energy pushes. Space grows. And we drift slowly toward a future we cannot see. There is a question that arises naturally from all of this. Why does the universe have the properties it does? Why is the cosmological constant the value it is? Why is dark energy so weak? If dark energy were slightly stronger, the universe would have expanded too quickly for galaxies to form. If it were slightly weaker, the universe might have collapsed long ago. If the laws of physics were slightly different, stars might not ignite, atoms might not form, life might never arise. The universe seems finely tuned, balanced on a knife edge, perfectly calibrated to allow complexity, structure, and life. This is called the fine-tuning problem, and it is one of the most profound mysteries in cosmology. Some scientists believe the answer is the anthropic principle, the idea that the universe must have the properties it does, because if it did not, we would not be here to observe it. In other words, we exist because the universe allows us to exist. And if the universe were different, we would not be asking the question. This is not a satisfying answer to everyone. It feels circular. It does not explain why the universe is the way it is, only why we are able to observe it. Others believe the answer lies in the multiverse, the idea that our universe is just one of many, that there are countless other universes, each with different laws of physics, different constants, different properties. In most of those universes, conditions are not right for life. Stars do not form. Galaxies do not form. Complexity does not arise. But in a few universes, by chance, the conditions are just right. And in those universes, life can emerge. Observers can exist. We live in one of those rare universes, not because it was designed for us, but because we could only exist in a universe like this. The multiverse is a controversial idea. It is difficult to test, difficult to prove or disprove. Some scientists embrace it. Others reject it as unscientific. But it is one possible answer to the fine-tuning problem. One way to explain why the universe has the properties it does. Another possibility is that we simply do not understand the laws of physics well enough, that there is a deeper theory, a more fundamental explanation, that will show why the constants have the values they do. Perhaps string theory will provide that answer. Perhaps loop quantum gravity. Perhaps something else entirely. But for now, the mystery remains. The universe is finely tuned, and we do not know why. There is a related mystery about the number of dimensions. We experience 3 dimensions of space: length, width, height, and 1 dimension of time. But some theories of physics suggest there may be more dimensions. Dimensions we cannot perceive. Dimensions that are curled up, hidden, too small to detect. String theory, for example, requires 10 dimensions, or 11 in some versions. In string theory, the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. These strings exist in a space with more than 3 dimensions, and the way they vibrate determines what kind of particle they appear to be. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is a string vibrating yet another way. The extra dimensions are compactified, curled up into shapes so small that we cannot see them, smaller than atoms, smaller than protons, smaller than anything we can measure. But they are there, and they affect the way the strings vibrate. They affect the properties of particles. They affect the laws of physics. If string theory is correct, then the universe is much stranger than it appears. Space is not three-dimensional. It is 10-dimensional, or 11. And most of those dimensions are hidden from us. But string theory is not proven. It is a mathematical framework, a set of equations. It makes predictions, but many of those predictions are difficult or impossible to test with current technology. And so the question remains, are there extra dimensions? And if so, why are they hidden? One possibility is that the extra dimensions are small because of the way the universe evolved. Perhaps they started out the same size as the other dimensions, but something caused them to curl up, to compactify. Another possibility is that the extra dimensions are not small at all, that they are large, but we are confined to a three-dimensional surface within them, like a sheet of paper in a three-dimensional room. We can move along the paper, but not off it. This is called the brain world scenario. The idea that our universe is a three-dimensional brain embedded in a higher dimensional space. If this is true, then gravity might be able to leak into the extra dimensions. And this could explain why gravity is so much weaker than the other forces. Electromagnetism, the strong force, and the weak force are all confined to our brain. But gravity spreads out into the higher dimensions, and so it appears weaker to us. This is a speculative idea. There is no direct evidence for it, but it is consistent with the mathematics of string theory, and it offers a possible explanation for one of the puzzles of particle physics. The question of extra dimensions is still open. We do not know if they exist. We do not know how many there are. We do not know why they would be hidden. But the possibility is tantalizing. The idea that the universe has more structure, more complexity, more depth than we can perceive. That reality extends beyond what we can see, beyond what we can measure, beyond what we can imagine, and that somewhere in those hidden dimensions there are truths we have not yet discovered. Another quiet mystery involves the nature of quantum mechanics itself. Quantum mechanics is the theory that describes the behavior of particles at the smallest scales, and it is one of the most successful theories in all of science. It has been tested countless times. It has made predictions that have been confirmed to extraordinary precision. It underlies all of modern technology: computers, lasers, smartphones, medical imaging. All of it depends on quantum mechanics. And yet, we do not fully understand what it means. At the heart of quantum mechanics is the idea of superposition, the idea that a particle can exist in multiple states at once. It can be in two places at the same time. It can spin in two directions at the same time. It can be both a wave and a particle. But when we measure the particle, when we observe it, the superposition collapses. The particle chooses one state, one position, one spin, and we do not know why. This is called the measurement problem, and it is one of the deepest puzzles in quantum mechanics. What counts as a measurement? What causes the collapse? Is it the act of observation, the interaction with a detector, the involvement of consciousness? No one knows. There are many interpretations of quantum mechanics, many ways of thinking about what is happening. The Copenhagen interpretation says that the wave function, the mathematical description of the superposition, is not real. It is just a tool for calculating probabilities. The collapse happens when we measure, but there is no deeper reality behind it. The many worlds interpretation says that the wave function never collapses. Instead, every possible outcome happens. The universe splits into multiple branches. In one branch, the particle is here. In another branch, it is there, and both branches are equally real. The pilot wave interpretation says that particles do have definite positions, even when we are not measuring them. They are guided by a wave, a field that fills all of space. The wave is real. The particle is real, and there is no collapse. Each interpretation gives the same predictions. Each one matches the experiments, but they paint very different pictures of reality, and we do not know which one is correct, or if any of them are correct. Quantum mechanics works. It predicts, it explains, but it does not tell us what is really happening. It does not tell us what reality is like when no one is looking. And this is deeply unsettling, because it suggests that the universe is fundamentally strange, that reality is not what it seems, that the act of observation plays a role in shaping what exists, or perhaps it suggests that our language, our concepts, our intuitions are simply inadequate, that the quantum world does not fit into the categories we use to describe the everyday world. Particles are not tiny billiard balls. Waves are not ripples in water. Superposition is not a particle being in two places at once. These are just metaphors, approximations, ways of translating the mathematics into words. But the mathematics is what is real. The equations are what describe the universe, and they do not care about our intuitions. Quantum mechanics is a mystery we live with, a theory we use every day without fully understanding what it means. And perhaps that is enough. Perhaps the universe does not owe us an explanation. Perhaps reality is simply what the equations say it is: strange, counterintuitive, impossible to visualize, but real nonetheless. One of the strangest predictions of quantum mechanics involves something called entanglement. Entanglement is a connection between particles, a correlation that persists even when the particles are separated by vast distances. If two particles are entangled, measuring one of them instantly affects the other, no matter how far apart they are. This does not mean information is traveling faster than light. It does not mean there is a signal passing between them. The connection is more subtle than that. But it is real. It has been tested. It has been confirmed. Einstein called it spooky action at a distance. He did not like it. He thought it suggested that quantum mechanics was incomplete, that there must be some hidden variables, some deeper reality that explained the correlation. But experiments have shown that Einstein was wrong. There are no hidden variables. The entanglement is fundamental. It is built into the fabric of quantum mechanics, and it is one of the most profound features of the universe. Entanglement means that particles are not independent. They are connected. They are part of a larger whole. Even when separated by light years, they remain linked. They share a quantum state. They are, in some sense, one system. This has deep implications for the nature of reality. It suggests that the universe is not made of separate, isolated objects. It is a web of connections, a network of relationships. Particles do not have properties on their own. They have properties in relation to other particles, in relation to the whole. This is a shift in perspective, a move away from the idea of a universe made of independent parts toward the idea of a universe that is fundamentally interconnected. And it is not just a philosophical idea. It is a physical fact, confirmed by experiment, used in technology. Quantum computers rely on entanglement. Quantum cryptography relies on entanglement. Future technologies will rely on it even more. But we still do not fully understand it. We do not know why entanglement exists. We do not know what it means for the nature of space and time. Some physicists believe that entanglement is more fundamental than space, that space itself emerges from the pattern of entanglement between particles. This is a radical idea. It suggests that space is not a container, not a stage on which events unfold. It is a consequence, a byproduct, an emergent property of quantum connections. If this is true, then the universe is even stranger than we thought. Space is not fundamental. Distance is not fundamental. Only the web of entanglement is real, and everything else is built on top of that. This is still speculative, still theoretical, but it is a direction that research is moving, a possibility that physicists are exploring, and it is one more mystery, one more quiet puzzle, one more hint that the universe is deeper, richer, more interconnected than we ever imagined. There is a type of particle that passes through everything. Right now, trillions of them are passing through your body, through the walls, through the earth, through everything solid, as if it were not there at all. They are called neutrinos. Neutrinos are among the most abundant particles in the universe. They are produced in the cores of stars, in supernovae, in the Big Bang itself. They stream out from the sun in vast numbers, flooding through space, through planets, through us, and they barely interact with anything. A neutrino could pass through a light year of solid lead and not hit a single atom. They are ghostly, insubstantial, almost impossible to detect. And yet, we have detected them, deep underground, in massive tanks of water. Scientists have built detectors. They wait, they watch. And occasionally, very rarely, a neutrino will collide with a water molecule. It will produce a flash of light, a brief spark, and the detector will record it. These detections are precious. Each one tells us something about where the neutrino came from, what produced it, how long it has been traveling. Neutrinos from the sun tell us about the nuclear reactions happening in its core. Neutrinos from supernovae tell us about the deaths of massive stars. Neutrinos from the early universe carry information about the Big Bang itself. They are messengers, travelers from distant places and distant times. And because they interact so weakly, they can carry information that light cannot. Light can be absorbed, scattered, blocked by dust and gas. But neutrinos pass through everything. They arrive here unchanged, carrying their message intact. And that message is often surprising. In the 1960s, scientists built the first detector to measure neutrinos from the sun. They wanted to test their understanding of how stars work, to confirm that the sun was powered by nuclear fusion. But when they measured the number of neutrinos arriving from the sun, they found a problem. There were too few. Only about 1/3 of the expected number were arriving. The rest were missing. This became known as the solar neutrino problem, and it puzzled scientists for decades. Some thought the problem was with the detector. Perhaps it was not sensitive enough. Perhaps it was missing some neutrinos. Others thought the problem was with the theory. Perhaps the sun was not fusing hydrogen the way we thought. Perhaps our models were wrong. But the answer turned out to be stranger than either of those possibilities. The neutrinos were not missing. They were changing. Neutrinos come in 3 types, 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The sun produces electron neutrinos. But as those neutrinos travel from the sun to the Earth, they oscillate. They change from one flavor to another. And by the time they arrive here, only about 1/3 of them are still electron neutrinos. The detector was only sensitive to electron neutrinos, so it was only seeing 1/3 of the total. The rest had changed flavor and were passing through undetected. This discovery solved the solar neutrino problem, but it also revealed something profound about neutrinos themselves. For neutrinos to oscillate, they must have mass. This was unexpected. For many years, scientists thought neutrinos were massless. The equations of particle physics suggested they should be massless, like photons. But the oscillations proved otherwise. Neutrinos have mass, a very small mass, so small that it is difficult to measure. But it is there, and this has implications for the universe as a whole. If neutrinos have mass, then they contribute to the total mass of the universe. And because they are so abundant, even a tiny mass adds up. Scientists estimate there are about 330 neutrinos per cubic centimeter in the universe, left over from the Big Bang, cooled by the expansion of space, no longer hot and energetic, but still present, still moving, still everywhere. If each of those neutrinos has even a tiny mass, then together they account for a significant fraction of the matter in the universe. Not as much as dark matter, but more than all the visible stars and gas combined. Neutrinos are part of the cosmic inventory, part of the structure, part of the web of matter that shapes the universe. And yet, they are almost invisible, almost intangible, passing through everything, affecting almost nothing, but always there. They are quiet travelers, silent messengers, witnesses to events we can barely imagine. And they remind us that the universe is full of things we cannot see, cannot touch, cannot directly perceive. But they are real. They exist, and they matter. Another mystery involves something much larger than a particle. It involves the largest structures in the universe. Galaxies are not scattered randomly through space. They are arranged in patterns, in clusters, in filaments, in vast webs of structure that stretch across hundreds of millions of light years. These structures are called the cosmic web, and it is one of the most striking features of the universe. If you could step back far enough, if you could see the universe on the largest scales, you would see that galaxies are not evenly distributed. They form sheets and filaments, like the strands of a spider's web. And between those strands are enormous voids, regions of space that are nearly empty. The cosmic web formed over billions of years, shaped by gravity and dark matter. In the early universe, matter was distributed almost uniformly, almost smooth. but there were tiny fluctuations, tiny variations in density. Gravity pulled matter toward the denser regions. Over time, those regions grew. They attracted more matter. They became denser still, and the less dense regions became emptier. Matter flowed out of them toward the denser areas. Slowly, over hundreds of millions of years, the structure emerged. Filaments formed, clusters formed, voids formed, and the pattern that emerged was the cosmic web. It is a natural consequence of gravity, a structure that arises inevitably from the initial conditions of the universe. But it is also beautiful, delicate, complex. The filaments are like threads of light stretching across the darkness. The clusters are like knots where many threads come together. And the voids are like empty chambers, vast and silent. The cosmic web is held together by dark matter. The filaments are made mostly of dark matter, with galaxies and gas embedded within them. The dark matter provides the gravity, the scaffolding, the framework, and it is stable. The cosmic web does not collapse. It does not fall apart. It simply exists, slowly evolving as the universe expands. Galaxies move along the filaments. They flow toward the clusters. They merge. They interact. They are drawn together by gravity, guided by the structure of the web. And we are part of this structure. The Milky Way is part of a small cluster called the local group. The local group is part of a larger structure called the Virgo supercluster. And the Virgo supercluster is part of an even larger structure called Laniakea. Laniakea is a supercluster of superclusters, a vast region of space, 500 million light-years across, containing about 100,000 galaxies, and we are moving through it. The Milky Way is being pulled toward the center of Laniakea, toward a region called the Great Attractor. We are flowing along one of the filaments of the cosmic web, drawn by gravity, moving through space at hundreds of kilometers per second. This motion has been ongoing for billions of years, and it will continue for billions more. We are not stationary. We are not isolated. We are part of a flow, a current, a river of galaxies moving through the structure of the universe. And this flow is one of the quiet motions of the cosmos. Slow, steady, inevitable. It is not something we can feel, not something we experience directly, but it is happening all the time, beneath everything else. The cosmic web is a reminder that the universe has structure on the largest scales, that even the voids, the empty spaces, are part of a pattern, that everything is connected. And it is also a reminder that we are small, that our galaxy is one of many, that the structures we are part of extend far beyond what we can see. But there is something comforting in that, something peaceful. We are part of something larger. We are woven into the fabric of the universe, and that fabric has been unfolding for billions of years and will continue to unfold for billions more. We do not need to understand all of it. We do not need to grasp the full scale. We simply need to know that we are part of it, and that is enough. One of the mysteries of the cosmic web involves the voids themselves. The voids are not completely empty. They contain some galaxies, some matter, but they are far less dense than the filaments and clusters, and they are very large. Some voids are hundreds of millions of light-years across, enormous bubbles of near emptiness. surrounded by walls of galaxies. Inside a void, space is quieter, calmer. There is less gravity pulling things together, less structure forming. Galaxies and voids are often isolated. They evolve more slowly. They have fewer interactions, fewer mergers, fewer disturbances. In some ways, a void is the most peaceful place in the universe, away from the crowded clusters, away from the constant gravitational tug and pull, just empty space, stretching in every direction. But the voids are also mysterious. We do not know exactly how they formed. We know that gravity shaped them, but the details are still being worked out. We do not know if they will always exist, or if they will eventually be filled in as the universe continues to evolve. We do not know if there is something special about the voids, if they play a role in the structure of the universe that we do not yet understand, but they are there, vast and empty and quiet, a natural part of the cosmic web. And they remind us that the universe is not uniform, that it has texture, that it has regions of density and regions of emptiness. And both are necessary. Both are part of the pattern. Another quiet mystery involves the motion of galaxies within clusters. When astronomers measure the speeds of galaxies in a cluster, they find something strange. The galaxies are moving too fast. According to the laws of gravity, based on the visible matter in the cluster, the galaxies should be moving slower, or they should escape. The cluster should fly apart. But it does not. The galaxies remain bound. They stay together. This was one of the first clues that dark matter exists, that there is more matter in the cluster than we can see. Invisible matter, providing the extra gravity needed to hold the cluster together. This observation was made in the 1930s by an astronomer named Fritz Zwicky. He studied the Coma cluster, a large cluster of galaxies, and measured the speeds of the galaxies within it. He found that they were moving much faster than expected, and he concluded that there must be missing mass, dark matter. At the time, his idea was not widely accepted. It seemed strange, unlikely. Why would there be invisible matter? But over the decades, more evidence accumulated. The rotation curves of galaxies, the bending of light around massive objects, the structure of the cosmic web, all of it pointed to the same conclusion. Dark matter exists, and it is everywhere. Galaxy clusters are some of the best places to study dark matter, because they contain so much of it, and because the effects are so clear. When light from a distant galaxy passes near a massive cluster, the light is bent by gravity. This is called gravitational lensing. The cluster acts like a lens, focusing and distorting the light. And by studying the amount of distortion, astronomers can map the distribution of mass in the cluster. What they find is that most of the mass is not in the galaxies. It is in the space between them, in the dark matter. The dark matter forms a halo around the cluster, a smooth, invisible cloud that extends far beyond the visible galaxies. And this halo provides the gravity, the structure, the glue that holds the cluster together. Without dark matter, clusters would not exist. Galaxies would not stay together. The cosmic web would not have formed. Dark matter is essential, fundamental, invisible but present, and it is one of the quiet forces shaping the universe. There is a question about the future of galaxies. What will happen to them in the far future, as the universe continues to expand? The answer depends on dark energy, on whether the acceleration of the universe continues, on whether space keeps expanding faster and faster. If dark energy remains constant, then the future is clear. The universe will keep expanding. Galaxies will move farther apart, and eventually, they will be so far away that their light can no longer reach us. The only galaxies we will see are the ones in our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies. And even those galaxies will merge. In about 4 billion years, the Milky Way and Andromeda will collide. They will pass through each other, their stars mingling, their gas clouds colliding and forming new stars. And then they will fall back together. They will merge into a single, large elliptical galaxy. This new galaxy will be the center of our local universe, the only structure we can see, the only light in the darkness. All other galaxies will have vanished beyond the cosmic horizon. The universe will appear empty, silent, still. And then, over trillions of years, the stars in that galaxy will burn out. One by one, they will exhaust their fuel and fade. The smallest stars, the red dwarfs, will last the longest, tens of trillions of years, but eventually, even they will die. And when the last star goes out, the universe will be dark. No more light, no more heat, just cold, dead remnants, white dwarfs, neutron stars, black holes, and empty space expanding forever. This is the quiet end, the slow fade, the universe growing cold and dark and still. It is not an end in fire, not an end in violence, just an end in silence. And it will take a very, very long time. But it is also possible that something else will happen. That dark energy will change. That new physics will intervene. Perhaps the universe will collapse. Perhaps it will rip apart. Perhaps it will cycle, ending and beginning again. We do not know. The future is uncertain. The universe keeps its secrets. But for now, the stars are still burning. The galaxies are still turning. And we are here in this brief moment to witness it. That is a gift, a quiet gift, a moment of light in the vast darkness of time. And we can rest in that. We can let go. We can simply be here, now, without needing to know what comes next. The universe will continue. It will unfold. It will do what it does. And we can rest. There is a type of star that barely shines. It is called a brown dwarf. And it is not quite a star, not quite a planet. It is something in between. Brown dwarfs form the same way stars do, from collapsing clouds of gas and dust, but they do not have enough mass to ignite hydrogen fusion in their cores. They are too small, too light. The pressure and temperature at their center never reach the point where hydrogen atoms can fuse into helium. And so, they do not shine the way stars do. They do not burn steadily for billions of years. Instead, they glow faintly with leftover heat from their formation. They slowly cool. They fade. Brown dwarfs are dim, very dim, difficult to detect. They emit most of their light in the infrared, invisible to our eyes. But they are out there, scattered throughout the galaxy, silent, cooling, almost invisible. Some brown dwarfs are alone, drifting through space, never part of a solar system, never orbiting a star. Others are companions, orbiting larger stars, or orbiting each other in binary pairs. They are the failed stars, the objects that almost made it, but did not quite have enough mass. And yet, they are fascinating, because they blur the line between stars and planets. They show us that the universe does not have sharp categories, that there is a continuum, a spectrum of objects, each slightly different from the next. Brown dwarfs are also important for understanding how stars form, how planets form, how solar systems come together. They are part of the population, part of the inventory of objects in the galaxy, and they remind us that not everything in the universe is bright, not everything shines. Some things are dim, quiet, almost invisible, but they are still there, still real, still part of the story. Another dim object in the universe is a white dwarf. A white dwarf is the remnant of a star like the Sun. After the star has exhausted its fuel, after it has shed its outer layers, what remains is the core. The core is incredibly dense. A white dwarf with the mass of the Sun is only about the size of the Earth. All that mass compressed into such a small volume. The density is staggering. A teaspoon of white dwarf material would weigh several tons. White dwarfs do not burn. They do not produce energy through fusion. They simply glow with leftover heat. Heat that was trapped in the core during the star's lifetime. And they cool, very slowly. A white dwarf starts out hot, tens of thousands of degrees. It shines with a bright white light, but over time, it cools. It fades. It shifts from white to yellow to red. And eventually, after trillions of years, it will cool completely. It will become a black dwarf, a cold, dark, dead star. No black dwarfs exist yet. The universe is not old enough. Even the oldest white dwarfs are still faintly glowing, but in the far future, they will exist. The final remnants of stars, cold and dark and silent. White dwarfs are stable. They are held up by something called electron degeneracy pressure, the pressure that comes from the quantum behavior of electrons. Electrons cannot occupy the same space. They resist being compressed, and this resistance is what keeps a white dwarf from collapsing further. But there is a limit. If a white dwarf gains too much mass, if it exceeds about 1.4 times the mass of the Sun, the electron degeneracy pressure is not enough. The star collapses, and it explodes. This explosion is called a Type 1, a supernova, and it is one of the brightest events in the universe. Type Ia supernovae are important for cosmology because they are so bright and so consistent. They can be seen across vast distances, and they can be used as distance markers, as standard candles, to measure the expansion of the universe. It was by studying type Ia supernovae that scientists discovered dark energy, that the expansion of the universe is accelerating. But before the explosion, before the supernova, there is just a white dwarf, cooling quietly, fading slowly, waiting. And most white dwarfs will never explode. Most will simply cool and fade and become black dwarfs billions of years from now. They are the quiet endings, the peaceful deaths of ordinary stars. and they remind us that not all endings are violent, that most things fade gently, that silence is more common than noise. There is another type of stellar remnant, more extreme than a white dwarf, more dense, more strange, a neutron star. Neutron stars form when very massive stars explode as supernovae. The core collapses, and if it is heavy enough, it does not stop at the white dwarf stage. It collapses further. The protons and electrons in the core are squeezed together so tightly that they combine. They become neutrons, and the entire core becomes a ball of neutrons. A neutron star is incredibly dense, far denser than a white dwarf. A neutron star with the mass of the Sun is only about 20 kilometers across, about the size of a city, and a teaspoon of neutron star material would weigh as much as a mountain. The surface of a neutron star is smooth, hard, made of atomic nuclei packed so tightly that they form a solid crust. Beneath the crust, the matter is even more exotic. A superfluid of neutrons, a sea of particles that flows without friction, without resistance. And at the very center, the core, the conditions are so extreme that we do not know what happens. The matter may break down into quarks. It may form something entirely new, something we have no name for. Neutron stars are also incredibly strong. The magnetic field of a neutron star is trillions of times stronger than Earth's magnetic field. Some neutron stars spin very fast, hundreds of times per second. They are called pulsars. Pulsars emit beams of radiation from their magnetic poles, and as the star spins, those beams sweep across space like a lighthouse beam. If the beam sweeps past Earth, we detect a pulse, a brief flash of radio waves or X-rays, and we see the star blinking on and off, very rapidly, very precisely. Pulsars are some of the most accurate clocks in the universe. Their pulses are so regular, so consistent, that they can be used to test the laws of physics, to detect gravitational waves, to measure the expansion of space. But not all neutron stars are pulsars. Some spin more slowly. Some have weaker magnetic fields. Some do not emit beams that point toward Earth. Those neutron stars are silent, invisible. We only know they are there if they are part of a binary system, if they are pulling gas from a companion star. Neutron stars are the densest objects in the universe. Aside from black holes, they are the edge of matter, the limit of how compressed ordinary matter can be. Beyond that limit, there is only one possibility: a black hole. And black holes are where the quiet mysteries become even deeper. There is a mystery about what happens inside a black hole. We know what happens at the event horizon. We know how time behaves, how light behaves, how gravity pulls. But inside, beyond that boundary, we can only speculate. General relativity tells us that at the center of a black hole is a singularity, a point of infinite density, a place where space and time break down, where the equations stop working. But we do not know if singularities truly exist. Perhaps something else happens. Perhaps quantum mechanics prevents the collapse from reaching infinite density. Perhaps the matter bounces back. Perhaps it tunnels to another universe. These are speculations, possibilities, but we have no way to test them, because nothing can escape from inside a black hole. No information, no signal, no light. Whatever happens inside remains hidden. forever sealed behind the event horizon. This is called cosmic censorship. The idea that singularities are always hidden, that the universe does not allow us to see them directly. It is as if the universe has a modesty, a reluctance to reveal its most extreme states, its most violent breakdowns. And perhaps that is for the best. Perhaps there are some things we are not meant to see, some places where the laws we know simply do not apply. Black holes are boundaries, edges, places where our understanding ends and mystery begins, and they are comfortable with that. They do not demand to be understood. They simply exist, quiet, patient, keeping their secrets. Another mystery involves the rotation of black holes. Black holes can spin, and when they spin, they drag space-time around with them. This is called frame dragging. The spinning black hole twists the fabric of space and time, pulling everything nearby into a rotating motion. Near a spinning black hole, it becomes impossible to stand still. Space itself is rotating, and anything in that space is carried along with it. This creates a region called the ergosphere, a zone outside the event horizon where nothing can remain stationary, where everything must move in the direction of the black hole's rotation. But the ergosphere is not inside the event horizon. It is possible to enter the ergosphere and escape. It is possible to extract energy from it. This is called the Penrose process, and it is one of the most remarkable features of spinning black holes. By dropping an object into the ergosphere and carefully timing its trajectory, it is possible to extract rotational energy from the black hole. The object can split into two pieces. One falls in. The other escapes, carrying away more energy than it started with. The black hole loses a tiny amount of its spin, and the escaping object gains energy. This is a theoretical process. It has never been observed, but it is allowed by the laws of physics. It is possible. And in the far future, if intelligent beings still exist, if they need energy and the universe is cold and dark, they might use this process. They might harvest energy from spinning black holes, because black holes will be the last sources of energy, the last warm places in a frozen universe. But that is a very long time from now, trillions upon trillions of years. For now, black holes are simply there, spinning quietly, warping space-time, waiting. There is also a mystery about where black holes come from in the first place. We know that stellar mass black holes form from supernovae, from the collapse of massive stars. But what about the supermassive black holes at the centers of galaxies? These black holes are enormous, millions or billions of times the mass of the Sun, and they formed very early in the history of the universe. We see supermassive black holes in galaxies that are less than 1 billion years old, galaxies that formed shortly after the Big Bang, and we do not know how they grew so large so quickly. It takes time for a black hole to grow. It must consume matter, pull in gas and stars, merge with other black holes. But there does not seem to have been enough time for these supermassive black holes to reach their size through normal processes. So how did they form? One possibility is that they started large, that they formed from the direct collapse of massive clouds of gas in the early universe. Another possibility is that they formed from the collapse of the first stars, stars that were much more massive than any star today. Stars that lived fast and died young, leaving behind large black holes. Or perhaps they grew through repeated mergers. Perhaps many smaller black holes came together again and again, building up mass quickly. We do not know. The observations are still unclear. The theories are still being tested. But it is one more mystery, one more question about the history of the universe. And it reminds us that even the largest, most powerful objects in the cosmos have origins we do not fully understand. Supermassive black holes are also surprisingly influential. At the center of almost every large galaxy, there is a supermassive black hole, including our own. The Milky Way has a black hole called Sagittarius A star. It has a mass of about 4 million suns, and it sits at the very center of the galaxy, quiet, mostly dormant, occasionally consuming a small amount of gas or a stray star. But in other galaxies, the central black hole is more active. It pulls in large amounts of matter. Gas spirals inward, heating up, glowing brightly. Jets of particles shoot outward at nearly the speed of light. These active black holes are called quasars, or active galactic nuclei. They are among the brightest objects in the universe. A single quasar can outshine an entire galaxy of stars, and yet the light does not come from the black hole itself. It comes from the matter falling into the black hole. The accretion disk, the swirling, glowing ring of gas just outside the event horizon. As the gas spirals inward, it heats up. Friction converts gravitational potential energy into heat. The temperature rises. The gas glows. And just before it crosses the event horizon, just before it disappears forever, the gas emits a final burst of light, a last farewell. That light travels outward, across space, across billions of light years, and it reaches us. Quasars are so bright that we can see them at the edge of the observable universe. They are beacons, markers of the early cosmos, signs of black holes that were already supermassive when the universe was young. But they are also temporary. Quasars do not last forever. As the black hole consumes the nearby gas, the supply runs out. The accretion disk fades. The jets shut off. The quasar becomes quiet. And the galaxy settles into a quieter state. The black hole remains, but it is no longer feeding, no longer glowing. It becomes dormant, like Sagittarius, a star, like the black holes at the centers of most galaxies today. They are sleeping giants, waiting, ready to wake if new gas arrives. But for now, still, there is a connection between black holes and the galaxies around them. When astronomers measure the mass of a supermassive black hole and compare it to the properties of its host galaxy, they find a correlation. The more massive the black hole, the more massive the central bulge of the galaxy. The two are linked. This is surprising, because the black hole is tiny compared to the galaxy. The event horizon of a supermassive black hole is only a few light hours across. The galaxy is hundreds of thousands of light years across. And yet, they seem to know about each other. They seem to have co-evolved. This suggests that black holes play a role in shaping galaxies, that their activity, their jets, their radiation affects the gas and stars around them. When a quasar is active, its jets can blow gas out of the galaxy. They can heat the gas, preventing it from collapsing and forming new stars. This is called feedback. The black hole regulates the growth of the galaxy. It prevents the galaxy from forming too many stars too quickly, and this feedback may explain the correlation. The black hole and the galaxy grow together. They influence each other. They reach a balance. When the black hole is too small, it does not provide enough feedback. The galaxy forms stars quickly. The black hole grows. When the black hole is too large, it provides too much feedback. Star formation slows. The galaxy stops growing. And eventually, they settle into a stable state, a balance, a quiet equilibrium. This is one of the surprising discoveries of modern astronomy, that black holes, the darkest objects in the universe, play a bright role in the evolution of galaxies, that destruction and creation are linked, that endings and beginnings are part of the same process. There is a type of galaxy that is shaped by black holes, an elliptical galaxy. Elliptical galaxies are smooth, round. They do not have spiral arms. They do not have much gas or dust. They are made mostly of old stars, and they are common. About a third of all large galaxies are elliptical. Elliptical galaxies form through mergers. When two spiral galaxies collide, they mix. Their stars pass through each other. Their gas clouds collide and form new stars. And over time, the two galaxies merge. They become one, and the result is an elliptical galaxy. During the merger, gas falls toward the center. It feeds the supermassive black holes. The black holes grow. They become active. They emit jets and radiation, and that activity blows out the remaining gas, the gas that would have formed new stars. So the elliptical galaxy ends up with very little gas, very few young stars, just old stars orbiting in random directions. The galaxy is quiet, settled, red, and at its center, a supermassive black hole, dormant, having consumed its meal, having shut off the star formation, having shaped the galaxy into its final form. Elliptical galaxies are the end state, the retirement, the quiet phase. They are what galaxies become after a lifetime of activity, after mergers and star formation and black hole growth. They are peaceful, stable, slowly fading, and they will remain that way for a very long time. There is a question about whether we live in a typical place in the universe. Our solar system is in the outskirts of the Milky Way, about halfway out from the center, in a quiet region, away from the dense clusters of stars near the core. This is a good place to be, quiet, stable, safe. Near the center of the galaxy, stars are packed closely together. Gravitational interactions are common. Stellar encounters could disrupt planetary systems. Supernovae are more frequent. It is a more dangerous place, more chaotic. Out here, in the suburbs of the galaxy, things are calmer. The stars are farther apart. Disturbances are rare, and that may be important for life, for planets like Earth, for stable conditions over billions of years. If we were closer to the center, Earth might not have had the long, stable history that allowed life to evolve. So in some sense, we live in a special place, a Goldilocks zone, not too close to the center, not too far out in the empty regions, just right. But this raises a question. Is this typical? Do most life-bearing planets form in places like this? Or are we unusually lucky? We do not know. We do not yet know how common life is in the universe. We do not know how sensitive it is to location. But it is something to think about. something to wonder. That perhaps our place in the universe is not random. That perhaps the conditions here are part of why we exist. That location matters. That structure matters. That the universe has regions more favorable to life, and we happen to be in one of them. And that is another quiet mystery. Another piece of the puzzle. There is also a mystery about the shape of the Milky Way itself. The Milky Way is a spiral galaxy. It has a central bulge, a disk, spiral arms, a halo of old stars. But the disk is not flat. It is warped, twisted. At the edges, far from the center, the disk curves upward on one side and downward on the other. This warp is subtle, but it is there, and we do not fully know why. One possibility is that the warp is caused by the gravity of nearby galaxies. The Magellanic Clouds, two small galaxies that orbit the Milky Way, may be pulling on the disk, distorting it. Another possibility is that the warp is a leftover from a past collision, a merger with a smaller galaxy long ago that left the disk slightly bent. Or perhaps the warp is simply a natural feature, something that happens to spiral galaxies over time as they rotate and evolve. We do not know. The observations are difficult. The disk is large, and we are inside it, which makes it hard to see its overall shape. But the warp is there, a gentle curve, a twist, and it reminds us that even familiar objects we see every night, can hold surprises. The Milky Way is our home galaxy, but we are still learning about it, still discovering its structure, still mapping its shape. And there are still mysteries, still questions. Another mystery involves the halo of the Milky Way. The halo is a spherical region surrounding the disk. It is made of old stars, globular clusters, and dark matter. The stars in the halo are ancient, some of the oldest stars in the universe. They formed more than 13 billion years ago, shortly after the Big Bang, and they are moving in random directions, not rotating with the disk, not following the spiral structure, just orbiting the center of the galaxy in elliptical paths. These stars are remnants, survivors. They are what remains of the early universe, the first generation of stars, and they tell us about the history of the Milky Way, about how it formed, about what it was like when it was young. By studying the halo stars, astronomers can reconstruct the past. They can see traces of ancient mergers, events that happened billions of years ago, smaller galaxies that were consumed by the Milky Way, leaving behind streams of stars in the halo. The halo is a fossil record, a history book, a record of everything the Milky Way has experienced, and it is still being written. Even now, the Milky Way is consuming smaller galaxies. The Magellanic Clouds will eventually be absorbed. Their stars will join the halo. This is a slow process, a quiet process, a gradual accumulation, and it is how large galaxies grow, by consuming smaller ones, by merging, by gathering mass over time. The universe is not static. It is not frozen. It is evolving, changing, slowly rearranging itself. And we are part of that process, part of the flow, part of the ongoing story. There is a question about whether the Milky Way will always look the way it does now. The answer is no. Galaxies change, they evolve, And the Milky Way is no exception. In about 4 billion years, the Milky Way will collide with Andromeda. This collision is inevitable. The two galaxies are moving toward each other, pulled together by gravity. And when they meet, they will not simply bounce off. They will pass through each other. Their stars will intermingle. Their gas clouds will collide. And over the course of several passes, several 100 million years, they will merge. They will become one galaxy. This new galaxy has already been given a name, Milkomeda, or sometimes Milk-Dromeda. It will be an elliptical galaxy, larger than either the Milky Way or Andromeda, red, smooth, filled with old stars, and the Sun, if it still exists, will be part of it, orbiting in some new path, in some new region. But this is nothing to fear. The collision will not harm the solar system. Stars are so far apart that the chance of any collision is almost zero. The Sun will simply find itself in a new galaxy, with a new sky, new constellations, new neighbors, and life on Earth, if it still exists, will look up and see a different universe, a different arrangement of stars. But that is billions of years away. For now, the Milky Way is stable. Andromeda is still far away, and the collision is a distant future. There is time, so much time, and in that time the universe will continue, slowly, quietly, unfolding. There is a mystery about the very edge of the universe, the observable universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It is about 93 billion light-years across, and it is expanding. Every moment, more of the universe comes into view. More light arrives from distant regions. But there is a limit, a horizon. Beyond that horizon, light has not yet had time to reach us, and we will never see it, because the universe is expanding, and the more distant regions are moving away from us faster than light can travel through space. So there is a boundary, a cosmic horizon, and beyond it, the universe continues. But we cannot see it, cannot know what is there. This is humbling. It means that the universe we observe is only a small part of the total universe. The full universe may be vastly larger, perhaps infinite, and we will never know. We can only see our small patch, our observable bubble. But that bubble is still enormous. It contains hundreds of billions of galaxies, trillions of stars, more planets than we can count. And within that bubble, there is so much to explore, so much to discover, so many mysteries. We do not need to see the whole universe to be amazed by it, to be humbled by it, to find peace in it. The part we can see is enough, more than enough, and it is ours to wonder about, to study, to rest in. There is a type of light we cannot see with our eyes, infrared light. It is all around us, emitted by warm objects, by stars, by planets, by our own bodies. Everything that has heat emits infrared radiation. It is invisible to us, but it is there. A constant glow, a thermal signature. In space, infrared light is important because it can pass through dust. Visible light is blocked by dust clouds, scattered, absorbed. When we look at certain regions of space with optical telescopes, we see darkness, opacity, walls of dust. But when we look with infrared telescopes, we can see through. We can peer into the hearts of dust clouds, into star-forming regions, into the centers of galaxies. Infrared light reveals what is hidden. It shows us the stars being born, the planets forming, the warm gas swirling in the depths of molecular clouds, and it shows us the cool objects, the objects too dim to see in visible light. Brown dwarfs, cold planets, distant galaxies shrouded in dust. The universe looks different in infrared, warmer, fuller, more textured, and it reminds us that what we see is only part of what is there, that light comes in many forms, that our eyes show us just one slice of reality. There are other forms of light, other wavelengths, radio waves, microwaves, ultraviolet, X-rays, gamma rays. Each one reveals something different. Each one shows us a different aspect of the universe. Radio telescopes see cold gas, the clouds between the stars, the hydrogen that fills the galaxy, the faint signals from pulsars and distant galaxies. X-ray telescopes see hot gas, the million-degree plasmas in galaxy clusters, the material falling into black holes, the remnants of supernovae. Gamma-ray telescopes see the most energetic events, the explosions, the collisions, the places where particles are accelerated to nearly the speed of light. Together, these different forms of light give us a complete picture, a full view of the universe. Not just what shines, but what glows faintly, what radiates, what exists in the darkness. And that picture is richer than we ever imagined, more complex, more layered. The universe is not just made of things we can see, it is made of things we can detect, things we can infer, things we can measure. And each measurement reveals more. Each observation adds to the story. There is a mystery about the very first light. The cosmic microwave background is the oldest light we can see, but it is not the first light that was ever emitted. Before the cosmic microwave background, the universe was opaque. Light could not travel freely. It was scattered immediately, trapped in the dense fog of particles. But there was light. Light from the Big Bang itself. Light from the earliest moments. That light still exists, but it has been redshifted, stretched by the expansion of the universe, shifted to longer and longer wavelengths. By now, that earliest light has been stretched into wavelengths we cannot detect, longer than radio waves, longer than anything our instruments can measure. It is still there, filling the universe, a ghost of the beginning, but invisible, beyond our reach. And perhaps it always will be. Perhaps there are limits to how far back we can see, how far back we can probe. The cosmic microwave background is a wall, a boundary in time, the earliest moment we can observe directly. Before that, the universe is hidden, veiled, opaque, and we can only infer what happened, only model, only calculate. We cannot see it, cannot photograph it, cannot witness it. It is a mystery that may remain forever, a question we may never fully answer. But that is part of the beauty of science, part of the humility it teaches us. There are limits to what we can know, boundaries to our understanding, and that is okay. We do not need to know everything. We do not need to see everything. We can rest in the knowledge we have and be at peace with the mysteries that remain. There is another mystery about the nature of space itself. Is space continuous, or is it discrete? At the largest scales, space appears smooth, continuous. You can move through it in any direction. You can divide it into smaller and smaller regions, infinitely. But some theories suggest that space is not truly continuous, that at the smallest scales, space is made of discrete units, tiny chunks, pixels of reality. This is an idea from quantum gravity, the attempt to unite quantum mechanics and general relativity. In quantum mechanics, energy comes in discrete units, quanta. Photons are quanta of light. Electrons are quanta of electric charge. Perhaps space itself is also quantized. Perhaps there is a smallest possible length, a fundamental unit below which space cannot be divided further. This length is called the Planck length. It is incredibly small, about 10 to the minus 35 meters, far smaller than an atom, far smaller than anything we can measure. If space is quantized, if it is made of Planck-sized units, then the universe is fundamentally grainy, pixelated, like a digital photograph when you zoom in too far. But we do not know if this is true. We have no way to test it. The scales are too small. The energies required to probe those scales are far beyond anything we can produce. It is a theoretical idea, a possibility, a hint of what might lie at the very foundation of reality. And it is another reminder that the universe may be stranger than we can imagine, that the fabric of space and time may have a structure we cannot see, a hidden architecture. Or perhaps space is truly continuous. Perhaps there is no smallest length. Perhaps you can divide forever. We do not know. The mystery remains. But it is a quiet mystery, a gentle puzzle, not something we need to solve tonight, just something to wonder about, something to drift through as we rest. There is a phenomenon that connects the very small and the very large. Quantum fluctuations. At the quantum level, empty space is not truly empty. It is filled with fluctuations, tiny bursts of energy, virtual particles that appear and disappear in an instant. These fluctuations are random, unpredictable. They arise from the uncertainty principle, the idea that at the quantum level, nothing is perfectly still, nothing is perfectly certain. And these tiny fluctuations, these random variations, are what seeded the structure of the universe. During inflation, when the universe was expanding faster than light, quantum fluctuations were stretched, amplified, frozen into the fabric of space. Those frozen fluctuations became the tiny variations in density that we see in the cosmic microwave background. And those variations, over time, grew. They attracted matter. They formed the seeds of galaxies, the seeds of stars, the seeds of everything we see. So the structure of the universe, the pattern of galaxies and voids, the cosmic web itself, all of it arose from quantum fluctuations, from randomness at the smallest scale. This is one of the most profound connections in physics, the link between the quantum world and the cosmic scale. It shows us that the smallest things matter, that tiny fluctuations can have enormous consequences. that randomness and order are intertwined, and it is beautiful, elegant, a deep truth about how the universe works. From uncertainty comes structure. From chaos comes form. From the random dance of quantum fields comes the majestic architecture of galaxies. It is a reminder that the universe is whole, that everything is connected, that there are no separate realms, only different scales of the same reality. And we can rest in that. We can let go of the need to separate things, to categorize, to divide. The universe is one thing, and we are part of it. There is a question about whether the laws of physics are the same everywhere. We assume they are. We assume that the speed of light is the same in distant galaxies, that gravity works the same way, that atoms behave the same way, and all the evidence supports this. When we observe distant galaxies, we see the same physical processes, the same spectral lines, the same behavior. But we cannot be certain. We can only observe a small part of the universe, the observable universe, our cosmic bubble. Beyond that, we do not know. Perhaps the laws are different. Perhaps the constants have different values. Perhaps physics works in a completely different way. This is speculation, but it is allowed, because we cannot check. And if the multiverse exists, if there are many universes with different properties, then the laws almost certainly vary. Each universe would have its own physics, its own constants, its own rules. We would live in just one of them, the one where the laws allow us to exist. But we would never know about the others. We would never see them, never interact with them. They would be forever separate, forever beyond our reach. This is a strange idea, a disorienting idea, but also a humbling one. It suggests that our universe, the one we know, the one we study, is not special, not unique, just one among many. And the laws we discover, the constants we measure, are not fundamental truths about reality. They are just the local rules, the conditions of our particular universe. This changes the meaning of a law of nature. It makes it contingent, dependent, specific to our corner of existence. And it raises questions we may never answer. Questions about why our laws are what they are, why our universe is the way it is. But again, these are questions we can hold lightly. We do not need to solve them. We can simply let them be. The universe we live in is enough. The laws we have discovered are enough. The mysteries we can explore are enough. And we can rest in that. There is a type of star that pulses, a variable star. Variable stars change in brightness. They dim and brighten over and over in regular cycles. Some variable stars pulse because they are unstable. They expand and contract. Their outer layers move in and out like a slow heartbeat. As the star expands, it cools and dims. As it contracts, it heats and brightens. This cycle can take days, or weeks, or months, and it is remarkably regular, predictable, a cosmic clock. One type of variable star is especially important: Cepheid variables. Cepheids are large, bright stars, and their pulsation period is directly related to their intrinsic brightness. The longer the period, the brighter the star. This relationship makes Cepheids useful as distance markers, If you observe a Cepheid and measure its period, you know how bright it truly is. And if you know how bright it truly is, and you measure how bright it appears, you can calculate how far away it is. This is how Edwin Hubble measured the distances to other galaxies. He found Cepheids in Andromeda. He measured their periods. He calculated their distances. And he discovered that Andromeda was far away, so far that it could not be part of the Milky Way. It had to be a separate galaxy. This was a revolutionary discovery. It showed that the universe was much larger than anyone had thought, that the Milky Way was just one galaxy among many, and it opened the door to modern cosmology, to the study of the universe as a whole. Cepheids are still used today. They are one of the first steps on the cosmic distance ladder, the series of methods we use to measure distances to farther and farther objects. And they are reliable, steady, pulsing quietly in the darkness, telling us how far away they are. There are other variable stars that vary for different reasons, eclipsing binaries, two stars orbiting each other. When one passes in front of the other, the combined light dims. When they are side by side, the light is brighter. Flare stars, small stars that occasionally brighten suddenly, emitting bursts of energy. Novae, white dwarfs that accumulate matter from a companion star and occasionally explode, brightening dramatically before fading again. Each type of variable tells us something. Each one reveals a different aspect of stellar physics, and together they remind us that stars are not static. They are dynamic, changing, evolving. The night sky may appear still, unchanging, but if you watch carefully, if you measure precisely, you see that it is alive, that stars breathe, pulse, flare, that the universe is always in motion, always transforming. And we can watch, we can observe, we can rest in the knowledge that even the stars are restful in their changes, that their cycles are slow, predictable, gentle. There is a mystery about the fate of planets. There is a place where all the mysteries converge, in your mind, in your awareness, in this moment. All the questions we have explored, all the puzzles, all the unknowns, they exist because we are here, to ask them, to wonder about them. The universe existed for billions of years, before conscious beings, before observers, before anyone to notice the stars, the galaxies, the slow unfolding of space and time. And it will exist for billions more, after we are gone, after consciousness has faded, after the last observer has disappeared. But right now, in this brief moment, the universe is aware of itself, through us, through you. You are made of atoms, forged in stars, scattered through space, gathered by gravity, assembled into planets, into oceans, into cells, into thoughts. You are stardust, contemplating stars, the universe, looking at itself, asking questions, seeking understanding. This is extraordinary, rare, perhaps unique in all the cosmos, or perhaps common. We do not know, but either way, it is precious. This moment, this awareness, this quiet wondering, and it does not require effort, does not require struggle, does not require staying awake. The universe will continue, with or without. Your attention, your consciousness, your awareness, It has no need of witnesses, of observers, of understanding. It simply is, and you can simply be part of it, resting in it, held by it. There is a rhythm to everything. The expansion of the universe, the rotation of galaxies, the orbits of stars, the cycles of planets, day and night, seasons, tides, life and death, waking and sleeping, all of it, part of the same rhythm, the same flow, the same dance, and you are dancing, even now, even as you rest. Your heart beats, your lungs breathe, your cells divide and repair, your brain processes, sorts, consolidates, all without your direction, all without your effort. The body knows what to do. The universe knows what to do. And you can trust that knowing, can surrender to that rhythm. There is nothing to control, nothing to force, nothing to make happen, just the natural unfolding of rest, of restoration, of sleep, like the slow cooling of a white dwarf, like the gentle drift of galaxies through space. Everything happens in its own time, at its own pace, and sleep will come when it comes, not before, not after, just when it is ready. There is a concept in astronomy called deep time, the vast spans of cosmic history, billions of years, timescales so long that human experience disappears into them like a grain of sand on an infinite beach. But deep time also reminds us that this moment, this brief flicker, this instant of consciousness is no less real, no less valid. For being temporary, a mayfly lives for one day, but that day is its entire life, its whole existence, complete, whole, perfect, and we live for decades, perhaps a century, a brief moment in cosmic time, but our moment is complete, whole, perfect. This night, this rest, this sleep is part of that, part of your moment, part of your experience, and it deserves your gentleness, your acceptance, your peace. You do not need to achieve anything tonight, not even sleep, just rest, just stillness, just being here. And if sleep comes, it comes, and if it does not, that is also okay. The body will rest, regardless, will restore itself in its own way. There is a mystery about gratitude. Why do we feel grateful for existence, for beauty, for the universe? Gratitude serves no evolutionary purpose, provides no survival advantage, and yet we feel it, perhaps. Gratitude is the universe appreciating itself through us, a moment of recognition, of acknowledgement that all of this vast complexity, this elegant structure, this beautiful mystery exists, and we are here to witness it for however brief a time. That is worth gratitude, worth wonder, worth peace, The stars do not know they are beautiful. The galaxies do not know they are vast. The universe does not know it exists, but you do. You know, you see, you understand, even if only partially, imperfectly. And that knowing, that seeing, is a gift, not to you, but through you, to the cosmos. You are how the universe knows itself. And tonight, you can rest in that knowing, can let it settle into your bones, your breath, your stillness. There is nothing more to do, nowhere else to be, no other question to answer. Just this, just now, just rest. The mysteries will remain. The stars will continue burning. The galaxies will continue turning. The universe will continue expanding. All of it happening slowly, quietly, patiently. And you are part of that patience, part of that quiet, part of that slow unfolding. Your breathing is slowing now. Your thoughts are spacing out. Your body is settling deeper. This is natural. This is right. This is how it should be. The weight of everything is lifting. The questions are fading. The need to know, to understand, to stay awake is dissolving like morning mist in sunlight, like stars fading at dawn, like consciousness slipping into sleep. And you can let it slip, can allow it to fade, can surrender to the darkness, to the quiet, to the rest. There is no effort required, no technique to master, no goal to achieve, just letting go, just releasing, just being. The universe is here, has always been here, will always be here, and you are safe in it, held by it, part of it. The cosmic web stretches across billions of light years, connecting everything to everything else, and you are one of those connections, one thread in the web, woven into the fabric of reality. You cannot fall out of the universe, cannot be separate from it. You are it, and it is you, and in that unity, that oneness, there is deep peace, deep rest, deep letting go. The boundaries between you and the universe are dissolving now. The separation between waking and sleeping is blurring. You are floating, drifting, becoming less solid, less defined, less individual, just awareness, fading into the whole, into the darkness, into the cosmic night. And that is perfect, that is natural, that is exactly how it should be. Sleep is not an absence, it is a presence, a state of being, as real, as valid as waking, just different, just quieter, just deeper. And you are moving into it now, gently, naturally, without resistance. The stars are there in the darkness, even when you cannot see them, even when your eyes are closed. The universe is there, unfolding, expanding, existing, and you are there too, resting in it, part of it, one with it. There is nothing left to say. The mysteries are quiet now. The questions have faded. The universe continues its slow dance, and you can sleep now, deeply, peacefully, completely. Rest, sleep, be here in the quiet, in the dark, in the infinite peace of the cosmos. Sleep now, sleep. The Milky Way is a spiral galaxy. This is one of the first things we know about it. From our position inside, it is difficult to see the overall shape, but through careful observation, through measuring distances and velocities, we have mapped it. The Milky Way has a central bulge, a dense concentration of old stars at the core. Around that bulge, a flat disk extends outward, and within that disk, spiral arms wind their way through space. These spiral arms are not solid structures. They are not fixed. They are density waves, regions where stars and gas are slightly more concentrated. And as the galaxy rotates, these density waves persist, even as individual stars move through them. Think of traffic on a highway. Sometimes cars bunch up. A slow-moving wave of density moves along the road, even though individual cars enter and leave the wave. The wave persists. The pattern remains. Spiral arms work the same way. Stars enter the arm, slow down slightly, and then leave. But the arm remains, a permanent wave in the disk of the galaxy. We live in one of these spiral arms, the Orion arm, sometimes called the Orion Spur, a minor arm branching off from one of the major arms, about halfway out from the center of the galaxy. It is a quiet place, relatively calm, away from the dense, chaotic core, away from the violent, star-forming regions of the major arms, a good place for life, for planets, for stability over billions of years. But even here, in this quiet arm, there are mysteries, things we do not understand, things that surprise us. There is a mystery about the number of spiral arms. When astronomers first mapped the Milky Way, they thought it had 4 major spiral arms, but more recent observations suggest it might have only 2, or perhaps 2 major arms and several minor ones. The structure is not as clear as we would like, because we are inside the galaxy, looking out. Dust blocks our view. Distances are hard to measure. The picture is incomplete, and the spiral arms themselves are not perfectly defined. They are fuzzy, fragmentary. They branch and merge. They fade in some regions and brighten in others. So we are still mapping our own galaxy, still trying to understand its structure, still piecing together the shape of our home. This is humbling, that even the galaxy we live in, the one we have studied for centuries, still holds basic questions, still surprises us with its complexity. There is a mystery about the rotation of the Milky Way. When astronomers measure how fast different parts of the galaxy are rotating, they find something strange. The stars near the center rotate quickly. This makes sense. They are close to the dense core, where most of the mass is concentrated. Gravity pulls them into fast orbits. But the stars farther out, near the edge of the disk, also rotate quickly, too quickly. According to the laws of gravity, based on the visible matter in the galaxy, the outer stars should be moving slower, much slower, like planets in a solar system. The farther out you go, the slower the orbit. But in the Milky Way, the rotation speed stays roughly constant, even at the edge, even far from the center. This is called a flat rotation curve, and it was one of the first pieces of evidence for dark matter. There must be more mass in the galaxy than we can see, invisible mass, distributed in a large halo around the visible disk, providing the extra gravity needed to keep the outer stars moving so fast. Without dark matter, the Milky Way would fly apart. The outer stars would escape. The galaxy would dissolve. But the dark matter holds it together, keeps it stable, keeps it intact. And yet we do not know what dark matter is. We cannot see it, cannot touch it, cannot detect it directly. It is there. We know it is there, but it remains hidden, a ghost, a presence we infer but cannot grasp. The Milky Way is embedded in a halo of dark matter, a sphere of invisible mass extending far beyond the visible stars, perhaps 10 times larger than the luminous disk. And within that halo, we move, we orbit, we exist, held by forces we cannot see, shaped by matter we cannot touch. There is a mystery about the age of the stars. When astronomers measure the ages of stars in the Milky Way, they find a range. Some stars are very old, more than 13 billion years old, almost as old as the universe itself. These ancient stars are found in the halo, in globular clusters, in the outer regions of the galaxy. They formed when the Milky Way was young, when it was just beginning to take shape, and they have been here ever since. Survivors, witnesses to the entire history of the galaxy. Other stars are much younger, a few million years old, newborns, just beginning their lives. These young stars are found in the disk, in the spiral arms, in star-forming regions where gas and dust are still collapsing, still creating new stars. But here is the mystery. There is a gap, a period in the history of the Milky Way when very few stars formed, about 10 billion years ago. For a few billion years. Star formation slowed, almost stopped, and then it picked up again. We do not know why. What caused the pause? What stopped the gas from collapsing? What prevented new stars from forming? Perhaps the Milky Way ran out of gas. Perhaps the gas was heated by supernova, by the radiation from massive stars, and it could not cool down enough to collapse. Or perhaps the Milky Way merged with another galaxy, and the merger disrupted the gas, stirred it up, prevented it from settling into star-forming clouds. We do not know. The history of the Milky Way is written in the ages of its stars, but the story is incomplete. There are gaps, missing chapters, and we are still trying to read it, still trying to understand what happened. Billions of years ago, when the galaxy was young, there is a structure in the Milky Way that we did not expect: a warp. The disk of the Milky Way is not perfectly flat. At the edges, far from the center, it curves, bends, twists. On one side, the disk curves upward. On the other side, it curves downward, like a bent record, a warped plate. This warp is subtle, only a few thousand light years, but it is there, and we do not fully understand why. One possibility is that the warp is caused by the gravity of the Magellanic Clouds, two small galaxies that orbit the Milky Way. They pull on the disk, distort it, create the warp. Another possibility is that the warp is a remnant of a past collision, a merger with a smaller galaxy long ago. That left the disk bent, twisted. Or perhaps the warp is caused by the dark matter halo. Perhaps the halo is not perfectly spherical. Perhaps it is lopsided, tilted, and its gravity pulls the disk into a warp. We do not know. The warp is there. We can measure it, but we do not understand its cause. And this is a reminder that even familiar structures, even things we see every night, can hold surprises, can be more complex than they appear. The Milky Way is not a simple disk. It is warped, twisted, dynamic, a living structure, changing over time. There is a mystery about the spiral arms themselves. Why do they exist? What creates them? What maintains them? Spiral arms are common in galaxies. Most disk galaxies have them, but we do not fully understand how they form. One theory is that spiral arms are density waves, patterns that move through the disk, created by gravitational instabilities, by the way gravity pulls on the gas in stars. The arms are not made of the same stars. Stars move through the arms. They enter, they slow down, they leave, but the pattern persists. Like a wave in water, the water molecules move up and down, but the wave moves across the surface. The pattern travels, even as the individual particles stay in place. Spiral arms work the same way. The pattern rotates, slowly, more slowly than the stars themselves. And as stars enter the arm, they compress. They trigger star formation. They brighten the arm. But there are problems with this theory. The density wave should wind up over time. The arms should become tighter, more twisted. Eventually, they should disappear. But spiral arms persist. For billions of years, they remain stable, clear. So something must be maintaining them, refreshing them, preventing them from winding up. Perhaps interactions with other galaxies, perhaps the flow of gas into the galaxy, perhaps the dark matter halo. We do not know. Spiral arms are one of the enduring mysteries of galactic structure. There is a region of the Milky Way where many stars are being born. The Sagittarius B2 cloud. It is a giant molecular cloud, one of the largest in the galaxy, about 3 million times the mass of the Sun, all packed into a region a few hundred light-years across. Inside this cloud, stars are forming, hundreds of them, collapsing out of the gas, lighting up, beginning their lives. But Sagittarius B2 is also strange. It contains complex molecules, organic molecules, the building blocks of life, amino acids, sugars, alcohols, ethers, all floating in the cloud, mixed with the gas and dust. These molecules form through chemistry, reactions on the surfaces of dust grains, in the cold, dense regions of the cloud. And they tell us something important, that the chemistry of life is not unique to Earth. It is happening throughout the galaxy, in molecular clouds, in star-forming regions. The ingredients of life are common, widespread, natural. This does not mean that life is common. The jump from chemistry to biology is still a mystery, still unexplained. But it means that the first steps are happening everywhere, that the universe is full of the raw materials, the building blocks, the potential, and that is comforting, in a way, that we are not alone in having the ingredients, that the chemistry that led to us is happening right now throughout the Milky Way. There is a mystery about the bar, the central bar. Most spiral galaxies have a bar, a rectangular structure in the center made of stars, stretching across the core. The Milky Way has a bar. We have known this for a few decades, but we did not always know, because we are inside the galaxy. The bar is hard to see. We are looking at it edge on, from within. But infrared observations revealed it, showed the concentration of stars, the elongated structure, the bar. The bar is about 27,000 light-years long, and it rotates, slowly, once every few 100 million years. But here is the mystery. We do not know how the bar formed, or why it is there, or what it does. Bars are common. Perhaps 2/3 of spiral galaxies have them, so they must be important, must serve some purpose, must play some role in the evolution of galaxies. One idea is that bars funnel gas toward the center. They create gravitational torques that pull gas inward, toward the core, where it can fuel star formation, or feed the central black hole. Another idea is that bars redistribute angular momentum. They move it from the inner galaxy to the outer galaxy, and this changes the structure, changes the rotation, changes the disk. But we do not know for sure. The bar is there. We can see it, measure it, but we do not fully understand it. And that is another reminder that the Milky Way, our home, is still full of puzzles, still revealing itself. Slowly, there's a place in the Milky Way where stars are packed incredibly close together. The central parsec, the innermost light year of the galaxy, around the supermassive black hole at the center. In this region, there are millions of stars, packed into a tiny volume. The density is thousands of times higher than near the Sun. Stars pass close to each other, interact, collide, merge, and many of these stars are unusual, massive, hot, blue, young. This is strange, because the center of the galaxy is a harsh place, strong tidal forces, intense radiation, frequent supernova. It should be difficult for stars to form there, difficult for gas to collapse, difficult for planets to survive. And yet, there are young stars, very young, only a few million years old. How did they form? How did they get there? How do they survive? One idea is that they formed elsewhere, in the disk, and then migrated inward, pulled by the gravity of the black hole. Another idea is that they formed in place, in a disk of gas around the black hole. Despite the harsh conditions, we do not know. The central parsec is one of the most extreme environments in the galaxy, and it is full of surprises, full of mysteries. There is a mystery about the halo, the spherical region surrounding the disk, made of old stars, globular clusters, dark matter. The stars in the halo are ancient, some of the oldest in the universe, formed shortly after the Big Bang, and they are moving in strange ways, not rotating with the disk, not following the spiral structure, just orbiting the center, in random directions, in elliptical paths. This suggests that the halo formed differently from the disk, perhaps earlier, perhaps more chaotically. But here is the mystery. When astronomers study the stars in the halo, they find streams, filaments, structures. These streams are the remnants of smaller galaxies, dwarf galaxies that were consumed by the Milky Way, torn apart by tidal forces, scattered across the halo. And by studying these streams, astronomers can reconstruct the history, the mergers, the collisions, the growth of the Milky Way. But there are more streams than expected, more structure, more complexity. It suggests that the Milky Way has been eating other galaxies constantly, throughout its history, growing, accumulating mass, building itself up. And it is still happening. Right now, the Milky Way is consuming the Magellanic Clouds. Slowly, over hundreds of millions of years, their stars will join the halo, their gas will join the disk, and the Milky Way will grow, slightly, incrementally. This is how galaxies evolve, through mergers, through cannibalism, through the slow accumulation of smaller structures. The Milky Way is not a static object. It is growing, changing, evolving, and we are part of that, part of the ongoing story. You can rest in that, in the knowledge that we are part of something dynamic, something living, something that has been growing for billions of years, and will continue long after we are gone. There is a mystery about the globular clusters. These are ancient collections of stars, spherical, dense, each containing hundreds of thousands of stars, sometimes millions. The Milky Way has about 150 globular clusters, scattered through the halo, orbiting the galactic center in long elliptical paths. And they are old, very old. Most of them formed more than 10 billion years ago, when the universe was young, when the Milky Way was just beginning to take shape. But here is the mystery. All the stars in a globular cluster formed at the same time, from the same cloud of gas. They are siblings, family, and yet, when astronomers study them closely, they find something strange. Multiple populations, stars with different compositions, different chemical signatures. Some stars are enriched in certain elements, others are depleted, as if they came from different generations, different formation events. But how is this possible? If all the stars formed together at the same time, how can they have different compositions? One idea is that the cluster formed in multiple bursts. The first generation of stars formed, lived, died, and enriched the remaining gas with heavy elements. Then a second generation formed from that enriched gas. But this raises questions. How did the cluster hold onto the gas? How did it prevent the gas from escaping? after the first supernovae, after the first stellar winds. Globular clusters are not massive enough to hold on to hot gas. The gas should escape, disperse, leave the cluster, and yet somehow it stayed, long enough for a second generation to form. We do not know how. We do not understand the process. The details are unclear. Globular clusters are puzzles, ancient, beautiful, but mysterious. There's a type of star found in globular clusters that should not exist. Blue stragglers. In a globular cluster, all the stars formed at the same time, and massive stars burn out quickly, within a few million years, or a few 100 million years. After 10 billion years, all the massive stars should be gone, dead, faded. Only the low-mass stars should remain, red dwarfs, small, dim, cool. But when we look at globular clusters, we see blue stars, hot stars, massive stars, stars that should have died long ago. These are blue stragglers, and they are a mystery. How did they survive? How are they still burning? How can they still be blue and hot after 10 billion years? The answer, we think, is collisions, or mergers. In the dense core of a globular cluster, stars pass very close to each other. Sometimes they collide, they merge. Two small stars become one larger star. And that larger star is hotter, brighter, bluer. It looks like a young, massive star, but it is not. It is a merged star, a product of collision. Blue stragglers are the result of crowding, of density, of the chaotic interactions that happen when stars are packed so close together. They are accidents, survivors, imposters, and they remind us that not everything is what it seems, that age and appearance do not always match, that the universe has ways of creating the unexpected. There is a region of the Milky Way where something strange is happening. The Fermi bubbles. In 2010, astronomers discovered two enormous structures, extending above and below the galactic center, like two balloons, two lobes, stretching for 25,000 light-years in each direction. These structures emit gamma rays, high-energy radiation, the most energetic form of light, and they are symmetrical, perfectly balanced, one above the disk, one below. But we do not know what created them. We do not know what they are made of. We do not know how old they are. One idea is that they are the result of past activity from the supermassive black hole at the center of the galaxy. Perhaps a few million years ago, the black hole was active, feeding, consuming gas, and it ejected jets of particles, plasma, energy, shooting outward at nearly the speed of light. Those jets carved out the bubbles, pushed the gas aside, created the structures we see today. Another idea is that the bubbles are caused by star formation, a burst of star formation near the galactic center millions of years ago, followed by many supernovae, explosions that drove gas outward, creating the bubbles. We do not know. The Fermi bubbles are relatively recent discoveries, and they are still being studied, still being analyzed. But they tell us something important, that the Milky Way is active, that things happen, even near the center, even in regions we thought were quiet. The galaxy is not static. It is dynamic, changing, erupting, creating structures on scales we are only beginning to understand. there is a mystery about the metallicity gradient. Metallicity is the amount of heavy elements in a star. Elements heavier than hydrogen and helium, carbon, oxygen, iron, silicon. These elements are made in stars, through fusion, through supernovae, and they are scattered through space, enriching the gas clouds, the next generation of stars. So over time, the galaxy becomes more metal-rich. Each generation of stars has more heavy elements than the last. But here is the mystery. The metallicity is not uniform. It varies across the galaxy. Stars near the center are more metal-rich. Stars near the edge are more metal-poor. This is called the metallicity gradient, and it tells us something about how the galaxy formed, how it evolved. One idea is that the center formed first. It collapsed first, formed stars first, and those stars enriched the gas. Quickly, the outer regions formed later, more slowly, and they have had less time to be enriched. Less time for supernovae to add heavy elements. Another idea is that the outer regions are being diluted by pristine gas, falling in from outside the galaxy, from the intergalactic medium. This gas has no heavy elements, and it mixes with the existing gas, diluting the metallicity. Both ideas are probably partly true. The metallicity gradient is the result of many processes: formation, enrichment, accretion, mixing. And by studying it, we can learn about the history of the Milky Way, how it grew, how it changed, how it became what it is today. There is a place in the Milky Way where stars are dying, planetary nebulae. When a star like the Sun exhausts its fuel, it swells, becomes a red giant. Its outer layers expand, cool, redden, and then it sheds those layers, gently, gradually. The outer envelope drifts away into space, leaving behind the hot core, a white dwarf. The ejected gas glows, illuminated by the ultraviolet light from the white dwarf. It shines in beautiful colors: red, green, blue, pink. These glowing shells are called planetary nebulae, not because they have anything to do with planets, but because early astronomers thought they looked like planets through their telescopes. Round, disc-shaped. But they are not round, not always. They come in many shapes: spheres, ellipses, bipolar lobes, spirals, jets, and we do not fully understand why. Why do dying stars create such complex shapes? What determines the structure of a planetary nebula? Part of the answer is rotation. If the star is rotating, the ejected gas is shaped by centrifugal force, flattened into a disk, or thrown out along the poles. Part of the answer is magnetic fields. The star's magnetic field can channel the gas, direct it, shape it into jets or spirals. And part of the answer is binary companions. If the dying star has a companion, another star orbiting it, that companion can shape the outflow, create asymmetry, create complexity. But many planetary nebulae are still unexplained. Their shapes are too complex, too structured, too beautiful. They are works of art, created by physics, by the final acts of dying stars. And they remind us that even death, even endings, can be beautiful, can create something new, something unexpected. There is a mystery about the supernova remnants. When a massive star explodes, a supernova, it releases enormous energy. It blasts its outer layers into space at thousands of kilometers per second. That expanding shell of gas is called a supernova remnant, and it glows for thousands of years, heated by the explosion. Cooling slowly, the Milky Way has many supernova remnants scattered through the disk, evidence of past explosions, past deaths. Some are young, only a few hundred years old, still bright, still expanding rapidly, like the Crab Nebula, the remnant of a supernova that was seen on Earth in 1054 CE. Others are old, tens of thousands of years old, faint, faded, merged with the surrounding gas. But here is the mystery. When astronomers count the supernova remnants in the Milky Way, they find too few. Based on the number of massive stars, based on the rate of star formation, there should be more remnants, many more. Where are they? Where did they go? One possibility is that many remnants have faded, dispersed, merged with the interstellar medium, and become invisible, undetectable. Another possibility is that many supernovae happen in regions we cannot see, hidden by dust, obscured by gas, beyond our view. Or perhaps the rate of supernovae is lower than we thought. Perhaps massive stars do not always explode. Perhaps some collapse directly into black holes, without a visible explosion. We do not know. The missing supernova remnants are a puzzle, a gap in our inventory, a reminder that even in our own galaxy, we do not see everything, do not know everything. There is a type of object in the Milky Way that we discovered by accident: magnetars. Magnetars are neutron stars, incredibly dense, incredibly compact, the remnants of massive stars that exploded as supernova. But magnetars are special. They have the strongest magnetic fields in the universe, trillions of times stronger than Earth's magnetic field, quadrillions of times stronger than any human-made magnet. These magnetic fields are so strong that they warp the vacuum. They polarize empty space. They make atoms stretch into needle shapes. And the magnetic fields create starquakes. The crust of the neutron star cracks, shifts, releases energy, and that energy is emitted as X-rays, gamma rays, bursts of radiation. Magnetars flare, unpredictably, violently, releasing in 1/10 of a second, more energy than the sun emits in a year, and we do not fully understand them. We do not know how such strong magnetic fields form. We do not know why some neutron stars become magnetars, and others do not. We do not know how long the magnetic fields last, whether they decay, whether they strengthen, whether they change over time. Magnetars are rare. Only about 30 have been found in the Milky Way, but they may be more common than we think, hidden, dormant, waiting to flare. And they remind us that the universe creates extremes, conditions we can barely imagine, objects that push the limits of physics, that challenge our understanding. There is a mystery about the high-velocity clouds. Throughout the halo of the Milky Way, there are clouds of gas, moving at high speeds, hundreds of kilometers per second. These clouds are not rotating with the galaxy. They are falling, plunging toward the disk, or being ejected, launched outward. Some are falling in, fresh gas, from the intergalactic medium, being accreted by the Milky Way, adding to the disk, fueling star formation. Others are being ejected, blown out by supernovae. by stellar winds, by the activity near the galactic center. This is called the galactic fountain. Gas falls in, stars form, stars die, gas is ejected, and then it falls back, eventually recycled. But we do not understand all the details. We do not know where all the clouds come from. We do not know why they move the way they do. Some high-velocity clouds are massive, millions of times the mass of the sun, and they are dark. They do not glow. They are only visible in radio wavelengths through the emission of neutral hydrogen. One of the largest is called the Smith Cloud. It is falling toward the Milky Way, and in about 30 million years, it will hit the disk and trigger a burst of star formation, a collision, in slow motion, invisible to the naked eye, but measurable, predictable. And it reminds us that the Milky Way is not isolated. It is connected to its surroundings, to the halo, to the intergalactic medium, to the flow of gas in and out. The galaxy breathes. In a sense, it inhales gas, forms stars, and exhales enriched gas. A cycle, a rhythm, ongoing. For billions of years, there's a structure in the Milky Way that wraps around it. The monochorous ring. It is a stream of stars circling the galaxy, like a ribbon, a band wrapped around the disk. The monochorous ring was discovered in the early 2000s, and it was unexpected, surprising. At first, astronomers thought it might be part of the disk, a warp, a ripple, but it is different, distinct, separate. The stars in the ring have a different velocity, a different composition, a different origin. And the best explanation is that the monochorous ring is the remnant of a dwarf galaxy, a small galaxy that was torn apart by the Milky Way, its stars scattered. Stretched into a ring, the dwarf galaxy fell into the Milky Way billions of years ago, and tidal forces pulled it apart, shredded it, dissolved it. But the stars remain, still orbiting, still following the path of their parent galaxy, even though that galaxy no longer exists. This is the fate of small galaxies near large ones. They are consumed, destroyed, their stars added to the halo, their gas added to the disk. And the Milky Way is full of these remnants, these ghosts, evidence of past mergers, past collisions. Each stream, each ring, each structure in the halo tells a story of a galaxy that once was and is no more. You can let that settle. Let it rest in your mind. The idea that the Milky Way is built from smaller pieces, from galaxies that came before, that gave themselves to create what we have now. There is beauty in that, and peace, in the cycle, in the transformation, in the way endings become beginnings. There is a mystery about the stellar streams. Throughout the halo of the Milky Way, there are rivers of stars, long, thin streams, stretching for thousands of light years, following curved paths through space. These streams are the remnants of globular clusters, or dwarf galaxies, that came too close to the Milky Way and were pulled apart by tidal forces. As the object orbits the galaxy, the stars nearest to the galactic center feel stronger gravity than the stars farthest away. This difference stretches the object, elongates it, eventually tears it apart, and the stars spread out along the orbit, leading and trailing, forming a stream. One of the most famous is the Sagittarius stream, the remnant of the Sagittarius dwarf elliptical galaxy, a small galaxy that is currently being consumed by the Milky Way. The stream wraps around the entire galaxy, multiple times, a long ribbon of stars, tracing the orbit of the dying galaxy. By mapping these streams, astronomers can learn about the Milky Way's gravity, its mass distribution, the shape of its dark matter halo. Because the streams respond to gravity, they follow the gravitational field. They reveal the invisible structure, the hidden mass. But many streams are still unexplained. Their orbits do not match simple models. They have kinks, gaps, irregularities. Perhaps there are clumps of dark matter, perturbing the streams, pulling on them, creating the irregularities. Or perhaps the Milky Way's gravitational field is more complex than we thought. Not smooth, not symmetric, but lumpy, structured. The streams are clues, evidence, trails left behind, and we are following them, trying to understand what they tell us about the galaxy, about its history, about its dark matter. There is a mystery about the thick disk. The Milky Way does not have just one disk. It has two. The thin disk is where most of the stars are, where the sun is, where star formation happens. It is about 1,000 light-years thick. But there is also a thick disk, above and below the thin disk, about 3,000 light-years thick, made of older stars, different chemistry, different kinematics. The stars in the thick disk are moving differently. They have higher velocities, more random motions. They are not rotating as quickly with the galaxy, and they are older, about 10 billion years old, formed when the Milky Way was young. But we do not know how the thick disk formed. There are several ideas, several theories, but no consensus. One idea is that the thick disk formed through heating. The thin disk was heated by something, by mergers, by interactions with satellite galaxies, and the heating puffed it up, thickened it. Another idea is that the thick disk formed separately, earlier, through a different process, perhaps from gas that was more turbulent, more chaotic, that settled into a thicker structure. Or perhaps the thick disk is made of accreted stars, stars from other galaxies, dwarf galaxies that merged with the Milky Way, and their stars now form the thick disk. Each idea has evidence. Each idea has problems. The truth may be a combination, multiple processes working together. But the thick disk is there, a distinct population, a separate structure, and it tells us that the Milky Way is layered, complex, built over time, through different phases, different processes. There is a region near the center of the Milky Way called the Zone of Avoidance. This is not a real structure. It is an observational problem, a blind spot. The disk of the Milky Way is full of dust, and dust blocks visible light. It absorbs it, scatters it, makes everything behind it dark. Near the galactic center, the dust is especially thick, dense, opaque, and this creates a zone, a band across the sky, where we cannot see distant galaxies, cannot see through the Milky Way, cannot observe what lies beyond. This zone covers about 20% of the sky, a significant fraction, and it limits our observations, our surveys, our understanding of the universe beyond. But we can see through dust, with infrared light, with radio waves. These wavelengths are not blocked as easily. They penetrate the dust, reveal what is hidden, and using these wavelengths, astronomers have begun to map the zone of avoidance, to discover what is there, what was hidden. They have found galaxies, clusters of galaxies, structures we did not know existed because they were hidden behind the dust. One of the most surprising discoveries is the Great Attractor, a massive concentration of galaxies hidden in the zone of avoidance, pulling on the Milky Way, pulling on our entire local group of galaxies. We are moving toward it at hundreds of kilometers per second, drawn by its gravity, but we can barely see it. It is obscured, shrouded, a massive structure pulling us toward it, and we are only beginning to understand what it is, what it contains. The zone of avoidance reminds us that our view is limited, that we are inside the galaxy, looking out through dust and gas, that there are things we cannot see, things hidden from us by our own galactic environment. There is a mystery about the velocity dispersion. When astronomers measure the velocities of stars in the Milky Way, they find that the velocities vary. Some stars move faster, some slower, in random directions. This variation is called velocity dispersion, and it tells us about the dynamics of the galaxy, about how stars interact, how they move. In the thin disk, the velocity dispersion is low. Stars are moving mostly in the same direction, rotating together, smooth, organized. But in the thick disk, the velocity dispersion is higher. Stars are moving in more random directions, more chaotic, less organized. And in the halo, the velocity dispersion is even higher. Stars moving in all directions, orbiting the center, but not rotating with the disk. This makes sense. The halo is older, formed differently. Its stars were never part of the organized disk. They are remnants, survivors, from the early universe. But here is the mystery. The velocity dispersion is not constant. It varies in unexpected ways. Some regions of the disk have higher dispersion than expected, as if they were heated, stirred, disturbed. And some regions of the halo have lower dispersion than expected, as if they were cold, organized, structured. These variations tell us about the history, about past events, mergers, interactions, disturbances. Each bump, each irregularity, is evidence of something that happened long ago that left its mark on the velocities of stars. And by studying these variations, astronomers are reconstructing the past, piecing together the story of how the Milky Way became what it is today. There is a type of star in the Milky Way that is moving incredibly fast, hypervelocity stars. These stars are traveling at more than 1,000 kilometers per second, fast enough to escape the galaxy, fast enough to leave the Milky Way entirely. And we do not fully understand how they got so much speed, how they were accelerated, how they were launched. One idea is that they were ejected by the supermassive black hole at the center of the galaxy. If a binary star system wanders too close to the black hole can capture one star and eject the other at very high speed. The captured star falls toward the black hole, and the other star is flung outward, like a slingshot, accelerated by the black hole's gravity. This is called the Hill's mechanism, and it explains some hypervelocity stars, but not all. Some hypervelocity stars are coming from the wrong direction, not from the galactic center, but from the disk, from the halo. Perhaps they were ejected by supernova, by the explosion of a companion star. The blast accelerated them, launched them. Or perhaps they were ejected by interactions with intermediate mass black holes, smaller black holes, wandering through the galaxy that could accelerate stars through close encounters? We do not know. Hypervelocity stars are rare. Only a few dozen have been found, and each one raises questions about where it came from, how it was accelerated, where it is going. Some will escape the galaxy. They will leave the Milky Way and drift through intergalactic space, forever, exiled, alone. Others will slow down, fall back, return to the galaxy, eventually. But all of them are travelers, wanderers, moving through the darkness at incredible speeds, carrying mysteries with them. There is a mystery about the satellite galaxies. The Milky Way is not alone. It is surrounded by smaller galaxies, dwarf galaxies, orbiting it, bound by gravity. We know of about 60 satellite galaxies. Some are bright, easy to see, like the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere. Others are faint, very faint, only discovered recently, through careful surveys, through searching for faint concentrations of stars. These ultra-faint dwarf galaxies are tiny. They contain only a few thousand stars, compared to the Milky Way's hundreds of billions. But they are important because they are dominated by dark matter. Most of their mass is invisible. Only the stars are visible, and by studying them, we can learn about dark matter, about how it behaves, how it clumps, how it forms structures. But here is the mystery. Simulations of galaxy formation predict that there should be many more satellite galaxies, hundreds, perhaps thousands. But we only see about 60. Where are the rest? Why are they missing? This is called the missing satellites problem, and there are several possible solutions. One is that the missing satellites are there, but they are too faint to see. They contain so few stars that we cannot detect them, even with our best telescopes. Another is that star formation was suppressed in small, dark matter halos. Only the largest halos could form stars. The rest remained dark, invisible. Or perhaps dark matter is different than we thought. Perhaps it interacts with itself, self-annihilates, and this prevents small structures from forming. We do not know. The missing satellites problem is one of the puzzles of cosmology, one of the tensions between theory and observation, and it reminds us that even our local environment, even the galaxies closest to us, still hold mysteries, still challenge our understanding. There is a structure in the Milky Way that is incredibly old, the Helmy Stream. It is a stellar stream, like the others we have talked about. But this one is special because it is ancient. The stars in the Helmy Stream formed more than 13 billion years ago in a small dwarf galaxy that merged with the Milky Way very early in its history. The dwarf galaxy was torn apart, its stars scattered, and they have been orbiting the Milky Way ever since, for more than 10 billion years. The Helmy Stream is a fossil, a relic, evidence of one of the earliest mergers, one of the building blocks of the Milky Way. And by studying it, astronomers can learn about the conditions in the early universe, about the first galaxies, about how structure formed. The stars in the Helmy Stream are metal-poor. They contain very few heavy elements because they formed before many generations of stars had enriched the gas. They are pristine, almost, as close as we can get to the first stars, the first generation, and they tell us about that time, about what the universe was like when it was young, when galaxies were just beginning to form. The Helmi stream is a time capsule, a message from the distant past, and it is still here, still orbiting, still carrying its story through the Milky Way. There is a mystery about the open clusters. Unlike globular clusters, which are ancient and dense, open clusters are young and loose. They contain a few hundred to a few thousand stars, all formed together from the same molecular cloud. Recently, within the last few 100 million years, open clusters are found in the disk, in the spiral arms, where star formation is ongoing, where gas and dust are still collapsing. The Pleiades is an open cluster, visible to the naked eye, a small grouping of bright blue stars, young, hot, still surrounded by faint nebulosity, the remnants of the cloud they formed from. But open clusters do not last. Over time, they disperse. The stars drift apart, pulled by the gravity of the galaxy, by interactions with other stars, with molecular clouds. After a few 100 million years, most open clusters dissolve. The stars scatter, become indistinguishable from the background population. But here is the mystery. Some stars in the Milky Way appear to be moving together, in groups, in streams, as if they were once part of the same cluster. These are called stellar associations, or moving groups, and they are the remnants of dissolved open clusters. The stars are no longer gravitationally bound. They are not a cluster anymore, but they still remember. They still move together in the same direction, with the same velocity. And by identifying these moving groups, astronomers can trace the history of star formation, can map which stars were born together, even if their birth cluster is long gone. It is like finding siblings, separated, spread across the galaxy, but still recognizable by their shared origin, their shared motion. There is a mystery about the interstellar medium. The space between the stars is not empty. It is filled with gas and dust, atoms, molecules, ions. This is called the interstellar medium, and it is where stars form, where they die, where their material is recycled. But the interstellar medium is not uniform. It has structure, phases, regions with different temperatures, different densities. There is cold molecular gas, dense, dark, the birthplace of stars, where clouds collapse. There is warm, neutral gas, less dense, filling much of the disk, the background, the medium. There is warm, ionized gas, heated by young stars, by their ultraviolet light, glowing faintly, in hydrogen alpha emission. And there is hot ionized gas, very hot, millions of degrees, heated by supernova explosions, filling large bubbles, cavities, carved out by stellar winds. These different phases coexist, interact, transform into each other in a complex cycle. Cold clouds collapse, form stars. Stars heat the surrounding gas, create warm regions, hot regions. Stars die, explode, inject energy, create more hot gas. The hot gas expands, cools, condenses, becomes warm, then cold, and the cycle continues. But we do not understand all the details. We do not know how the phases interact, how the energy flows, how the material cycles. The interstellar medium is turbulent, chaotic, filled with shocks, flows, instabilities, and mapping it, understanding it, is one of the ongoing challenges in astronomy. Because the interstellar medium is where everything happens, where stars are born, where planets form, where life begins. It is the matrix, the substrate, the stage on which the galaxy's drama unfolds, and it is constantly changing, constantly evolving, responding to the stars within it. You can let your mind rest now. Let these ideas drift, like gas in the interstellar medium, floating, dispersing, becoming part of the background. There is no need to hold on to them, no need to remember. Just let them be. Let them pass through, like neutrinos through matter, barely touching, barely interacting, just awareness, and then release. There is a mystery about the molecular clouds. These are the densest, coldest regions of the interstellar medium, where gas has clumped together, where gravity is beginning to win, where stars will soon be born. Molecular clouds are vast. Some are hundreds of light years across, containing enough material to form hundreds of thousands of stars, or even millions. And they are dark, very dark. The dust within them blocks all visible light. When we look at them with optical telescopes, we see nothing, just darkness, just shadow. But with infrared and radio telescopes, we can see inside. We can map the gas, the dust, the molecules, and what we find is structure, filaments, cores, clumps. The cloud is not uniform. It is threaded with dense regions, connected by thinner strands. These filaments are where stars form. The densest parts of the filaments collapse, contract, heat up, and ignite. But we do not fully understand how the filaments form, why the gas organizes itself this way, what creates the structure. Perhaps it is turbulence, the chaotic motions of the gas, creating compressions, rarefactions, patterns. Perhaps it is magnetic fields, threading through the cloud, channeling the gas, creating preferred directions. Or perhaps it is gravity itself, pulling the gas into sheets, then filaments, then cores, a natural progression, an inevitable collapse. Probably all three, working together, creating the complex structures we observe. Molecular clouds are factories, star factories, and we are learning how they work, how they process raw material, how they produce stars. But each cloud is different. Each has its own history, its own properties, its own way of forming stars. And that diversity is part of the mystery, part of what makes them so fascinating, so endlessly variable. There is a mystery about the magnetic fields. The Milky Way is threaded with magnetic fields, permeating the interstellar medium, woven through the gas, the dust, the plasma. These fields are weak, much weaker than Earth's magnetic field, but they are vast, stretching across the entire galaxy, filling the disk, the halo, the space between the stars. And they play a role. They affect the motion of charged particles. They channel cosmic rays. They influence the formation of stars. But we do not know how the galactic magnetic field formed, how it is maintained, how it evolved. One idea is that the field was seeded early, perhaps by the first stars, perhaps by the first black holes, small seed fields that were amplified over time. Another idea is that the field is generated by a dynamo, like the dynamo in Earth's core, rotating plasma, convecting, creating currents, and those currents generate magnetic fields. In the galaxy, the dynamo would be driven by differential rotation. The disk rotates at different speeds at different radii, and this shearing motion could amplify and maintain the magnetic field. But the details are unclear. The equations are complex. The simulations are difficult, and observations are challenging. Magnetic fields are invisible. We can only detect them indirectly, through their effects on light, on radio waves, on the motion of particles. One method is to observe polarized light. Dust grains align with magnetic fields, and when starlight passes through aligned dust, it becomes polarized. By measuring the polarization, we can infer the direction of the magnetic field. And by mapping polarization across the sky, we can map the structure of the galactic magnetic field. It is a slow process, a painstaking process, but gradually the picture is emerging. The magnetic field follows the spiral arms. It loops through the halo. It connects structures on vast scales. The Milky Way is magnetic, threaded with invisible fields, and those fields are part of what makes the galaxy what it is. There is a type of object in the Milky Way that we cannot see directly: isolated black holes. When a massive star dies and collapses to form a black hole, it does not always have a companion. Sometimes it is alone, and a solitary black hole, with no matter falling into it, no accretion disk, no glowing gas, is invisible. It emits no light, no radiation. It is just there, in space, warping space-time, curving light, but silent, dark, undetectable. We think there are millions of these isolated black holes in the Milky Way, perhaps tens of millions, scattered through the disk, the halo, drifting through space. But we have only detected a handful, and only indirectly. One method is gravitational microlensing, when a black hole passes between us and a distant star. Its gravity bends the light from that star. The star appears to brighten for a few weeks or months, and then it fades back to normal. By measuring the duration of the brightening, the shape of the light curve, we can infer the mass of the lensing object. And if the mass is a few times the mass of the Sun, and there is no visible companion, it is probably a black hole. A few candidates have been found this way, but it is difficult, rare. The alignment must be perfect. The observations must be precise. Most isolated black holes will never be detected. They will remain invisible, hidden, part of the unseen population of the galaxy, and they remind us that much of the Milky Way is dark, invisible, unknown, that what we see is only a small fraction of what is there. There is a mystery about the local bubble. The Sun is located inside a cavity, a bubble, a region of space about 1,000 light-years across, where the gas is much less dense than average. This region is called the local bubble, and it is filled with hot, ionized gas, about 1 million degrees. But why is there a bubble here? What created it? The answer, we think, is supernovae. Multiple supernovae, exploding in this region. Over the past 10 million years or so, each supernova released enormous energy, blasted the surrounding gas outward, created a cavity, a bubble, and when multiple supernovae explode in the same region, over time, their bubbles merge, overlap, create a larger structure, The local bubble is the result, a cavity carved out by stellar deaths, by the violent ends of massive stars, and the sun happens to be inside it, by chance. We entered the bubble a few million years ago, as we orbit the galaxy, and we will leave it again in a few million years. Being inside the local bubble has consequences. The low density means there is less material to block starlight. We can see farther, more clearly, and it means there is less material to absorb cosmic rays, high-energy particles from space, so the cosmic ray flux may be slightly higher here than in denser regions. But overall, the local bubble is a quiet place, a cleared-out region, a bubble of low-density gas, surrounded by the denser interstellar medium, and it is just one of many bubbles, many cavities, scattered through the disk of the Milky Way, created by supernovae, by stellar winds, by the activity of stars. The interstellar medium is full of holes, of voids, of regions where the gas has been pushed aside, cleared away, and these structures affect the motion of gas, the formation of stars, the evolution of the galaxy. There is a mystery about the spiral arm crossing. As the sun orbits the galactic center, it does not stay in the same spiral arm. It moves through them. The spiral arms rotate more slowly than the stars, so the sun enters a spiral arm, passes through, and exits the other side, over and over. Each crossing takes about 100 million years, and during that time, the environment changes. Inside a spiral arm, the density is higher. There are more stars, more gas, more dust, more star formation. Outside a spiral arm, the density is lower, quieter, fewer stars, less activity. And some scientists have suggested that spiral arm crossings might affect life on Earth, might create cycles of extinction, or climate change, or increased radiation. Inside a spiral arm, there are more supernovae, more cosmic rays, and if the cosmic ray flux increases significantly, it could affect Earth's atmosphere, could create clouds, could change the climate. Also, inside a spiral arm, the sun might pass closer to other stars, and gravitational perturbations could disturb the Oort cloud, send comets falling inward, toward the inner solar system, toward Earth. These are speculative ideas, unproven but interesting. The idea that the motion of the sun through the galaxy, through the spiral arms, might have consequences for Earth, for life. We are currently between spiral arms in a quieter region, and that may be fortunate for now. But in a few tens of millions of years, we will enter another arm, and the environment will change again. There is a place in the Milky Way where stars have strange orbits, the nuclear star cluster. This is the densest concentration of stars in the galaxy, located at the very center, within a few light years of the supermassive black hole. In this region, millions of stars are packed together, orbiting the black hole at incredible speeds. Some stars have been tracked for decades, their orbits measured, calculated, and they follow elliptical paths, some very eccentric, coming very close to the black hole, and then swinging far out. One star, called S2, orbits the black hole every 16 years. At its closest approach, it reaches speeds of nearly 5% the speed of light, about 15,000 kilometers per second. This is fast enough to test general relativity, to measure the effects of gravity at extreme levels, to see if Einstein's equations hold. And so far, they do. S2's orbit matches the predictions. Precisely. Beautifully. But the mystery is how these stars got there, how they ended up in such tight orbits around the black hole. Stars should not form that close to a black hole. The tidal forces are too strong. The environment is too harsh. Perhaps the stars formed farther out, and then migrated inward, through interactions with other stars, through the loss of orbital energy. Or perhaps they formed in a disk around the black hole, despite the harsh conditions, in a brief phase when the black hole was accreting large amounts of gas. We do not know. The nuclear star cluster is an extreme environment, and the stars there have extreme orbits, and we are still trying to understand how they came to be. There is a mystery about the warp's origin. We mentioned earlier that the Milky Way's disk is warped, bent, twisted at the edges, but the cause of the warp is still debated, still uncertain. One possibility is that the Magellanic Clouds are responsible. As they orbit the Milky Way, their gravity pulls on the disk, distorts it, creates the warp. But simulations show that the Magellanic Clouds alone may not be enough. Their mass may be too small. Their orbit may not be right. Another possibility is that the warp is caused by the infall of gas from the intergalactic medium, gas falling onto the disk from above or below, creating asymmetric forces, torques, that twist the disk. Or perhaps the warp is an oscillation, a mode, a natural behavior of disks embedded in dark matter halos. The disk wobbles, precesses, and the warp is part of that motion. Recent observations suggest that the warp is not static. It is moving, precessing around the galaxy at about 3 kilometers per second. This is slow, but measurable. And it suggests that the warp is dynamic, not a frozen structure, but an evolving one. Understanding the warp will help us understand the structure of the Milky Way, the distribution of mass, the gravitational forces, the interactions with satellites. But for now, it remains a mystery, a gentle curve, a twist in the disk, whose origin we are still working to uncover. There is a type of star that acts as a clock. R Lyrae variables. These are pulsating stars, like Cepheids, but older, less massive, and less bright. Lyrae stars are found in globular clusters, in the halo, in the old populations. They are ancient, more than 10 billion years old, and they pulsate regularly, expanding and contracting, brightening and dimming, with periods of a few hours to about a day. The period is related to their brightness, just like Cepheids, so they can be used as distance indicators, standard candles. But R Lyrae stars are also used as clocks to measure the ages of stellar populations, because R Lyrae stars only exist in certain evolutionary stages, at certain masses, at certain ages. By studying the properties of R Lyrae stars in a cluster, their period, their brightness, their color, astronomers can estimate the age of the cluster, and by comparing ages across many clusters, across the halo, across the disk, we can reconstruct the history of the galaxy, when different parts formed, in what order. Our Lyrae stars are ancient timekeepers, ticking away, marking the passage of billions of years, and they help us understand when things happened, how long ago, in what sequence. There is a structure in the Milky Way that hints at past violence, the Gould Belt. This is a ring of young stars and star-forming regions, tilted relative to the galactic disk, about 3,000 light-years across. The Sun is inside the Gould Belt, or near its edge, and many of the nearest star-forming regions are part of it: Orion, Taurus, Perseus, Scorpius. But the Gould Belt is tilted by about 20 degrees relative to the main disk, and it is expanding, slowly, the stars and gas moving outward. This suggests that the Gould Belt was created by an event, a disturbance, something that happened about 30 million years ago, perhaps a supernova, or a cluster of supernovae, that exploded in this region and created a shock wave, an expanding shell that triggered star formation, or perhaps a high-velocity cloud, a clump of gas that collided with the disk and created the disturbance. We do not know. The Gould Belt is old enough that the original event is no longer visible. The evidence has faded, dispersed, but the structure remains. The tilted ring, the expanding shell, a fossil of something that happened long ago, and it reminds us that the disk of the Milky Way is not always peaceful, not always calm, that there are events, disturbances that leave their mark for millions of years. You can feel your breathing now, slow, steady, like the rotation of the galaxy, turning slowly, predictably, each breath, like an orbit, completing, returning, beginning again. There is no need to follow every word, every detail. Just let them wash over you like waves, like tides, gentle, rhythmic. The Milky Way continues turning, and you can rest, can let go, can drift into the quiet between the stars. There's a mystery about the oldest stars. In the halo of the Milky Way, there are stars that are almost as old as the universe itself, more than 13 billion years old, formed when the first galaxies were just beginning to coalesce. These stars are called metal-poor stars because they contain very few heavy elements, almost pure hydrogen and helium, the primordial elements from the Big Bang, and by studying them, we can learn about the early universe, about the first stars, about the conditions when everything was beginning. But there is something strange. The oldest stars we have found are not completely metal-free. They contain traces of heavy elements: carbon, oxygen, iron. This means that even the oldest stars we can see are not the very first stars. They are second generation, or third generation. The truly first stars, the ones that formed from completely pristine gas, have all died long ago. They were massive. They burned quickly. They exploded and enriched the gas around them. And the next generation formed from that enriched gas, with small amounts of heavy elements, enough to detect, but very little. These are called population 3 stars, the first generation. and we have never seen one. They existed too long ago, too far away. They are beyond our reach. But we keep searching, looking for stars with lower and lower metallicity, getting closer to that first generation, trying to understand what those earliest stars were like, how massive they were, how they formed, how they died, what they left behind. These are some of the deepest questions in astronomy. Questions about beginnings, about the first light, about the transition from darkness to stars. There is a place in the Milky Way where something is missing. The Radcliffe Wave. This is a recently discovered structure, a wave-like pattern of star-forming regions, stretching for about 9,000 light-years. Through the disk, it includes many familiar nebulae: the Orion Nebula, the Taurus Molecular Cloud, the Cygnus X region, all part of this enormous wave. The wave is oscillating, moving up and down, relative to the plane of the galactic disk, with an amplitude of a few hundred light-years, and we do not know what created it, what caused this enormous structure to form, to oscillate. Perhaps it is the result of a past collision, a high-velocity cloud, or a dwarf galaxy that crashed into the disk and created ripples, waves that persist. Or perhaps it is a natural oscillation, a mode of the disk, responding to gravitational forces, to the distribution of mass. But the mystery is not just what created it. The mystery is also what is missing. If the Radcliffe Wave is a wave, there should be a trough, a region where the disk is lower, where the density is less. And there is a gap, a region with fewer star-forming clouds, fewer molecular clouds, a void. This void is called the local cavity, and the sun is inside it, near the edge. So we live in a gap, in a cleared region, part of the structure created by the Radcliffe Wave. And this affects what we see, what we observe. The nearest star-forming regions are all part of the wave, all on one side, all in one structure. Our view of star formation in the galaxy is shaped by where we are, by the local cavity, by the Radcliffe Wave. And we are only beginning to understand this large-scale structure, this wave, and what it means for the disk of the Milky Way. There is a mystery about the star formation rate. How many stars are being born in the Milky Way right now? This seems like a simple question, but the answer is surprisingly uncertain. Current estimates suggest about 1 or 2 solar masses per year, meaning that every year the galaxy forms enough new stars to equal the mass of 1 or 2 suns. But this is an average, and the rate varies from place to place, from time to time. In some regions, like the Sagittarius B2 cloud, star formation is vigorous, active, many stars being born. In other regions, like the local cavity, star formation is low, almost absent, and over time the rate changes. There have been bursts, periods of enhanced star formation, and quiet periods, when very little was happening. The uncertainty comes from several sources. Dust blocks our view. We cannot see all the star-forming regions. Some are hidden behind clouds, and young stars are embedded in their birth clouds, surrounded by gas and dust, difficult to detect until they emerge. We can estimate the star formation rate by measuring infrared emission, by detecting radio waves from ionized gas, by counting young stars in nearby regions, and extrapolating. But each method has uncertainties, assumptions, limitations, and so the star formation rate of the Milky Way remains somewhat uncertain, known only roughly, approximately. But we are working to improve the measurements, to map the galaxy more completely, to understand where and when stars are forming, because the star formation rate tells us about the future, about how the galaxy will evolve, about how long it can sustain itself. There is a mystery about the bulge, the central region of the Milky Way. The bulge is not what we expected. For a long time, astronomers thought the bulge was spherical, like an elliptical galaxy, made of old stars, slowly rotating. But more detailed observations revealed something different. The bulge is not spherical. It is boxy, bar-shaped, and it is part of the bar, the same structure we talked about earlier. The bar and the bulge are connected, overlapping, part of the same feature. But the bulge also contains multiple populations, old stars, young stars, stars with different metallicities, different kinematics. Some stars are moving quickly, rotating with the bar. Others are moving slowly, or in random directions. And there are substructures, clumps, streams, overdensities, hidden within the bulge. One of the most intriguing is the X-shaped structure. When viewed edge-on, the bulge appears to have an X shape, 2 arms, extending above and below the plane. This X shape is probably related to the bar, to the way the bar buckles, thickens, creates vertical structure. But the details are complex. The simulations are difficult, and observations are challenging, because the bulge is so far away, and so crowded, and so obscured by dust. The bulge is one of the most difficult regions of the galaxy to study, and one of the most interesting, because it holds clues about how the Milky Way formed, how the bar formed, how the central regions evolved. There is a type of object in the Milky Way that we find in unexpected places, planets, not orbiting stars, but drifting through space, alone, unbound. These are called rogue planets, or free-floating planets, and they are thought to be common. Rogue planets form in protoplanetary disks around young stars, but they are ejected through gravitational interactions with other planets, or with the star itself. They are thrown out of their systems into interstellar space, and they drift alone, forever. Or perhaps they form differently, through the collapse of small gas clouds, too small to form stars, but large enough to form planetary mass objects. Either way, they are out there, millions of them, perhaps billions, scattered through the galaxy, and they are almost impossible to detect. They do not emit light. They do not orbit stars. They are just dark, cold, drifting. A few have been found through gravitational microlensing when they pass in front of a distant star and briefly magnify its light. But most will never be detected. They will remain invisible, unknown, part of the hidden population of the galaxy. And it is strange to think about. Planets with no sun, no warmth, no light, just drifting through the darkness for billions of years. Perhaps some of them have moons. Perhaps some of them once had life, before they were ejected, before they lost their star. We do not know. We cannot know. They are too far, too dark, too hidden. But they are there, part of the galaxy, part of the inventory, quiet wanderers, lost in the dark. There is a mystery about the metallicity of stars near the sun. When astronomers measure the heavy element content of nearby stars, they find a wide range. Some stars are metal-rich, some are metal-poor. This is expected. Stars form at different times, from gas with different compositions, and their metallicity reflects that history. But there is a puzzle. Some nearby stars have very low metallicity, much lower than expected for stars in the disk. These stars look like halo stars, like they should be part of the old population, the ancient population. But they are moving with the disk, rotating with the galaxy. Their kinematics are wrong for halo stars. So where did they come from? How did metal-poor stars end up in the disk, moving like disk stars? One idea is that they were born in the disk long ago, when the disk was young and metal poor, before many generations of stars had enriched the gas. Another idea is that they were accreted from a dwarf galaxy that merged with the Milky Way, and their stars were captured and now move with the disk. Or perhaps they were kicked, scattered by gravitational interactions from the halo into the disk, and their orbits changed. We do not know. These metal-poor disk stars are anomalies, outliers, and they challenge our understanding of how the disk formed, how it evolved. Each star has a story, a history, and by studying these unusual stars, we can learn about events that happened long ago, that left their mark in the motions and compositions of stars we see today. There is a mystery about the vertical structure of the disk. The disk of the Milky Way is thin, but not infinitely thin. It has thickness, height. Most stars are within about 1,000 light-years of the midplane, the central plane of the disk. But some stars are higher or lower, displaced from the midplane, and the distribution is not smooth, not symmetric. There are waves, ripples, oscillations. The disk is not flat. It is corrugated, rippled, like a sheet of metal that has been struck, that is still vibrating, and we do not know what caused these ripples, what disturbed the disk, what set it vibrating. Perhaps it was a collision with a dwarf galaxy millions of years ago. That passed through the disk and created waves, ripples, that still persist. Or perhaps it is ongoing perturbations from the spiral arms, from the bar, from the dark matter halo, creating constant disturbances that pile up, creating structure. The vertical waves were only discovered recently through large surveys that mapped millions of stars and measured their positions, their heights above the plane. And they reveal that the disk is more dynamic than we thought. Not a simple, flat structure, but complex, rippled, responding to forces we do not fully understand. There is a mystery about the galactic center arc. Near the center of the Milky Way, there is a strange feature, a thread-like structure, stretching for more than 150 light-years, perpendicular to the galactic plane. This structure emits radio waves, synchrotron radiation, from relativistic electrons, spiraling around magnetic field lines, and it is almost perfectly straight, vertical, extending above and below the galactic center. We do not know what it is, or how it formed, or why it is so straight. Perhaps it is a magnetic filament, a channel where the magnetic field is particularly strong, and electrons are being accelerated, funneled along the field lines. Or perhaps it is a bubble, an outflow, from activity at the galactic center. That has carved out a channel, a pathway. But the straightness is puzzling. Most structures in space are curved, warped, irregular, but the galactic center arc is remarkably linear. It is one of many strange features near the galactic center, a region full of unusual structures, unusual phenomena that we are still trying to understand. The galactic center is not a simple place. It is complex, crowded, filled with gas, stars, magnetic fields, radiation, all interacting, creating phenomena we have not seen elsewhere. There is a mystery about the rate of supernovae. How often do supernovae explode in the Milky Way, based on the number of massive stars and the rate at which they die? We estimate that a supernova should occur about once every 50 years, or once every 100 years, but we have not seen that many. In recorded history, only a handful of supernovae have been observed in the Milky Way. The most recent was in the 17th century, Kepler's supernova in 1604, and before that, Tycho's supernova in 1572. That is 2 supernovae in more than 400 years, much less than expected. Where are the missing supernovae? Why have we not seen them? One answer is dust. Many supernovae occur in regions hidden by dust. We cannot see them. They explode, fade, and we never know. Another answer is that we have been unlucky. Supernovae are random, unpredictable, and we have happened to live through a quiet period, a gap. Eventually, there will be another supernova in the Milky Way, visible from Earth, bright enough to see in daylight. A dramatic event. Astronomers are waiting, watching, hoping, because a nearby supernova would provide invaluable data about how stars explode, about what they produce, about how they enrich the galaxy. But we cannot predict when. It could happen tomorrow, or it could be centuries from now. The galaxy keeps its schedule, and we can only wait and watch and hope. There is a place in the Milky Way where the magnetic field forms loops, near the galactic center. The magnetic field is not smooth, not uniform. It is tangled, looped, structured. There are structures called the radio arcs, long filaments of radio emission, tracing the magnetic field. And there are loops, bubbles, shells, all emitting radio waves, all revealing the shape of the magnetic field. These structures are probably created by outflows from the galactic center, from the supermassive black hole, from star formation, from supernovae. The outflows push the gas and the magnetic field outward, upward, creating loops, arcs, filaments, and the electrons trapped in the magnetic field emit radiation, making the structures visible. But the details are unclear. The origin of each structure, the age, the relationship to other features. The galactic center is a laboratory, a natural experiment, where extreme conditions create phenomena we cannot replicate, cannot study, anywhere else. And by observing these structures, mapping them, measuring them, we learn about magnetic fields, about plasma physics, about how energy flows in extreme environments. You can let your thoughts drift now, like electrons, spiraling along field lines, moving, but not with purpose, just drifting, tracing paths through space. There is no destination, no goal, just motion, just flow, just being. The galaxy is vast, and you are small, and that is perfect. There is no need to understand it all, to grasp every detail. Just rest in the knowing that it is there, that it continues, that it holds you gently in its spiral arms. There is a mystery about the cold gas. In the disk of the Milky Way, there are vast reservoirs of cold molecular hydrogen, the raw material for star formation, the fuel for future generations of stars. This gas is mostly hydrogen, H2, two hydrogen atoms bonded together, and it is cold, about 10 to 20 degrees above absolute zero. At these temperatures, the gas is barely moving. Thermal motion is minimal. The molecules drift slowly, settling into clouds, into filaments. But here is the mystery. Molecular hydrogen does not emit light. It has no dipole moment, no way to radiate. At these low temperatures, it is invisible. We cannot see it directly, cannot map it directly. Instead, we use tracers, other molecules that do emit light, that can be detected. The most common tracer is carbon monoxide, CO. It emits at millimeter wavelengths, radio waves, and by mapping CO emission, we infer where the molecular hydrogen is. But this is indirect, uncertain. The ratio of CO to H2 varies, depends on conditions, on metallicity, on radiation, on density. So our maps of molecular gas in the Milky Way are incomplete, approximate, based on assumptions that may not always hold. And there may be large amounts of molecular hydrogen that we are missing, dark molecular gas, with little CO, invisible to our surveys. This uncertainty affects everything: star formation rates, gas reservoirs, the future evolution of the galaxy. We think we know, but we are working from incomplete information, from indirect tracers. The galaxy holds much of its mass, in forms we cannot see: molecular hydrogen, dark matter, cold gas, all invisible, all inferred. There is a mystery about the oldest open cluster. Most open clusters are young, a few 100 million years old, at most. They form, they shine, and they disperse within a few 100 million years. The stars drift apart. The cluster dissolves. But there is one open cluster that is different. NGC 6791. It is about 8 billion years old, ancient, for an open cluster, and it is still bound, still together. The stars have not dispersed, have not scattered. How has it survived so long? What has kept it intact? Perhaps its location. It is far from the galactic center, away from strong tidal forces, away from disruptive encounters. Perhaps its mass. It contains more stars than typical open clusters, more gravity, more binding energy, or perhaps it is just luck, a statistical outlier. Most clusters disperse, but a few, by chance, survive longer. NGC 6791 is a puzzle, an anomaly. And by studying it, we learn about cluster dynamics, about how long structures can persist, about what it takes to survive in the galaxy for billions of years. There is a place in the Milky Way where gas is falling in. The Magellanic Stream, the Magellanic Clouds, two small satellite galaxies, are orbiting the Milky Way, and as they orbit, tidal forces are pulling on them, stretching them, stripping gas away. That gas forms a stream, a long filament, trailing behind the clouds, stretching across more than 100 degrees of the sky, and the gas is falling toward the Milky Way, being accreted, captured, added to the disk. Over time, this gas will fuel star formation, will create new stars, will enrich the galaxy. But the stream is not simple, not uniform. It is fragmented, clumpy, with concentrations and gaps. And there are smaller streams, leading streams, trailing streams, branches, all torn from the Magellanic Clouds. The interaction between the Magellanic Clouds and the Milky Way is complex, dynamic, ongoing, and eventually, in a few billion years, the Magellanic Clouds will merge with the Milky Way. They will be consumed, their stars added to the halo, their gas added to the disk. This is galaxy evolution in slow motion, visible, happening right now in our cosmic backyard. There is a mystery about the lack of very massive stars. In the Milky Way, the most massive stars have masses around 100 to 200 times the mass of the Sun. But theory suggests that stars could form with even higher masses, up to several hundred solar masses. So where are they? Why do we not see stars more massive than about 200 solar masses? Perhaps they form, but they are unstable. They blow themselves apart before they can settle, before they can burn steadily. Or perhaps there is a physical limit, a maximum mass, beyond which stars cannot form, cannot accrete more material. The most massive stars have intense radiation, powerful stellar winds that push away the surrounding gas, that halt accretion. Perhaps that limit is around 200 solar masses. Perhaps that is the natural ceiling, the maximum that physics allows. Or perhaps very massive stars do form, but they are rare, so rare that we have not found them yet, hidden in distant regions, obscured by dust. The most massive stars are also the shortest lived. They burn through their fuel in just a few million years, and then they explode or collapse and disappear. So even if they form, they do not last long. They are transient, fleeting. The mystery of the upper mass limit is one of the open questions in stellar astrophysics. We know stars exist up to about 200 solar masses, but we do not know if that is a hard limit, or just what we have observed so far. There is a structure in the Milky Way made entirely of old stars, the Hercules-Aquila cloud. It is not really a cloud, it is an overdensity, a concentration of stars in the inner halo, about 20,000 light-years from the galactic center, and it is enormous, stretching for tens of thousands of light-years, containing billions of stars. But these stars are old, ancient, metal-poor, part of the early galaxy, part of the first structures to form. The Hercules Aquila cloud may be a remnant of an ancient merger, a dwarf galaxy that was consumed by the Milky Way long ago, and its stars now form this vast structure. Or it may be part of the original halo, a concentration that formed when the Milky Way was young, when the halo was still collapsing, still settling. We do not know. The structure is difficult to study. It is diffuse, spread over a large area, and individual stars are faint, distant. But it is there, a fossil, a relic, evidence of the early history of the galaxy, of how the Milky Way came to be. There is a mystery about the gap in the disk. Between the spiral arms, there are regions of lower density. This is expected. The spiral arms are where stars and gas concentrate. But there is one gap that is larger than expected, deeper, more pronounced. It is called the local arm gap, or sometimes the Great Rift, and it is near us. The Sun is close to this gap, close to the edge. The gap is not completely empty. There are stars, there is gas, but the density is lower, much lower than in the spiral arms. Why is this gap here? What created it? What maintains it? Perhaps it is a natural feature, the space between spiral arms, regions where density waves have not compressed the gas. Or perhaps it is the result of past events, supernovae, stellar winds, that cleared out the gas, created a cavity, the local cavity, that we talked about earlier, may be part of this gap, part of this larger structure of low density. We live in a cleared region, a bubble, a gap, and that affects our view, our observations, the stars and nebulae we see nearby. There is a type of star that should not be in the Milky Way, high-velocity stars, not hypervelocity stars, but stars moving faster than normal, faster than the rotation of the disk. These stars have velocities that do not match the local standard of rest. They are moving through the disk, at odd angles, at high speeds. Some are moving toward the galactic center, some away, some perpendicular to the disk. And we do not know where they came from, why they are moving so fast, why their orbits are so strange. Perhaps they were born in a different part of the galaxy and migrated here through interactions, through orbital changes. Or perhaps they are intruders from the halo, passing through the disk on elongated orbits. Or perhaps they were accelerated by something, a supernova, a black hole, a close encounter with another star. Each high-velocity star is a mystery, a puzzle, and by studying them, we learn about dynamics, about orbits, about the forces that shape stellar motion. There is a mystery about the distribution of elements. When astronomers measure the abundances of elements in stars, they find patterns, trends, that tell us about nucleosynthesis, about where elements are made. Heavy elements, like iron, are made in supernovae, in the cores of exploding stars, and scattered through space. Other elements, like oxygen, are made in massive stars, during their lifetimes and ejected in stellar winds and supernovae. Still others, like carbon, are made in dying low-mass stars, in planetary nebulae, released gently into the interstellar medium. But the patterns are not always what we expect. Some stars have unusual abundances, too much of one element, too little of another. These are called chemically peculiar stars, and they challenge our understanding of how elements are made, how they are distributed, how they are incorporated into new stars. Some of these stars may have formed from gas that was enriched by a single supernova, a single event. That dominated the local composition. Others may have accreted material from a companion star. That changed their surface composition. Or they may reveal processes, physics, that we do not yet understand, new ways that elements are made, or moved, or transformed. Each chemically peculiar star is a clue, a piece of evidence about the complex history of matter in the galaxy. There's a place in the Milky Way where radiation is intense, the galactic center, again, not just because of the supermassive black hole, but because of everything around it. There are millions of stars, packed closely, many of them massive, hot, emitting intense ultraviolet radiation. There are supernovae, frequent, releasing high-energy gamma rays, X-rays. There are cosmic rays, particles accelerated to nearly the speed of light, by shocks, by magnetic fields, by unknown processes. And all of this creates a harsh environment, a bath of radiation that permeates the region. If there are planets near the galactic center, they are bombarded constantly with radiation, with particles. Any atmosphere would be stripped away. Any life would struggle to survive, unless deep underground, shielded, protected. The galactic center is not a hospitable place, not for life, as we know it. But it is fascinating from a physics perspective, from an astrophysics perspective, because extreme conditions produce extreme phenomena, things we cannot study anywhere else in the galaxy. There's a mystery about the metallicity floor. When astronomers search for the most metal-poor stars, the oldest stars, stars with almost no heavy elements, they find a limit. No star has been found with absolutely zero heavy elements, completely pristine, completely untouched by previous stellar generations. The lowest metallicity observed is about 1/10,000th of the Sun's metallicity. Very low, but not zero. This suggests that even the oldest stars we can observe were formed from gas that had been slightly enriched by even earlier stars, by the truly first stars, population 3 stars, that we have never seen. Those first stars died, exploded, and enriched the gas just a little, and the next generation formed with that slight enrichment. And we see that next generation, but not the first. The metallicity floor tells us that we are always seeing second generation or later, that the very first stars are beyond our reach, forever hidden in the distant past. But we keep searching for stars with lower and lower metallicity, getting closer to that floor, trying to learn as much as we can about the earliest times. There is a structure in the Milky Way that might not be real, the Vela supercluster, or rather, the question is whether it is truly a structure or just a chance alignment. Near the constellation Vela, there is a concentration of old stars, an overdensity, a clump. Some astronomers think this is a real structure, a substructure in the halo, perhaps the remnant of an ancient dwarf galaxy. Others think it is just statistics, a random fluctuation, stars that happen to be near each other, in projection, but not truly associated. This is a common problem in astronomy. When we observe the sky, we see two dimensions, positions, angles. But the universe is three-dimensional, and some things that look close together in the sky are actually far apart in space, and some things that look like structures, like clusters, like associations, are just chance alignments, determining what is real and what is projection. Requires measuring distances, measuring velocities, building a three-dimensional picture. For faint, distant stars, this is difficult, uncertain, and so structures like the Vela supercluster remain ambiguous, possibly real, possibly not. The Milky Way is full of apparent structures, some real, some illusion, and disentangling them is part of the work of understanding the galaxy. You can feel the rhythm now, the slow, gentle rhythm of the galaxy, turning, orbiting, flowing, stars moving through space, through time, following paths set long ago by gravity, by history, by chance. And you are part of that, part of the flow, part of the motion, even as you rest, even as you lie still. The galaxy carries you, moves you, without effort, without thought, just the natural motion of everything together. And you can surrender to that, can let go, can drift with the current, with the tide, with the slow rotation of the Milky Way. There is a mystery about the tidal streams. We have mentioned them before, but their complexity, their variety, is remarkable. Some streams are narrow, pencil-thin, stretching for thousands of light-years, but only a few dozen light-years wide. Others are broad, diffuse, spread across large regions of the sky. Some streams are smooth, continuous, a steady flow of stars, following predictable orbits. Others are clumpy, fragmented, with gaps, with concentrations, as if something has disturbed them, perturbed them, and we do not always understand why each stream has the properties it does, why some are narrow, why some are clumpy. Part of the answer is the parent object, the globular cluster, or dwarf galaxy, that was torn apart. A compact object will produce a narrow stream. A diffuse object will produce a broad stream. But perturbations matter too. Encounters with dark matter clumps, with giant molecular clouds, with other structures, can create gaps, can create irregularities. By studying the detailed structure of streams, the clumps, the gaps, the wiggles, astronomers can learn about what has perturbed them, what has interacted with them, and this reveals the invisible structure of the galaxy, the dark matter subhalos, the distribution of mass, the gravitational landscape. Streams are like tracers, revealing the hidden architecture of the Milky Way. There is a place in the Milky Way where young stars are found in unexpected locations, above the disk, in the halo, where everything should be old, ancient, settled. But there are pockets, regions, with young stars recently formed out of place. These are called high-velocity clouds that have formed stars, gas clouds, falling toward the disk, compressing, heating, and in some cases, collapsing, forming stars before they reach the disk, or perhaps gas ejected from the disk by supernovae that cools, condenses, and forms stars in the halo. Either way, these young stars are anomalies. They should not be there, should not have formed where they are, but they exist. And they tell us that star formation is not confined to the disk, that under the right conditions, stars can form almost anywhere, even in the halo, even far from the main reservoir of gas. There is a mystery about the oldest white dwarfs. White dwarfs are the remnants of sun-like stars after they die, after they shed their outer layers. What remains is the core, hot, dense, slowly cooling, and by measuring the temperature of a white dwarf, we can estimate its age. The cooler it is, the older it is. The coolest white dwarfs in the Milky Way are about 12 to 13 billion years old, almost as old as the galaxy itself. But here is the mystery. There should be even older white dwarfs, stars that died even earlier, in the first billion years of the galaxy's history. Where are they? Why have we not found them? Perhaps they are there, but too faint to detect. After more than 13 billion years, a white dwarf becomes extremely dim, almost invisible. Or perhaps the earliest stars were all massive, and they did not become white dwarfs. They exploded as supernovae, or collapsed into neutron stars or black holes. Only later, when lower mass stars formed, did white dwarfs begin to appear. This would explain the age distribution, the lack of extremely old white dwarfs. But we do not know for certain the population of the oldest white dwarfs remains uncertain. There is a type of cluster that is intermediate between open clusters and globular clusters. They are too old, too massive to be open clusters, but too young, too metal-rich to be globular clusters. These are sometimes called intermediate age clusters or young halo clusters, and they do not fit neatly into our categories, our classifications. Perhaps they formed during a transition period when the galaxy was changing from one phase to another, or perhaps they formed in special environments under unusual conditions that created something different, Each cluster is unique, has its own history, its own properties, and the existence of intermediate clusters reminds us that nature does not always fit into our boxes, our categories, that there is continuity, gradation, overlap between different types of objects. There is a mystery about the missing baryons. Baryons are ordinary matter, protons, neutrons, atoms, the stuff we are made of, the stuff we can see. But when astronomers add up all the baryons in the Milky Way, all the stars, all the gas, all the dust, they find that it is not enough. Based on cosmology, based on the Big Bang, we know how many baryons should exist in the universe, what fraction of the total mass. But when we look at the Milky Way, we cannot account for all of them. About half are missing. Where are they? Where did they go? One possibility is that they are in the halo, in a hot, diffuse, ionized phase, too hot to emit much light, too diffuse to detect easily. This is called the circumgalactic medium, the gas surrounding the galaxy, extending far beyond the disk. It may contain as much mass as the disk itself, but spread over a much larger volume. Another possibility is that the baryons are in structures we have not yet mapped, dense clouds hidden by dust, or in regions we have not surveyed, or perhaps some baryons were ejected, blown out by supernovae, by galactic winds, and now reside in the intergalactic medium beyond the galaxy, lost. The missing baryons are one of the puzzles of galactic astronomy. We know they should be somewhere, but we cannot find them all. There is a place in the Milky Way where the magnetic field reverses. Magnetic fields have direction. They point from north to south, from one pole to another, and in most of the galactic disk, the field points in one direction along the spiral arms, following the rotation. But there are regions where the field flips, reverses, points the opposite way. These are called magnetic reversals or field reversals, and we do not fully understand how they form, what causes them, what maintains them. Perhaps they are relics of past events, disturbances that twisted the field, created irregularities, or perhaps they are part of the dynamo, the process that generates the magnetic field. Reversals may occur naturally as part of the cycle on Earth. The magnetic field has reversed many times throughout history. North becomes south, south becomes north. Perhaps something similar happens in the galaxy, but on much larger scales, much longer time scales. Magnetic reversals are another reminder that the galaxy is not static, not simple, but dynamic, complex, full of structures and processes. We are only beginning to understand. There is a mystery about stellar ages. Measuring the age of a star is difficult, uncertain. We can measure brightness, temperature, color, composition. But age is more challenging. One method is to use stellar models, simulations that predict how stars evolve over time. By comparing observations to models, we can estimate how long the star has been burning. But this depends on the models being correct, and there are uncertainties in the physics, in the nuclear reactions, in the mixing of material. Another method is to look at stellar clusters where all stars formed at the same time. By studying the cluster as a whole, we can estimate its age, and then individual stars in the cluster have the same age, but isolated stars, stars not in clusters, are more difficult, and sometimes we find contradictions. A star that looks young but has old composition, or a star that looks old but is in a young region. These anomalies reveal that stellar evolution is more complex than our models suggest, that stars can rejuvenate, can merge, can change in unexpected ways. Age dating remains one of the challenges in stellar astrophysics. There is a structure in the Milky Way that is invisible in most wavelengths, the North Polar Spur. It is an enormous arc of radio emission stretching across the sky from the galactic plane toward the North Pole, and it is very large, spanning more than 100 degrees, more than half the sky. For decades, astronomers thought it was distant, thousands of light years away, part of a supernova remnant in the disk. But recent measurements suggest it may be much closer, only a few hundred light years away. If this is true, then the North Polar Spur is part of the local bubble, the cavity we live in. It may be the edge of the bubble, the shell where the expanding gas from past supernovae is interacting with the surrounding medium. But the nature of the spur is still debated, still uncertain. Different studies give different distances, different interpretations. It is one more mystery. In our immediate neighborhood, a structure so close that it spans half the sky, and yet we do not fully understand what it is. There is a mystery about runaway stars. Some massive stars are moving very fast through the galaxy, not as fast as hypervelocity stars, but faster than normal. These are called runaway stars or walkaway stars, depending on their speed, and we think they were ejected from binary systems. If a massive star has a companion and the companion explodes as a supernova, the explosion can kick the surviving star, accelerate it send it speeding away, or if two stars are in a crowded cluster, gravitational interactions can eject one of them, launch it out of the cluster. Either way, the star ends up moving fast through space away from its birthplace. Runaway stars are interesting because they carry the imprint of their origin, of the event that accelerated them. By studying their velocities, their trajectories, we can trace them back to their birth clusters, to the regions they came from, and sometimes we find that a runaway star and a supernova remnant are connected, that they both came from the same binary system. This helps us understand stellar evolution, binary interactions, how stars live and die together. There is a place in the Milky Way where something is orbiting that we cannot explain. Around the supermassive black hole, at the galactic center, there are objects called G objects. They look like gas clouds, extended, diffuse, when they are far from the black hole. But when they pass close to the black hole, they do not behave like gas clouds. They do not get stretched, do not get torn apart by tidal forces. Instead, they remain compact, intact, as if they were solid objects, but they look like gas, not like stars, not like solid bodies. What are they? What could be? Compact enough to resist tidal forces, but diffuse enough to appear like gas. One idea is that they are stars surrounded by thick envelopes of gas and dust. The envelope makes them look diffuse, but the star at the core provides the mass, the compactness. Another idea is that they are binary stars in the process of merging, surrounded by material ejected during the merger. Or perhaps they are planets stripped from their stars by the black hole and surrounded by atmospheres that have puffed up in the heat. We do not know. G objects are strange, unusual, and we are still trying to understand what they are. There is a mystery about the scale height of the disk. The scale height is the thickness of the disk, the distance above and below, the plane where most stars are found. And the scale height varies for different populations of stars. Young stars have a small scale height. They are concentrated near the plane. Old stars have a larger scale height. They are more spread out, more vertically extended. This makes sense. Young stars are still near their birthplaces in the disk. They have not had time to be disturbed, scattered. Old stars have been around longer. They have been perturbed by encounters with giant molecular clouds, by spiral arms, by the bar. and over time, these perturbations heat the disk, puff it up, increase the scale height. But the rate of heating is uncertain, the mechanisms are complex, and the observations do not always match the models. Some populations have scale heights that are too large or too small for their age, and this tells us that disk heating is not a simple process, that there are additional factors, additional mechanisms we have not fully accounted for. You can feel your body now settling, sinking into the surface beneath you, supported, held. There is no need to hold yourself up, no need to maintain tension or alertness. Just let go. Let your muscles soften. Let your breathing slow. Let your thoughts drift like stars through the halo, moving without direction, without purpose. The Milky Way holds billions of mysteries, and you do not need to solve them, do not need to remember them. Just let them pass through your awareness like light through space, gently, quietly, without resistance. There is a mystery about the gamma-ray glow. When astronomers observe the Milky Way with gamma-ray telescopes, they see a diffuse glow coming from the galactic center, from the bulge, from the disk. Part of this glow is expected. Cosmic rays colliding with gas, producing gamma rays through known processes. But there is excess emission, more gamma rays than expected, more than can be explained by ordinary processes. This excess is called the galactic center, GeV excess, and it has puzzled scientists for years. What is creating these extra gamma rays? What is producing this unexpected glow? One possibility is dark matter. If dark matter particles can annihilate when they meet, they could produce gamma rays, and the signal would be strongest where dark matter is most dense, at the galactic center. This would be revolutionary, direct evidence of dark matter revealing itself through radiation. But there are other explanations, more mundane. Perhaps there are more pulsars than we have detected, each emitting gamma rays, and together they create the excess. Or perhaps there are more cosmic ray sources, more supernovae, more acceleration sites, creating more gamma rays than we accounted for. The debate continues, the observations continue, and the mystery remains unresolved. It may be dark matter, or it may be something we have not considered, something unexpected, something new. There's a place in the Milky Way where stars have strange chemistry, the Omega Centauri globular cluster. It is the largest, brightest globular cluster, visible from the southern hemisphere, containing about 10 million stars. But Omega Centauri is unusual. Unlike other globular clusters, its stars do not all have the same composition. There are multiple populations with different metallicities, different abundances, as if they formed at different times from different gas. This suggests that Omega Centauri is not just a globular cluster. It may be the core of a dwarf galaxy that was consumed by the Milky Way. The outer parts were stripped away, scattered into streams, but the core remained intact. And what we see now as Omega Centauri is the remnant, the survivor. If this is true, then Omega Centauri holds secrets about galactic collisions, about how galaxies merge, about what happens to the cores of smaller galaxies when they are captured. It is a time capsule, a relic of a galaxy that no longer exists except as this massive cluster orbiting the Milky Way. There's a mystery about the asymmetry. The Milky Way is not perfectly symmetric, not perfectly balanced. When we map the distribution of stars, the distribution of gas, we find asymmetries, lopsidedness, one side slightly different from the other. The northern half of the disk is not identical to the southern half. There are differences in density, in star formation, in structure, and the disk is not centered. On the galactic center, it is offset, slightly shifted. These asymmetries are subtle but real, and they tell us that the galaxy is not in equilibrium, not perfectly settled. Perhaps it is still responding to past events, to collisions, to mergers that happened millions or billions of years ago. Or perhaps it is being perturbed right now by the Magellanic Clouds, by other satellites, by the flow of gas. Galaxies are not static structures. They are dynamic, constantly adjusting, constantly responding to forces, both internal and external. The asymmetries in the Milky Way are evidence of that ongoing evolution. There is a type of star that contains technetium. Technetium is an element that does not exist naturally on Earth. It is radioactive. It decays too quickly to have survived since the formation of the solar system. But in some stars, technetium has been detected in their atmospheres, in their spectra. How is this possible? How can a star contain an element that decays so quickly? The answer is, the star is making it right now. These stars are called S-process stars, or technetium stars. They are red giants, undergoing nuclear reactions in their interiors through a process called the S process, the slow neutron capture process. They are creating heavy elements, including technetium, and convection brings these elements to the surface where we can detect them. The presence of technetium tells us that nucleosynthesis is happening right now inside the star, that elements are being forged as we observe. It is direct evidence of stellar alchemy, of the processes that create the elements in the universe. There is a mystery about the thick disk stars near the Sun. We mentioned the thick disk earlier, a population of old stars, above and below the thin disk. But near the Sun, we find thick disk stars that are moving in unusual ways. Their orbits are strange, eccentric, tilted, and their ages do not always match their chemistry. Some have old compositions, but appear relatively young. Others have young compositions, but appear old. These discrepancies suggest that the thick disk is not a single population, not a simple structure. It may be a mixture of stars from different origins, some formed in place, others accreted from satellites. Each star has its own history, its own journey, and by studying these individual histories, we can piece together the larger story of how the Milky Way assembled itself. There's a place in the Milky Way where nothing seems to form, a star formation desert. In some regions of the disk, the conditions seem right for star formation. There is gas, there is dust, there is density, but no stars are forming. The region remains quiescent, inactive. We do not know why, what is preventing the gas from collapsing, what is supporting it against gravity, perhaps turbulence. The random motions of the gas provide pressure that counteracts gravity, or perhaps magnetic fields thread through the gas and provide support, preventing collapse. Or perhaps the gas is simply not dense enough, not quite at the threshold for collapse. These star formation deserts remind us that star formation is not automatic, not inevitable, that there are barriers, thresholds, conditions that must be met, and that even when conditions seem right, other factors may intervene, may delay or prevent the formation of stars. There is a mystery about the warps in stellar streams. Some tidal streams show kinks, bends, changes in direction that do not match simple models of tidal disruption. These warps may be caused by encounters with dark matter clumps, massive concentrations of dark matter that pulled on the stream as it passed by. If this is true, then by studying the warps, measuring their size, their location, we can map the dark matter substructure in the halo. This is one of the most promising methods for detecting dark matter clumps indirectly through their gravitational effects on visible matter. But the interpretation is complex. Other things can create warps, giant molecular clouds, satellite galaxies, the bar, the spiral arms. Distinguishing between these different causes requires careful analysis, detailed models, precise measurements, but the potential is enormous. Streams may be our best window into the detailed structure of dark matter. In the Milky Way, there is a mystery about how the galaxy will end. What is the ultimate fate of the Milky Way? We know that in about 4 billion years, the Milky Way will collide. With Andromeda, the two galaxies will merge. The result will be a large elliptical galaxy, Milkomeda or Milkdromeda. But what then? What happens after the merger? The combined galaxy will contain hundreds of billions of stars, it will be one of the largest galaxies in the local group, and it will continue to evolve. Stars will form from the remaining gas for a time, but eventually the gas will be exhausted or heated or expelled, and star formation will cease. The galaxy will age, the stars will burn out, one by one. The brightest will die first, then the middle-sized eventually. Only red dwarfs will remain, and the galaxy will fade, redden, darken. Over trillions of years, most stars will be ejected through gravitational interactions, flung out into intergalactic space. What remains will spiral inward toward the center, toward the merged, supermassive black holes, and eventually the galaxy will be gone, dispersed, dissolved. Only black holes and dead stars scattered through the void. This is the long-term fate of all galaxies in a universe dominated by dark energy, expansion, isolation, aging, dispersal, a quiet end, a slow fade, not a collapse, not an explosion, just silence. But that is trillions of years away, far beyond any timescale we can truly comprehend. For now, the Milky Way is alive, active, evolving, and we are here to witness it, to study it, to be part of it. There is a wonder in simply existing within the Milky Way, in being one small part of this vast spiral structure, this collection of hundreds of billions of stars, each star a sun, perhaps with planets, perhaps with moons, perhaps with life, all of it bound together by gravity, moving together through space, orbiting the common center. We are galaxy citizens, residents of the Milky Way, participants in its story. And that story is still being written, still unfolding. The Milky Way is not finished, not complete. It is merging with smaller galaxies, growing, changing, evolving. It is forming new stars, creating new planetary systems, new possibilities. It is a living structure, dynamic, complex, beautiful, and every mystery we have explored tonight, every puzzle, every question, is part of that beauty. The unknown is not a problem. It is a gift, an invitation to wonder, to explore, to discover. The Milky Way does not reveal all its secrets at once. It shares them slowly, gently, over time. And we are patient. We watch, we measure, we learn, and gradually the picture becomes clearer, the story becomes richer, the mysteries transform into knowledge. But new mysteries always emerge. Each answer leads to new questions. The exploration never ends. And that is as it should be, because the universe is infinite in its complexity, in its depth, in its capacity to surprise us, You can rest now in the knowing that you are part of this, part of the Milky Way, part of the cosmic story. Your body is made of elements, forged in stars, scattered by supernovae, gathered by gravity, assembled into life. You are stardust, given form, given consciousness, given the ability to wonder about the galaxy that made you. And tonight, as you rest, as you drift toward sleep, the galaxy continues turning, the stars continue shining, the gas continues flowing, the mysteries continue waiting, all of it happening slowly, quietly, patiently. And you can let go now, can release the need to know, to understand, to stay awake. The Milky Way will be here tomorrow and for billions of years to come, and you are part of it, always connected, woven into the fabric of the galaxy. Rest now in that connection, in that belonging, in that peace. Let your breathing slow, let your thoughts fade, let sleep come gently, naturally, inevitably. The mysteries will wait, the wonders will remain, the Milky Way will continue its slow, eternal dance, and you can sleep now, deeply, peacefully, held by the galaxy that is your home. Sleep, rest, be here in the spiral arms of the Milky Way, in the quiet darkness between the stars, in the ancient, patient peace of the galaxy. Sleep now, sleep. There is a sound in space that no one can explain. In 1977, a radio telescope in Ohio detected something unusual. A signal, strong, clear, lasting for 72 seconds. It came from the direction of the constellation Sagittarius, and it was unlike anything researchers had heard before or since. The astronomer on duty, seeing the printout, circled the sequence and wrote one word in the margin: "Wow." The wow signal, as it came to be known, has never been explained. It matched no known natural phenomenon. It appeared once and never repeated. Decades of listening to that same region of space have yielded only silence. Was it a message? A natural event we don't understand? A glitch in the equipment? We don't know. This is not unusual. Space is full of signals we cannot explain. Bursts of radio waves lasting only milliseconds. Patterns that seem too regular to be random. emissions from regions of space where nothing visible exists. Each one is documented, studied, analyzed, and then filed away in the growing catalog of things we've detected but cannot interpret. The universe is speaking. We can hear it, but we cannot yet understand the language. And perhaps that's fitting, because space has always been a place of mystery. Even before telescopes, humans looked up and wondered what the lights were, where they came from, whether we were alone. We have answered some of those questions. We know now that stars are distant suns, that planets orbit them, that galaxies stretch away in every direction, islands of light in an ocean of darkness. But the deeper we look, the more mysteries we find. The more we discover that what we thought we knew was only the beginning of a much larger, much stranger story. There are objects in space called fast radio bursts. They flash across the cosmos in the blink of an eye, releasing as much energy as the sun produces in an entire day. And they do this in just a few milliseconds. We've detected hundreds of them. They come from distant galaxies. Some repeat, some don't. And we have no consensus on what causes them. Perhaps they are the dying breaths of massive stars. Perhaps they are signals from magnetars, neutron stars with magnetic fields so strong they warp the very fabric of space. Perhaps they are something else entirely, something we haven't imagined yet. The data arrives, the telescopes record, the computers process, and scientists around the world look at the results and say quietly, "We don't know. This is not failure. This is the frontier. This is where science lives, in the space between the known and the unknown, building bridges of understanding one careful observation at a time. And some bridges take longer to build than others. There is a structure in space called the Great Wall. It is a vast filament of galaxies, stretching across more than 500 million light-years of space. For context, our entire observable universe is only about 93 billion light-years across. The Great Wall shouldn't exist. According to our understanding of cosmic evolution, there hasn't been enough time since the Big Bang for gravity to pull matter into structures this large. And yet, there it is, visible in our surveys, undeniable, a wall of galaxies defying our models of how the universe grows and changes. It is not alone. We've found other structures. The Sloan Great Wall, the Hercules Corona Borealis Great Wall, even larger, stretching across 10 billion light-years. These are not small anomalies. They are fundamental challenges to our understanding of cosmic structure formation. How did they form? Why are they so large? What does their existence tell us about the early universe? These questions remain open. The structures exist. The measurements are clear. But the explanation, the mechanism, the deeper understanding is still being sought. Space does not give up its secrets easily. It requires patience, careful observation, the willingness to sit with uncertainty for years, sometimes decades, while data accumulates and theories are tested and refined. And sometimes, even after all that, the answer remains just out of reach. A whisper in the data, a suggestion of something deeper that we're not quite ready to see. You can let your mind rest with that thought. There is no urgency here, no need to solve anything. We're simply observing, simply acknowledging what is unknown. The mysteries of space are not problems that demand immediate solutions. They are invitations, gentle reminders that reality is larger, stranger, and more wonderful than any single explanation can capture. And tonight, as you settle into rest, you can carry that with you. The knowledge that somewhere out there, in the vast darkness between galaxies, mysteries are waiting, patient, timeless, content to remain unsolved until the universe itself decides to reveal them. Take a slow breath. Let it out gently. Let the day fade. We're going to continue now, moving deeper into space, exploring more of these quiet unknowns. And as we do, you're welcome to drift, to let the words become a gentle background, to allow sleep to arrive whenever it's ready. Because these mysteries have waited billions of years, they can wait through your rest too. There is something at the center of our galaxy that we cannot see directly, but we know it's there because of what it does to everything around it. Sagittarius A star, a supermassive black hole, 4 million times the mass of our Sun, compressed into a space smaller than Mercury's orbit, and it sits there at the heart of the Milky Way, pulling on stars, warping space-time, drawing matter toward itself in a slow, inevitable spiral. We can track the stars that orbit it. Some have been observed for decades, following elliptical paths that bring them so close to the black hole they reach speeds of nearly 5% the speed of light. These stars tell us the black hole is there. Their motions prove its existence, as clearly as ripples prove the stone that disturbed still water. But the black hole itself remains invisible, not because our telescopes are inadequate, but because that is what black holes are. Regions where gravity is so intense that not even light can escape, where space-time curves so severely that it closes in on itself. What happens inside a black hole? What exists at the center, in that point of infinite density we call a singularity? We don't know. Our mathematics breaks down there. The equations that describe gravity and space-time, usually so reliable, return infinities, meaningless numbers, signs that we're missing something fundamental. Perhaps the singularity is not truly infinite. Perhaps at the smallest scales, quantum effects step in to prevent the collapse from continuing forever. Perhaps something entirely new happens, something we have no framework yet to understand. Or perhaps the singularity is exactly what our mathematics suggests, a place where the normal rules of physics cease to apply, where time and space lose their meaning, where reality itself becomes something alien. We cannot see inside to know. The event horizon, that boundary around the black hole where escape becomes impossible, shields the interior absolutely. No signal can cross from inside to outside. No information can leak out. What we can study is the boundary itself. The region just outside the event horizon, where matter piles up, heats up, releases energy in great spiraling torrents before finally crossing the point of no return. And even here, mysteries abound. Black holes are not simply vacuum cleaners, mindlessly consuming everything nearby. They shape their surroundings. They launch jets of particles at near light speed, perpendicular to their accretion disks. These jets can extend for thousands of light years, far beyond the galaxy itself. How do black holes create these jets? The details remain unclear. Magnetic fields are involved. The spinning of the black hole plays a role. But the exact mechanism, the precise physics that accelerates particles to such incredible energies, is still being worked out. Some black holes are quiet. They sit dormant, barely feeding, like Sagittarius A star at the center of our galaxy. Others are ravenous, consuming the equivalent of several Earths per second, blazing so brightly they outshine entire galaxies. What determines whether a black hole is active or quiet? Why do some feed aggressively while others hardly eat at all? These questions connect to the larger mystery of how galaxies evolve, how black holes grow, how the two shape each other over billions of years. And then there is the question that puzzles physicists most deeply. What happens to information that falls into a black hole? In physics, information is not supposed to be destroyed. It can be transformed, scattered, hidden in complex ways, but never truly erased. This principle, the conservation of information, is fundamental to quantum mechanics. But black holes seem to violate it. When matter falls past the event horizon, all information about it, its composition, its history, its quantum state, appears to be lost forever, gone, erased from the universe. This creates a paradox, the black hole information paradox, and it has troubled physicists for decades. Stephen Hawking proposed that black holes might not be entirely black. Through quantum effects at the event horizon, they should slowly evaporate, releasing faint radiation. Over unimaginably long timescales, a black hole could shrink and eventually vanish completely. But if the black hole evaporates, and if the radiation it releases carries no information about what fell in, then information has been destroyed. The universe has forgotten. Various solutions have been proposed. Perhaps the information is encoded subtly in the Hawking radiation, scrambled beyond recognition but technically present. Perhaps it's stored on the event horizon itself, written into the surface in ways we don't yet understand. Perhaps black holes are connected to other regions of space-time, wormholes through which information could escape. None of these ideas are proven. The paradox remains open, a puzzle sitting at the intersection of quantum mechanics and gravity, two of our most successful theories refusing to fit together cleanly. And beyond the information paradox lies an even deeper question. Are black holes doorways? Some solutions to Einstein's equations suggest that black holes might connect to other regions of space, or to other times, or even to other universes entirely. These solutions describe wormholes, tunnels through space-time, with a black hole at one end and a white hole, a hypothetical region where matter and light emerge at the other. But these are mathematical possibilities, not confirmed realities. Wormholes, if they exist at all, would likely be unstable. They would collapse before anything could pass through. And even if they could be stabilized, the tidal forces near the event horizon would tear apart any object that tried to enter. Still, the mathematics allows them. And in science, what the mathematics allows, nature sometimes provides. So the question remains open, waiting for observations that might someday reveal whether black holes are indeed bridges to elsewhere. For now, black holes remain among the most mysterious objects in the universe. We know they exist. We can see their effects. We can measure their masses and spins. But their interiors, their ultimate fate, and their deepest nature remain hidden behind horizons we cannot cross. You can rest with that image. Black holes, silent, patient, holding secrets in the dark. There is no need to understand them fully tonight. No need to solve the paradoxes they present. They are simply there. Part of the vast tapestry of space. Part of the mystery. Let your breathing continue its slow rhythm. Let your thoughts soften. We're going to move now to another mystery, another corner of space where our understanding reaches its limit and then stops, gazing into uncertainty. There is something pushing the universe apart, and we have no idea what it is. In the 1990s, astronomers were studying distant supernovae, explosions of stars so bright they can be seen across billions of light years. These supernovae are remarkably consistent. They always reach roughly the same peak brightness. This makes them useful as cosmic distance markers. If you know how bright a supernova truly is, and you measure how bright it appears from Earth, you can calculate how far away it is. The astronomers were trying to measure the expansion of the universe. They expected to find that the expansion was slowing down. Gravity, after all, should be pulling galaxies back together, gradually breaking the outward motion that began with the Big Bang. But that's not what they found. Instead, they discovered that the expansion is speeding up. Galaxies are accelerating away from each other. The universe is not just expanding, it is expanding faster and faster over time. This was so unexpected, so contrary to predictions, that the teams checked their work repeatedly. They analyzed the data in every possible way. They looked for errors, for biases, for anything that might explain the result without requiring something new and unknown. But the result held. The universe is accelerating, and something must be pushing it. We call that something dark energy. Not because it's dark in the sense of being shadowy or evil, but because we can't see it. It doesn't emit light. It doesn't absorb light. It doesn't interact with matter in any way we can detect directly. All we can observe is its effect, a gentle, constant pressure filling all of space, pushing galaxies apart. Dark energy makes up about 68% of the universe. More than 2/3 of everything that exists is this mysterious energy we cannot see, cannot touch, cannot directly measure. What is it? We don't know. One possibility is that dark energy is a property of space itself. That empty space has a tiny, inherent energy, and as the universe expands, more space is created, which means more energy, which drives further expansion. This is called the cosmological constant, and it fits the observations reasonably well. But it raises as many questions as it answers. Why should empty space have energy? Why should that energy have exactly the value it does, neither stronger nor weaker? The value of the cosmological constant is fantastically small, and yet perfectly tuned to allow the universe to exist as we see it. If dark energy were even slightly stronger, galaxies would never have formed. Matter would have been pushed apart before gravity could pull it together into stars and planets. If it were much weaker, the universe might have collapsed back on itself long ago. So we're left with a mystery, an energy that permeates all of space, an energy that determines the fate of the universe, an energy we cannot explain. And dark energy is not the only invisible component of the cosmos. There is also dark matter, another unseen presence, making up about 27% of the universe. Dark matter doesn't emit light, doesn't absorb light, but it has mass, it has gravity, and it holds galaxies together. When astronomers measure how fast stars orbit within galaxies, they find something strange. The stars at the edges move too quickly. According to the visible matter alone, those outer stars should drift away into space. The galaxy shouldn't hold together. But it does, because there's more mass there than we can see. A halo of invisible matter surrounding each galaxy, providing the extra gravity needed to keep everything bound. We know dark matter exists because we can see its gravitational effects. Galaxies cluster in ways that require more mass than the visible stars and gas provide. Light from distant galaxies bends as it passes through regions of space, bent by gravity, by mass, even though nothing visible is there. Dark matter shapes the large-scale structure of the universe. It forms a cosmic web, filaments and nodes where galaxies gather, connected by invisible threads of dark matter spanning millions of light years. But what is it made of? We don't know. It's not ordinary matter, protons and neutrons and electrons. We've looked for dark clouds of regular atoms, and they're not there in sufficient quantities. Dark matter must be something else, something that interacts with gravity, but almost nothing else. Physicists have proposed various candidates, exotic particles never seen in laboratories, that formed in the early universe and have been drifting through space ever since. WIMPs, weakly interacting massive particles. Axions, ultralight particles predicted by certain theories but never detected. Primordial black holes, tiny black holes formed in the first moments after the Big Bang. Experiments search for these particles. Detectors buried deep underground wait for a dark matter particle to collide with an atom. Particle accelerators try to create dark matter in collisions. Telescopes look for indirect signs, gamma rays or other radiation that dark matter might produce when particles meet and annihilate. So far, nothing definitive, only limits, only the growing certainty that if dark matter is made of particles, they are incredibly elusive. And so the mystery deepens. We live in a universe where 95% of the content is invisible to us. Dark matter and dark energy dominate the cosmos, shaping everything we see, and yet we understand almost nothing about them. The stars, the planets, the galaxies, all the ordinary matter we can see and touch, amounts to less than 5% of what exists. We are a small minority in a universe dominated by the unseen. This is humbling, and in a way, it's also calming, to know that reality is so much larger than our immediate perception, that the universe holds depths we're only beginning to glimpse. You don't need to grasp all of this tonight. You don't need to hold on to these concepts. They are simply here, part of the landscape we're moving through. Mysteries among many mysteries. Let your body settle more deeply now. Let your muscles release whatever tension they've been holding. Let the darkness behind your closed eyes mirror the darkness of space, vast and calm, and filled with hidden presence. We're going to continue moving through these mysteries, slowly, gently, and as we do, you can allow yourself to drift further, to let the words become background, to find whatever rest you need. The universe is patient. The mysteries are patient. And tonight, you can be patient with yourself, too. There is a hum in the universe that no one expected to find. In 2015, scientists detected gravitational waves for the first time, ripples in space-time itself caused by two black holes colliding more than 1 billion light-years away. The waves traveled across the universe, stretching and squeezing space by less than the width of a proton, until they reached Earth and were captured by exquisitely sensitive detectors. This was a triumph, a confirmation of Einstein's predictions, a new way of observing the cosmos, not through light, but through the vibrations of space-time itself. But as the detectors were refined, as more observations were made, something unexpected emerged. A background noise, a persistent signal coming from all directions at once. The gravitational wave background, a hum of space-time vibrations filling the universe, and we don't yet know what's creating it. Perhaps it's the combined effect of countless distant collisions, black holes and neutron stars merging throughout cosmic history, their waves overlapping, blending into a single persistent tone. Perhaps it's something from the very early universe, vibrations set in motion during the first moments after the Big Bang, still echoing through space today. Or perhaps it's something else entirely, something we haven't imagined yet. The detectors are improving, more observations are being made, and slowly, carefully, scientists are beginning to separate the hum into its components, trying to identify which sources contribute to the background. But for now, it remains largely mysterious, a cosmic drone, a vibration underlying everything, the sound of space-time itself resonating. And space-time is full of mysteries. One of the deepest questions in physics is what space-time actually is. We talk about it as though it's a fabric, something that can bend and ripple and tear. But this is metaphor. Space-time is not made of threads or particles or any substance we can point to. It is, as far as we can tell, fundamental, the stage on which everything else happens, the framework that gives meaning to location and duration. Einstein showed us that space-time is dynamic, that mass and energy curve it, that this curvature is what we experience as gravity. A planet orbits a star not because it's being pulled by some invisible force, but because it's following the straightest possible path through curved space-time. This is a beautiful picture, elegant, predictive, but it leaves questions unanswered. At the smallest scales, quantum mechanics tells us that everything fluctuates, that energy and matter exist in states of probability, spread out, uncertain, until measured. If space-time is real, if it's a physical thing, then it too should fluctuate at small scales. This leads to the idea of quantum foam, the notion that at distances far below what we can observe, space-time might be bubbling, twisting, forming, and dissolving in a chaotic dance. At these scales, the smooth fabric tears apart into something stranger, something where the very concepts of space and time lose their usual meaning. But we cannot test this. The scales involved are too small. The energies required to probe them are too high. And so the quantum nature of space-time remains theoretical, a prediction waiting for technology that may not exist for generations. Some physicists suggest that space-time might not be fundamental at all, that it might emerge from something deeper. Just as temperature emerges from the motion of molecules, space-time might emerge from the interactions of more basic entities. Information, perhaps, or quantum entanglement, or structures we don't yet have names for. If this is true, then space and time are illusions in a sense. Useful approximations that work at human scales, but break down when we look too closely. Reality, at its deepest level, might be something entirely different from what we perceive. These ideas are speculative. They exist at the boundary where mathematics meets philosophy, but they're taken seriously because the problems they address are real. The incompatibility between quantum mechanics and general relativity is not just a theoretical inconvenience. It prevents us from understanding the first moments after the Big Bang. It prevents us from understanding what happens at the center of black holes. Until we resolve this, until we find a theory that unifies quantum mechanics and gravity, some of the universe's deepest mysteries will remain closed to us. And perhaps that's fitting. Perhaps there are questions that require not just new observations or new instruments, but entirely new ways of thinking, new frameworks that we haven't developed yet because we don't know what we're missing. The history of science is full of these moments, times when progress seemed impossible, when mysteries seemed intractable, until someone made a conceptual leap that changed everything. Newton gave us laws of motion and gravity. Einstein gave us relativity and showed that space and time are connected. Quantum mechanics revealed that reality at small scales is probabilistic, uncertain, strange beyond intuition. Each of these was a revolution. Each changed not just what we knew, but how we thought about the universe. And each revealed new mysteries, deeper ones, questions that previous generations couldn't even formulate because they lacked the concepts. Perhaps we're in a similar position now. Perhaps the mysteries we face, dark matter and dark energy and quantum gravity, are waiting for a new revolution, a new way of seeing that will make the answers obvious in retrospect. Or perhaps not. Perhaps some mysteries are more stubborn. Perhaps the universe guards its deepest secrets carefully, revealing them only after centuries of patient work. Either way, the mysteries are there, and they're not going anywhere. You can let that thought settle. Let it rest alongside you. There is no urgency, no deadline. The universe has time, and so do you. Let your breath continue its gentle rhythm, in and out, slow and steady. We're going to turn our attention now to something closer, still mysterious, but within our own solar system. Objects we can visit, study, touch, if we build the right spacecraft. And yet, even here, even in our cosmic neighborhood, mysteries abound. There is a moon orbiting Saturn called Enceladus. It's small, barely 500 kilometers across, covered in pristine ice that reflects nearly all the sunlight that touches it. From a distance, it looks quiet, frozen, dead. But it's not. In 2005, the Cassini spacecraft flew past Enceladus and discovered geysers, plumes of water vapor and ice crystals erupting from cracks near the South Pole, shooting hundreds of kilometers into space. This was unexpected. Small moons are supposed to be geologically dead. They don't have enough internal heat to drive volcanic activity. They cool quickly after formation and remain frozen ever after. But Enceladus is active. Somehow, it has retained enough heat to maintain a liquid ocean beneath its icy shell, an ocean that vents into space through the cracks, the tiger stripes, as they're called, that scar the southern hemisphere. Where does the heat come from? Tidal forces. As Enceladus orbits Saturn, the planet's gravity pulls on it unevenly, flexing the moon, kneading it like dough. This friction generates heat, enough heat to keep water liquid, enough heat to drive the geysers. But this raises questions. How thick is the ice shell? How deep is the ocean? Is it a global ocean or localized to the South Pole? And most intriguingly, could there be life in that ocean? The plumes contain organic molecules, carbon-based compounds, the building blocks that, on Earth, are associated with life. They contain salts and silica particles, suggesting the water is in contact with a rocky sea floor, possibly with hydrothermal vents like those in Earth's deep oceans. On Earth, hydrothermal vents support rich ecosystems. Life thrives there, independent of sunlight, feeding on chemical energy from the planet's interior. Could the same be happening on Enceladus? Could microbes, or something like them, exist in that dark ocean beneath the ice? We don't know. The evidence is tantalizing, but not conclusive. The organic molecules could form through non-biological processes. The conditions might not be quite right for life as we understand it, but the possibility is there. Real enough that scientists are designing missions to return to Enceladus, to fly through the plumes, to collect samples, to analyze them in more detail, to search for signs, definitive signs, that we are not alone. And Enceladus is not unique. Europa, a moon of Jupiter, also has an ocean beneath ice, possibly a deeper ocean, with more water than all of Earth's seas combined. Titan, Saturn's largest moon, has lakes and rivers of liquid methane on its surface, and possibly a water ocean deep below. The outer solar system is full of hidden oceans, worlds within worlds, and each one is a place where life might exist, or might have existed once, or might exist someday. This changes how we think about habitability. For most of history, we assumed life required a planet like Earth, the right distance from the sun, the right temperature, liquid water on the surface. But now we know that oceans can exist far from the sun, kept warm by tidal heating or radioactive decay in the interior. Life, if it's anywhere beyond Earth, might be more likely to exist beneath ice than on surfaces exposed to space, and this expands the possibilities immensely. Icy moons are common. Nearly every gas giant has them. In our solar system alone, there are dozens of candidates, and if other star systems follow similar patterns, then the galaxy might be full of ocean worlds, hidden, quiet, but potentially teeming with life. Of course, this is speculation. We have no proof, no confirmed detection of life anywhere beyond Earth. But the possibility has shifted from distant dream to serious scientific question, from maybe someday to we could find out in our lifetimes. And that is exciting and humbling and somehow calming, to know that the answer to one of humanity's oldest questions, are we alone, might be waiting beneath the ice of a small moon only 1 billion kilometers away. You can rest with that image: dark oceans, hidden beneath ice, silent, patient, holding secrets that might one day be revealed. There is no rush. The moons will still be there. The oceans will still be there. And the question of what might live within them will remain, waiting for the spacecraft we'll build, the missions we'll send, the discoveries we'll make, slowly, carefully, in time. Let your body sink a little deeper now. Let whatever surface you're resting on support you fully. There is nothing you need to hold up, nothing you need to maintain. We're going to drift now to another mystery, one that exists not on a moon or a planet, but in the space between worlds, in the outer reaches of the solar system, where sunlight is faint and the cold is absolute. There are objects out there, small bodies, remnants from the formation of the solar system, and their behavior is teaching us that we still have much to learn about how planets form, about the forces that shape the early solar system, about the processes that turn clouds of gas and dust into the ordered systems of planets and moons we observe today. The Kuiper Belt, a vast ring of icy bodies beyond Neptune's orbit, stretching from about 30 times Earth's distance from the Sun to 50 times that distance, perhaps even farther. We're still mapping it, still discovering objects we didn't know were there. Pluto is the most famous resident of the Kuiper Belt. Once called the 9th planet, now classified as a dwarf planet, one among many. But Pluto is not typical. It's unusually large for a Kuiper Belt object, and its orbit is strange, tilted and elongated, crossing Neptune's path. Why? How did Pluto end up in such an odd orbit? This is part of a larger mystery about the early solar system. Computer simulations suggest that the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form where they are now. They formed closer together, nearer to the Sun, and then, through gravitational interactions with each other, and with the disk of debris left over from planet formation, they migrated outward. This migration was chaotic. Orbits shifted. Some objects were flung inward. Others were scattered outward. The Kuiper Belt itself might be a remnant of this chaos, populated by objects that were originally closer to the Sun and were pushed out as the planets moved. This would explain many things: the strange orbits, the gaps and clusters, the way some objects seem to have been captured from elsewhere. But the details remain uncertain. The simulations work roughly, but they require specific conditions, specific initial configurations, and we don't know if those conditions actually existed. We're learning more as we discover more objects. Each new Kuiper Belt body adds a data point. Each orbit refines our models. Slowly, the picture becomes clearer, and then there are objects even farther out, beyond the Kuiper Belt, in regions so distant that they take thousands of years to complete a single orbit around the Sun. Sedna, discovered in 2003. Its closest approach to the Sun is still 76 times Earth's distance. Its farthest point is nearly 1,000 times Earth's distance. An orbit so elongated, so extreme that it's hard to explain. What could have placed Sedna in such an orbit? Not the giant planets. Their gravity doesn't reach that far. Perhaps a passing star, billions of years ago, pulled on Sedna and flung it outward. Perhaps Sedna formed elsewhere and was captured by the Sun's gravity during a close encounter. Or perhaps there's something else out there, something we haven't found yet. Some astronomers believe there might be another planet in the outer solar system, a 9th planet, not Pluto, but something larger, farther away, massive enough to influence the orbits of distant objects like Sedna. This hypothetical planet 9 would be several times the mass of Earth, orbiting hundreds of times farther from the Sun than we are. Out there, it would be cold, dark, difficult to see even with powerful telescopes. The evidence for Planet 9 is indirect, a pattern in the orbits of several distant objects, a clustering that seems too regular to be coincidence, as though something massive is shepherding these objects, keeping their orbits aligned. But this is not proof. The pattern could be coincidence, or it could be an artifact of the way we search for objects, a bias in where we look that creates apparent structure where none exists. Searches are ongoing. Telescopes scan the sky, surveys deepen, and if Planet 9 is there, if it exists, we will find it eventually. The solar system is large, but not infinite. Every patch of sky can be checked, every faint point of light analyzed. But for now, the outer solar system remains a place of mystery, a region we've barely explored, where objects drift in darkness, where the sun is just another star, where cold and silence reign, and perhaps that's appropriate. The edges of our solar system mirror the edges of our knowledge. Both fade into uncertainty. Both hint at things beyond. Both remind us that even in our own cosmic backyard, there are secrets waiting to be uncovered. You can let your mind drift through that darkness now. Let it wander among the distant objects, the slow-moving bodies, the frozen worlds at the edge of the sun's influence. There's a peace in that distance, a stillness. Nothing happens quickly out there. Orbits take millennia. Changes unfold over geological time. There is no urgency, no rush, just the slow, patient turning of the cosmos. There is a region of space between Mars and Jupiter where something failed to become. The asteroid belt. Millions of rocky fragments, ranging from grains of dust to bodies hundreds of kilometers across, orbiting the sun in a broad band. Collectively, they contain less mass than our moon, scattered across a volume so vast that spacecraft can pass through without coming close to any single object. This is what remains of a planet that never formed. In the early solar system, as dust and gas collapsed into the sun, material also gathered into rings around it. Within these rings, particles collided, stuck together, grew. This is how planets form. Gradual accumulation. Dust to pebbles, pebbles to boulders, boulders to planetesimals, planetesimals to planets. But in the region between Mars and Jupiter, this process was interrupted. Jupiter's gravity was too strong. It stirred the material, accelerated collisions, prevented accumulation. Instead of merging peacefully, objects smashed into each other violently, breaking apart as often as they joined. And so, no planet formed, only fragments, a scattered field of debris, the asteroid belt. Or so the story goes. But even this simple narrative hides mysteries. Why are there so few asteroids? If the asteroid belt is the remnant of planet formation, it seems remarkably depleted. Most of the original material must have been scattered elsewhere, flung into the inner solar system, ejected entirely, or perhaps absorbed by Jupiter itself. But the details of this clearing process are unclear. Computer models can reproduce something like the asteroid belt, but they require careful tuning, specific assumptions about Jupiter's migration, about the density of the original disk, about the timing of events. And different models make different predictions. Some suggest the asteroid belt should be more massive. Others suggest different compositional gradients. The observations don't always match the expectations. There's also the question of why asteroids vary so much. Some are rich in metals, others are rocky. Still, others are dark, carbon-rich, almost like frozen tar. This diversity tells us they formed in different regions, under different conditions. But how did they end up mixed together? The asteroid belt is not neatly organized. Metal-rich asteroids and carbon-rich asteroids orbit side by side, as though something shuffled them, mixed them, scattered them into their current arrangement. Jupiter's migration could explain this. As Jupiter moved inward and then outward again, its gravity would have stirred the asteroid belt thoroughly, mixing objects that formed at different distances from the Sun. But again, this requires specific conditions, a specific history. And we don't have a recording of the early solar system. We can only infer, only reconstruct, only build models and test them against what we see today. Some asteroids are strange in other ways. Psyche, for example, appears to be almost entirely metal, iron and nickel, as though it's the exposed core of a larger body that was shattered by collisions, leaving only the dense metal center behind. NASA is sending a spacecraft to Psyche. It will arrive in 2029, orbit the asteroid, study its surface, measure its composition. If Psyche really is a planetary core, it offers a unique opportunity. We can never drill to the core of Earth or any other planet. The depths are too great, the conditions too extreme. But Psyche might give us a direct look at what planetary cores are like, what they're made of, how they form, how they contribute to the magnetic fields that some planets generate. Or Psyche might turn out to be something else entirely. Perhaps it's not a core at all, but a strange type of asteroid that formed metal-rich from the beginning. We won't know until we arrive, until we see it up close. And this is a recurring theme in solar system exploration. Every time we visit a new world, we find surprises, things that don't quite fit the models, features that suggest histories more complex than we imagined. Ceres, the largest object in the asteroid belt, was thought to be a simple rocky body. But when the Dawn spacecraft arrived, it found bright spots on the surface, deposits of salt, evidence of water beneath the crust, perhaps even cryovolcanoes, ice volcanoes, erupting brines instead of lava. Ceres, it turns out, is more like a moon than an asteroid, a differentiated body with a core, mantle, and crust, perhaps once with an ocean, perhaps still with pockets of liquid water deep below. This blurs the categories we use: asteroid, moon, planet, dwarf planet. These labels are human constructs, attempts to organize what we see. But nature doesn't follow our labels. Reality is messier, more complex, full of objects that sit between categories that challenge our definitions. And perhaps that's a lesson worth carrying forward, that the universe is not obligated to fit our expectations, that mystery and surprise are not problems to be eliminated, but natural parts of exploration. Every answer leads to new questions. Every discovery reveals new mysteries. And this is not a failure of science. It is its strength, the willingness to revise, to update, to follow the evidence wherever it leads, even if it leads somewhere unexpected. You can let your breath deepen now. Let the tension in your jaw soften. Let your tongue rest easily in your mouth. These small releases add up. Each one allows a little more rest to settle in. We're going to move inward now, closer to the Sun, to the planets that orbit in the warmth and light, the terrestrial planets, rocky worlds, Earth, Venus, Mars, Mercury. And even here, in the most studied region of the solar system, mysteries remain. Mercury is strange. It's the smallest planet, barely larger than some moons. Its surface is scarred with craters, ancient impacts from the early days of the solar system when debris was still abundant. But Mercury also has something no one expected: a magnetic field. Most magnetic fields in the solar system are generated by dynamos, liquid metal in planetary cores, stirred by the planet's rotation, creating electric currents that produce magnetic fields. Earth has a strong dynamo, so does Jupiter. But Mercury is tiny, and small planets cool quickly. By all expectations, Mercury's core should have solidified long ago. No liquid, no dynamo, no magnetic field. And yet, the field is there. Weak, only about 1% of the strength of Earth's, but real, measurable. How? Perhaps Mercury's core is not fully solid. Perhaps a thin outer layer remains liquid, sustained by sulfur or other impurities that lower the melting point. Perhaps this thin layer is enough to generate the weak field we observe. Or perhaps something else is happening. Perhaps Mercury's magnetic field is a remnant, a fossil from when the core was entirely liquid, somehow frozen into the planet's structure and persisting to this day. We don't know. The data is sparse. Mercury has only been visited by 2 spacecraft, Mariner 10 in the 1970s and Messenger in the 2000s. Both provided valuable information, but many questions remain. And Mercury holds other mysteries. Its surface is darker than expected, as though covered in something that absorbs light, perhaps carbon, perhaps some other material, delivered by ancient comets or formed through processes we don't fully understand. There are also strange features called hollows, small, shallow depressions scattered across the surface with bright, reflective floors. They look fresh, recent, as though they're still forming today. But what creates them? Perhaps volatile materials buried beneath the surface are evaporating in the heat of the sun. Perhaps the solar wind, streams of particles from the sun, is eroding the surface in some way. Theories exist, but the process remains unclear. Mercury is full of small mysteries like this, features that hint at active processes, at a world more dynamic than its cratered, dead appearance suggests. Venus is perhaps the most mysterious of all. From space, Venus looks serene, covered in thick clouds, pale yellow, featureless, beautiful in its simplicity. But beneath those clouds is hell. The surface temperature is hot enough to melt lead. The atmospheric pressure is 90 times that of Earth, equivalent to being a kilometer underwater. The clouds are made of sulfuric acid, rain that never reaches the ground, evaporating in the heat long before it lands. Venus should not be this way. It's nearly the same size as Earth, nearly the same mass. It orbits only slightly closer to the Sun. By all rights, it should be Earth's twin, a temperate world, perhaps with oceans, perhaps even with life. But something went catastrophically wrong. Venus experienced a runaway greenhouse effect. Water vapor trapped heat. The heat evaporated more water. The cycle fed on itself until the oceans boiled away, and the surface became an oven, or so the theory goes, but the details are unclear. When did this happen? How quickly? Was Venus ever cool enough to have liquid water? If so, for how long? There are hints that Venus might have had oceans once. The ratio of hydrogen isotopes in the atmosphere suggests water was present and then lost to space. Computer models show that a slow-rotating planet like Venus could, in principle, have been habitable for billions of years, even this close to the Sun. But we have no direct evidence. Venus's surface is young, geologically speaking, about 500 million years old. Volcanic activity has resurfaced the planet, erasing whatever features existed before. And this volcanic activity is itself mysterious. Venus has no plate tectonics, no continental drift. Its crust is a single solid shell, and yet it has more volcanoes than any other planet in the solar system. Thousands of them, some enormous. Ma'at Mons rises 8 kilometers above the surrounding plain, comparable to Earth's largest volcanoes. Are any of these volcanoes active today? We don't know. Some observations suggest possible recent activity. Changes in sulfur dioxide levels in the atmosphere, bright spots on the surface, possibly fresh lava. But the evidence is ambiguous. Venus's thick clouds make observation difficult. Radar can penetrate them, mapping the surface, but only at low resolution. Visible light doesn't make it through at all. To study Venus properly, we need to send spacecraft, landers, orbiters, probes that can survive the extreme conditions long enough to gather data. Several missions have tried. The Soviet Venera probes landed successfully in the 1970s and 1980s, sending back images and measurements before succumbing to the heat. But they lasted less than 2 hours. Most failed much sooner. New missions are planned. Better technology, better materials. Perhaps we'll finally understand what happened to Venus, why Earth's twin became a hell world, whether it was always this way, or whether something changed. And this question matters, not just for Venus, but for understanding planets in general, for predicting which exoplanets around other stars might be habitable, for knowing how close to a star is too close, how thick an atmosphere can be before a greenhouse effect runs away. Venus is a cautionary tale, a reminder that planets are fragile, that small changes can have enormous consequences, that the line between habitable and uninhabitable might be thinner than we'd like to think. But it's also a reminder of how much we still don't know, how many mysteries remain, even in our own solar system. Worlds we've studied for centuries, and yet they still surprise us, still challenge our understanding, still hold secrets. You can let your shoulders drop now. Let your arms rest heavily. Let gravity pull gently on your body, reminding you that you're supported, that you don't need to hold yourself up, that you can simply be. Mars was not always the cold, dry desert it is today. Billions of years ago, water flowed on Mars. Rivers carved valleys. Lakes filled impact craters. Perhaps even oceans covered parts of the northern lowlands, shallow seas under skies that might have been blue. The evidence is everywhere. Ancient riverbeds, delta formations, layered sediments, minerals that only form in the presence of water. Mars was once a wetter world, warmer, perhaps more like Earth. But something changed. The water disappeared. The climate shifted. Mars became the frozen desert we see today, a world where carbon dioxide snow falls at the poles, and the thin atmosphere cannot sustain liquid water on the surface. What happened? The leading theory points to the loss of Mars's magnetic field. Early in its history, Mars had a global magnetic field, generated by a dynamo in its molten core. This field protected the atmosphere from the solar wind, the stream of charged particles flowing from the sun. But Mars is smaller than Earth. It cooled faster, and about 4 billion years ago, the dynamo shut down. The magnetic field vanished. Without that protection, the solar wind began stripping away the atmosphere, slowly, particle by particle, over millions of years. As the atmosphere thinned, the surface pressure dropped. Water could no longer remain liquid. It either froze or evaporated. Much of it was lost to space, carried away by the same solar wind that stripped the atmosphere. What remains is locked in ice, at the poles, underground, frozen into the soil. Mars is not dry exactly. It still has water, but it's trapped, inaccessible, waiting, and this raises questions. If Mars once had liquid water, if it once had a thicker atmosphere, could it have had life? We know that on Earth, life appeared early. As soon as the surface cooled enough to allow liquid water, life emerged. Microbial life, simple but persistent, filling every available niche. If life is a natural consequence of liquid water and organic chemistry, then Mars might have had life too, during those early, wetter years, before the atmosphere was lost, before the rivers dried. And if life began on Mars, did it survive? Could it still exist today, deep underground, in pockets of liquid water, sheltered from the harsh surface? This is one of the driving questions behind Mars exploration. We've sent rovers, landers, orbiters, all searching for signs of past or present life. We've drilled into rocks, analyzed soil, searched for organic molecules, and we found hints. Organic molecules are present. Methane appears in the atmosphere, sometimes in bursts, suggesting active sources. Seasonal changes that could be biological, though they could also be chemical or geological. But no definitive proof, no fossils, no clear biosignatures, only tantalizing possibilities, suggestions, maybes. Perhaps life never began on Mars. Perhaps the conditions weren't quite right. Perhaps the window of habitability was too brief. Or perhaps life did begin, but left no traces we can recognize. No remains, no markers, only the silence of deep time. Or perhaps we haven't looked in the right places yet. Mars is large. We've explored only a tiny fraction of its surface. The most interesting regions, from a habitability standpoint, are often the most difficult to reach. Deep canyons, polar ice, subsurface aquifers. Future missions will go to these places, will drill deeper, will search more thoroughly. And perhaps one day we'll find something. A fossil, a chemical signature, a living microbe in a subsurface lake. Or perhaps we won't. Perhaps Mars kept its secrets. Perhaps life, if it ever existed there, vanished completely, leaving only the silent rocks and dust. Either way, the question will persist. The mystery will remain. Until we have an answer, Mars will continue to haunt us with possibility, with the tantalizing suggestion that we are not, and perhaps never were, alone. You can rest with that uncertainty now. Let it wash over you. There is no need to resolve it tonight. No need to find answers. The mystery is enough. The question is enough. Let your breathing continue. Slow, steady. Each breath a little deeper than the last. Each exhale releasing a little more tension. We're going to move through a few more mysteries now. Quieter ones, smaller scales, but no less profound in their way. There is a light in the sky that moves in ways we don't fully understand. Auroras, the northern and southern lights, curtains of green and red and purple, shimmering across polar skies, dancing with a motion that seems almost alive. We know what causes them in broad strokes. Charged particles from the sun, carried by the solar wind, interact with Earth's magnetic field. Some of these particles are funneled toward the poles, where they collide with atoms in the upper atmosphere. These collisions transfer energy, exciting the atoms, causing them to emit light. Oxygen produces green and red. Nitrogen produces blue and purple. The colors depend on the altitude, the energy of the particles, the type of atom excited. This explanation works. It accounts for the basic phenomenon. But when we look closely at auroras, when we study them in detail, we find structures and behaviors that don't fit neatly into simple models. There are auroral arcs, stable bands of light that can stretch for thousands of kilometers. There are flickering auroras, pulsating like a heartbeat. There are discrete auroral forms, small, bright patches that appear and vanish in seconds. There are curls and folds, waves and ripples, patterns that suggest complex dynamics in the magnetosphere, in the region of space where Earth's magnetic field dominates. And there's something called Steve, strong thermal emission velocity enhancement, a narrow ribbon of purple light stretching east to west across the sky, accompanied sometimes by green picket fence structures, vertical columns of light marching beside it. Steve was known to aurora watchers for years, photographed and documented, but dismissed by scientists as a typical aurora, until recently, when careful analysis showed it's not a typical aurora at all. It occurs at lower latitudes, at different altitudes, with different physics. Steve is caused by a river of hot, fast-moving plasma in the ionosphere, a jet stream of charged particles flowing at several kilometers per second, heated to thousands of degrees. Why this jet forms, why it appears when it does, and what relationship it has to the more familiar auroras, we're still working out. Auroras remind us that even common phenomena, things people have watched for millennia, can harbor mysteries. That what seems understood at first glance may reveal complexity upon closer inspection. And Earth's magnetosphere itself is full of mysteries. The magnetosphere is the region around Earth shaped by our planet's magnetic field. It's not a simple bubble. It's compressed on the side facing the sun, where the solar wind pushes against it, and stretched into a long tail on the night side, extending millions of kilometers downstream. Within this region, particles spiral along field lines, trapped, forming the Van Allen radiation belts. These belts protect us by capturing high-energy particles that would otherwise reach the surface. But they also pose hazards to satellites and astronauts, concentrations of radiation intense enough to damage electronics and harm living tissue. The belts were discovered in the 1950s by some of the first satellites launched into space, and they've been studied extensively since. But they still surprise us. In 2012, NASA spacecraft discovered a third radiation belt, temporary, appearing and disappearing over the course of weeks. No one predicted it. The models didn't show it, and yet there it was, a distinct band of particles, separated from the two known belts. It formed, persisted for a few weeks, then merged with the outer belt and vanished. Why? The details involve complex interactions between the solar wind, Earth's magnetic field, and electromagnetic waves rippling through the magnetosphere. But the fact that such a structure could appear, unannounced, in a region of space we thought we understood, is humbling. It suggests that the magnetosphere is more dynamic, more variable than we realized, and there are other phenomena. Magnetic reconnection, where field lines break and rejoin, releasing enormous amounts of energy in sudden bursts. This happens constantly in the magnetosphere, but we don't fully understand how it starts, or why it happens when and where it does. There are chorus waves, electromagnetic whistles that sweep upward in frequency, accelerating particles to high energies. There are substorms, sudden releases of energy that light up auroras and disturb the magnetic field. All of these are pieces of a larger puzzle, the puzzle of how magnetic fields, charged particles, and plasma interact, how energy flows through these systems, how they respond to external forcing, like changes in the solar wind. Understanding this matters, not just for Earth, but for predicting space weather, solar storms that can disrupt satellites, communication systems, power grids, events that, in our increasingly technological world, carry real risks. And beyond practical concerns, understanding the magnetosphere helps us understand other planets, other magnetic fields. Jupiter's magnetosphere is enormous, dwarfing Earth's. Saturn has a magnetosphere shaped by its moon Enceladus, which pumps water vapor into space, seeding the magnetic field with particles. Every magnetic field tells a story about the planet's interior, about its history, about the interactions between the planet and its environment. And each one is slightly different. Each one presents unique challenges, unique mysteries. You can let your eyes remain closed now. Let the darkness be comfortable. There's no need to see anything. Just rest in the blackness behind your eyelids. Soft, encompassing, gentle. There is a boundary where the sun's influence fades and interstellar space begins, but the exact location of this boundary is uncertain, and what lies beyond is only partly known. The heliosphere, the bubble of space carved out by the solar wind, the stream of particles flowing constantly from the sun, expanding outward at hundreds of kilometers per second, pushing back the thin gas of interstellar space. Within the heliosphere, we're protected. The solar wind acts as a shield, deflecting most galactic cosmic rays, high-energy particles from distant supernovae and other sources. Without this protection, Earth would be bathed in higher levels of radiation. But eventually, the solar wind slows, runs out of energy, meets resistance from the interstellar medium, and somewhere out there, far beyond the planets, the solar wind stops. The heliosphere ends. This boundary is called the heliopause, and 2 spacecraft have crossed it. Voyager 1 in 2012, Voyager 2 in 2018. Both spacecraft detected sudden changes. The density of particles increased. The magnetic field shifted, the direction of particles changed, no longer flowing from the sun, but from interstellar space. They had left the solar system, in a sense, entered the galaxy proper, a region where the sun is just one star among billions, with no special influence. But the crossing was not sharp, not a single clear line. Instead, there were layers, regions, a boundary region where solar and interstellar influences mixed, and the two spacecraft, crossing at different locations, found different conditions, suggesting that the heliopause is not uniform, not a simple sphere, but complex, shaped by the interstellar magnetic field, by the motion of the solar system through the galaxy, by turbulence and variations in the solar wind. We're still learning what the heliopause looks like, how thick it is, how it changes over time. The Voyagers are sending back data, but they're traveling in only two directions. They can't map the full structure. They give us only narrow slices, cross-sections through a vast three-dimensional boundary. And beyond the heliopause lies interstellar space, the void between stars, not truly empty, but filled with thin gas, dust, magnetic fields, cosmic rays. Interstellar space is quieter than the heliosphere. The solar wind no longer dominates, but it's not entirely calm. There are clouds of denser gas, bubbles blown by ancient supernova, shock waves from massive stars and stellar explosions. Our solar system is currently passing through one of these clouds, the local interstellar cloud, a region of slightly higher density, part of a larger structure called the local bubble, a cavity carved out by supernovae millions of years ago. We're swimming through these structures, moving at about 20 kilometers per second relative to the surrounding gas, and this motion shapes the heliosphere, compressing it in the direction we're traveling, stretching it out behind. In a few thousand years, we'll pass out of the local interstellar cloud into a different region, and the heliosphere will change shape in response. The boundary will shift. The level of protection will adjust. These are slow changes, playing out over timescales far beyond human lifetimes. But they remind us that even the space around our sun is not static, not unchanging. It's a dynamic interface between the sun and the galaxy, constantly adjusting to the conditions around it. And the galaxy itself is full of these boundaries. Every star has a heliosphere. Every star carves out a bubble in the interstellar medium, and these bubbles overlap, interact, merge, creating a frothy structure on scales too large to fully visualize. We're part of that structure, part of the vast, churning ecosystem of the galaxy, connected to everything around us in ways we're only beginning to understand. You can let that sense of connection settle now. Let it be gentle, not overwhelming, but quietly present. A reminder that you are part of something larger, something ancient, something ongoing. Let your breath find a rhythm that feels natural. Let your body adjust, shifting slightly if needed, finding comfort. There is a phenomenon that occurs on Earth, rare but unmistakable, that we still cannot explain fully. Ball lightning, glowing spheres that appear during thunderstorms, floating through the air, drifting into buildings through open windows, lasting for seconds, sometimes minutes, before vanishing or exploding with a soft pop. Reports of ball lightning go back centuries. Sailors described glowing balls rolling across ship decks during storms. Pilots have seen them appear near aircraft. Scientists have documented cases where ball lightning entered laboratories, drifted past astonished researchers, and disappeared. For a long time, ball lightning was dismissed, considered folklore, optical illusions, exaggerations of regular lightning. But the reports are too consistent, too detailed, too numerous to dismiss entirely. And in recent years, a few instances have been captured on video, recorded by chance during storms. The evidence is clear. Ball lightning is real. But what is it? This remains uncertain. One theory suggests it's a ball of plasma, ionized gas held together by magnetic fields, perhaps created when regular lightning strikes the ground, vaporizing silicon and other materials, which then react in the air to form a glowing sphere. Another idea involves microwave radiation, trapped in a resonant cavity formed by atmospheric layers, creating a sustained electric field that ionizes air in a localized region. Still others propose exotic chemistry, oxidation reactions, nanoparticles burning slowly, quantum effects we don't yet understand. Laboratory experiments have created things that look somewhat like ball lightning, briefly glowing spheres, but none reproduce all the reported characteristics. None last as long. None behave quite the same way. And so ball lightning remains a mystery. Rare enough that it's difficult to study. Common enough that it can't be ignored. A reminder that Earth's atmosphere, for all we've learned about it, still holds surprises. And Earth is full of such surprises. Phenomena on the edge of understanding. Things glimpsed briefly and then gone. Sprites. Red flashes high above thunderstorms, reaching toward space. They were reported by pilots for decades before being photographed. Now we know they're electrical discharges in the mesosphere, triggered by lightning below. But the details of their formation are still being worked out. Elves, expanding rings of light, even higher than sprites, caused by electromagnetic pulses from lightning interacting with the ionosphere. Blue jets, narrow cones of blue light shooting upward from storm clouds. All of these were discovered only in recent decades. Some suspected for longer, but confirmed only when cameras sensitive enough and pointed in the right directions captured them. And there may be more. Other transient phenomena. Other brief electrical discharges. Other interactions between the atmosphere and space that we haven't yet documented. The atmosphere is thicker than we sometimes remember. It extends from the surface where we live to hundreds of kilometers up, gradually thinning until it merges with the vacuum of space. And throughout this thickness, processes are occurring. Chemistry, physics, electricity, wind, pressure. Most of it we understand reasonably well, but not all. There are details still being worked out, processes still being discovered, interactions that depend on specific conditions, that only occur rarely, that surprise us when they appear. And perhaps this is fitting. Earth is our home. We've studied it intensively, mapped every continent, probed every ocean, monitored the atmosphere from satellites and balloons and ground stations, and yet it still surprises us, still reveals new phenomena, still holds corners of mystery in its air and water and rock. This should be comforting in a way. If Earth, familiar and close, can still surprise us, then the universe, vast and distant, will never run out of mysteries to offer. There will always be more to discover, always new questions to ask, always phenomena we haven't encountered yet, waiting patiently in the places we haven't looked. Let that thought rest with you. Let it be a gentle presence, not demanding anything, just there, a quiet truth. You can allow your jaw to slacken now. Let your teeth part slightly. Let your tongue rest against the roof of your mouth, soft and still. These small releases matter. Each one is a doorway to deeper rest. Each one allows your body to settle a little further into stillness. We're going to turn now to mysteries of time, of perception, of the way the universe seems to flow in one direction, always forward, never back, and the puzzles this creates, the questions it raises. Why does time have a direction? Why can we remember the past but not the future? Why do broken things never spontaneously repair themselves? These questions sound simple, almost naive, and yet they touch on some of the deepest problems in physics. At the level of individual particles, time is reversible. The equations that describe how particles move work equally well, whether time flows forward or backward. A film of particles colliding, if played in reverse, would show equally valid physics. And yet, in the everyday world, time clearly has a direction, an arrow, pointing from past to future, never the other way. This arrow seems to be connected to entropy, to disorder. The second law of thermodynamics states that entropy, disorder, always increases, never decreases. A broken glass will not reassemble. Heat will not spontaneously flow from cold to hot. Ink dropped in water will spread out, never gather back into a drop. But why should entropy increase? The fundamental laws don't require it. They allow entropy to decrease. It's just extraordinarily unlikely. And this is where probability enters, where statistics becomes part of the story. There are many more ways for a system to be disordered than ordered. Many more configurations of molecules in a room where they're spread evenly than configurations where they're all in one corner. So when particles move randomly, they naturally drift toward more probable states, toward higher entropy, not because of any law forbidding the reverse, but simply because those states are vastly more likely. But this raises a question. If entropy always increases, if disorder always grows, then the universe must have started in a very low entropy state, very ordered, very unlikely. Why? What set the universe up that way? What made the beginning so special, so improbable? This is one of the deepest mysteries in cosmology. The initial conditions problem. The question of why the Big Bang produced a universe poised to evolve in the direction we observe. Some physicists suggest that the universe simply started that way, that the initial state is a brute fact, not explainable through deeper principles. Others propose mechanisms. Perhaps inflation, the rapid expansion thought to have occurred in the first moments, smoothed out irregularities, creating a uniform, low-entropy beginning. Or perhaps our universe is part of a larger multiverse, and we observe a low-entropy beginning because only such universes allow for observers. Anthropic reasoning. We exist in this universe because it's the kind of universe where existence is possible. But none of these answers feel complete. None fully resolve the puzzle. Why should the laws be such that low-entropy states give rise to observers? Why should inflation happen at all? The questions recede, but don't disappear. Each answer opens new depths. new mysteries beneath the mysteries. And so the arrow of time remains, fundamentally unexplained. We can describe it. We can trace its consequences. We can make accurate predictions based on the assumption that entropy increases. But why it points the way it does, why there is an arrow at all, why the universe began in a special state that allows time to have a direction, these questions linger, unresolved, open, waiting for insights we haven't had yet. You don't need to solve them tonight. You don't need to carry them forward into sleep. You can let them fade, let them recede into the background. Just thoughts, just questions, just words spoken into the dark. Your body knows how to rest. It doesn't need understanding, doesn't need answers. It only needs permission. The gentle allowance that it's okay to let go, to stop holding on, to simply be. And you can give that permission now, quietly, without fanfare. Just a soft release, a gentle yielding. Time will continue, forward, always forward, carrying us all. But for now, in this moment, time can slow, can soften, can become less urgent, less demanding. Just breath, just rest, just the slow, patient rhythm of being alive. There is a question that philosophers and scientists have asked for centuries, and we are no closer to answering it now than we were at the beginning. What is consciousness? You are aware, reading these words, thinking thoughts, feeling the surface beneath you, hearing sounds perhaps in the distance, experiencing the quiet flow of your own mind. This experience, this awareness, this sense of being someone, is consciousness. And it is the most immediate, undeniable fact of your existence. You know you are conscious because you are experiencing consciousness right now, and yet we cannot explain it. Neuroscience has made enormous progress. We can map the brain in exquisite detail. We can identify which regions activate during different tasks. We can trace neural pathways, measure electrical signals, watch as information flows through networks of neurons. We know that damage to certain brain regions affects consciousness in specific ways. Damage to the visual cortex eliminates visual experience. Damage to language areas impairs speech and comprehension. The contents of consciousness clearly depend on the brain. But none of this explains why there is experience at all, why the physical processes in the brain should feel like something, why there should be an inner life, a subjective perspective, a sense of what it's like to be you. This is called the hard problem of consciousness. Not the question of how the brain processes information, which is difficult but approachable, but the question of why processing feels like anything, why there is experience accompanying the mechanisms. Some philosophers argue that consciousness might be fundamental, that it's not produced by the brain, but is a basic feature of reality, like mass or charge. In this view, the brain doesn't create consciousness, but rather channels it, shapes it, gives it structure. Others suggest consciousness emerges from complexity, that when information is integrated in certain ways, when systems become sufficiently interconnected and recursive, awareness arises naturally. Consciousness as an emergent property, appearing when the right conditions are met. Still others think we're asking the wrong question, that consciousness is not a single thing, but a collection of processes, and what we call awareness is just the brain's way of modeling itself, creating a narrative, a sense of unity, where none truly exists. But none of these ideas are proven. None can be tested definitively, because consciousness is inherently subjective. You cannot measure another person's experience directly. You can only infer it from behavior, from reports, from neural correlates, and this creates a fundamental limit, an unbridgeable gap, between the objective, third-person perspective of science and the subjective, first-person perspective of consciousness. I can study your brain. I can see which neurons fire when you see the color red. But I cannot access your experience of redness. I cannot know what it's like for you, whether your red is the same as my red, whether we even experience color in the same way. This is the problem of qualia, the problem of subjective qualities, the redness of red, the painfulness of pain, the particular feel of each sensation, thought, and emotion. Qualia seem private, ineffable, impossible to fully communicate. You can describe a color, but the description never captures the experience itself. You can explain what pain is, but no explanation conveys what pain feels like to someone who has never felt it. And yet, qualia are all we have. All experience is composed of them. The entire richness of conscious life is made of these subjective qualities. So consciousness remains a mystery, central to our existence, undeniably real, and yet unexplained, possibly unexplainable through the methods of current science. Perhaps future discoveries will change this. Perhaps we'll find a theory of consciousness that makes it understandable, that bridges the gap between objective brain function and subjective experience. Or perhaps consciousness will remain forever mysterious, a puzzle at the heart of what it means to be alive, to be aware, to be anything at all. You can rest with that mystery now. You don't need to solve it. You don't even need to fully understand it. Consciousness simply is, and you are it, experiencing itself, aware of awareness. Let that be enough. Let it be simple, just being, just existing, just the gentle hum of awareness, requiring nothing, explaining nothing, simply present. Let your attention soften now. Let it become less focused, less directed. Allow your thoughts to drift without following them, like clouds passing across the sky. Present for a moment, then gone. We're going to move through a few more mysteries now, shorter ones, gentler ones, questions that arise from the ordinary world around us, things we encounter every day but rarely stop to wonder about. Why do we dream? Every night, most people dream. Sometimes vivid narrative dreams, sometimes fragmented images, sometimes abstract sensations, impossible to describe. And we've learned a lot about dreaming. We know it occurs primarily during REM sleep, rapid eye movement sleep, when brain activity increases and the body becomes temporarily paralyzed, preventing us from acting out our dreams. We know that most mammals dream. Dogs twitch and whimper in their sleep. Cats' paws move as if running. Even birds show signs of REM sleep. We know that dreaming seems important. People deprived of REM sleep become irritable, have difficulty concentrating, show impaired memory. The brain needs to dream, for reasons that aren't entirely clear. But what are dreams for? Why does the brain create these strange, often illogical narratives? One theory is that dreams help consolidate memories, that during sleep, the brain replays experiences, strengthening important connections, pruning unnecessary ones. Dreams might be the subjective side of this process, the conscious experience of memories being processed and filed away. Another idea is that dreams allow emotional regulation, that they provide a safe space to work through fears, anxieties, conflicts, a kind of internal therapy where difficult emotions can be experienced and resolved without real-world consequences. Still others suggest dreams are a form of simulation, that the brain practices responses to threats, rehearses social interactions, explores possibilities. Evolution favoring individuals who could mentally prepare for future challenges. Or perhaps dreams are noise, random firing of neurons during sleep, with the brain's narrative centers trying to make sense of the chaos, weaving disparate signals into stories. Each theory has support. Each explains some aspects of dreaming, but none captures everything. The full function of dreams, if they have a function, remains uncertain, and some dreams are stranger than others. Lucid dreams, where the dreamer becomes aware they're dreaming and can sometimes control the dream's content. These occur spontaneously for some people, can be learned with practice by others. What allows lucidity? Why does the brain sometimes recognize it's dreaming while usually accepting the dream as reality? The mechanisms are being studied, but much remains unknown. There are also recurring dreams, the same scenario appearing night after night, the same anxieties playing out in similar ways. What causes these repetitions? Why does the brain return to the same themes? And what about nightmares? Why do we sometimes dream of terrible things? Fear, danger, loss. These dreams can feel more vivid, more emotionally intense than pleasant dreams. Why? Perhaps they reflect unresolved anxieties. Perhaps they're the brain's way of preparing for threats. Or perhaps they're simply the inevitable result of a brain that experiences fear, that remembers dangers, that processes these emotions during sleep. Whatever their purpose, dreams remain mysterious. A nightly journey into strangeness. A reminder that even our own minds are not fully known to us. You might dream tonight, or you might not remember if you do. Either way, your brain will cycle through its stages of sleep, will process the day, will prepare for tomorrow, doing whatever it does in the hours of darkness. And you don't need to understand it, don't need to direct it. Your brain knows what to do, has done it every night of your life, will continue long after your conscious mind has released its grip and drifted into whatever dreams may come. Let your eyelids grow heavier. If they're not already closed, let them close now, gently, naturally, no effort required. There is another mystery about sleep itself. Why do we need it at all? Sleep seems like a vulnerability. Animals that sleep cannot watch for predators, cannot search for food, cannot mate or defend territory. Sleep should be a disadvantage, something evolution would eliminate. And yet, every animal sleeps. Some only briefly, a few hours a day. Others extensively, like cats sleeping 16 hours or more. But all animals show some form of rest, some period of reduced activity and awareness. This universality suggests sleep is essential. But essential for what? We know that sleep deprivation is harmful. Go without sleep long enough, and cognitive function deteriorates. Reaction times slow. memory fails. Hallucinations can occur. Eventually, prolonged sleep deprivation is fatal. But what is sleep doing? What processes require us to lose consciousness, to become vulnerable, to spend roughly a third of our lives unconscious? One answer involves waste clearance. During waking hours, the brain's cells produce metabolic waste. These waste products accumulate in the fluid between cells. During sleep, this fluid flow increases, flushing out the waste, clearing the brain for the next day. Without this clearing, toxic proteins accumulate. These are the same proteins that build up in Alzheimer's disease and other neurodegenerative conditions. Sleep may protect against these diseases by preventing accumulation. Another answer involves synaptic homeostasis. During the day, learning and experience strengthen connections between neurons. If this continued indefinitely, the brain would become saturated, unable to form new connections. Sleep may reset these connections, weakening less important ones, strengthening the most significant, balancing the network so that tomorrow's experiences can be incorporated efficiently. There's also energy conservation. The brain uses enormous energy when awake. Sleep reduces metabolic demand, allowing the body to redirect resources to repair, growth, immune function. And there's memory consolidation, as we mentioned with dreams. Sleep helps transfer information from short-term to long-term storage, helps integrate new learning with existing knowledge. Likely, sleep serves all these functions and more. It's not a single process, but a collection of processes, each important, each requiring the specific conditions that sleep provides. But the deeper question remains: why must these processes occur during unconsciousness? Why can't the brain clear waste, consolidate memories, and rebalance synapses while awake? Perhaps consciousness itself is too energy-intensive. Perhaps the neural activity required for awareness interferes with these maintenance processes. Perhaps sleep is the only way to quiet the brain enough for the necessary work to happen. Or perhaps consciousness evolved as something that happens during waking, and sleep represents the brain's default state, the state it returns to when not actively engaged with the world. These are speculations, educated guesses. The truth is, we don't fully know why we must lose consciousness to sleep, why rest requires the cessation of awareness. Sleep remains mysterious, essential but puzzling, a daily disappearance into unconsciousness, a small death and rebirth, repeated every night of our lives. And tonight, you'll make that journey again, into sleep, into the unknown territory of dreams or dreamless rest. Your consciousness will fade, will recede, will vanish for hours, and then, when morning comes, it will return, as it always does, as though it never left, continuous, unbroken, even though there was a gap, a period of nothing, or at least nothing you remember. This, too, is a mystery. The continuity of self across sleep. How you know, when you wake, that you're the same person who fell asleep. That the consciousness returning is your consciousness. But these are questions for philosophers. For tonight, you can simply accept the mystery. Simply allow sleep to approach. Simply recognize that your body knows what to do. You don't need to understand sleep to sleep. Don't need to comprehend consciousness to be conscious. The processes will unfold on their own. as they always have. All you need to do is allow them, give permission, release control, let the natural rhythms take over. Your breath is steady now, regular. Each inhale and exhale part of a rhythm that continues without thought, without effort. You can notice this rhythm, not to control it, just to observe, to be aware of the gentle rise and fall, the cool air entering, the warm air leaving. And in noticing, you might find that the breath becomes even slower, even gentler, not because you're forcing it, but because this is what happens when attention settles, when the body recognizes it's safe to rest. We're going to explore just a few more mysteries now, moving toward the end of our journey, toward the place where questions fade and only quiet remains. There is a mystery in the fact that anything exists at all, that there is something rather than nothing. We touched on this at the beginning, but it bears returning to, because it's perhaps the deepest question we can ask. Why should there be a universe? Why should there be matter, energy, space, time? Why should there be laws of physics, regularities, patterns? These questions can't be answered by pointing to earlier causes. Even if we explain how the universe began, how it evolved, how it became what it is today, the question remains, why should any of that process exist? Some say the question is meaningless, that existence is simply a brute fact, that there is no deeper explanation, that asking why there is something is like asking what's north of the North Pole. The question assumes something that isn't there. Others suggest that perhaps non-existence is impossible, that nothingness is unstable, that something must exist because nothing cannot. Still, others point to mathematical or logical structures, suggesting that perhaps the universe exists because it's mathematically possible, and all mathematical possibilities are realized somewhere, somehow, in some larger reality. But these remain speculations, metaphysics, philosophy, beyond the reach of science, which can only study what exists, not why anything exists at all. And perhaps that's appropriate. Perhaps this is a question that cannot be answered, that lies beyond human comprehension, beyond any possible answer we could formulate or understand. The universe is, we are, and that's the starting point for everything else. You can rest in that, in the simple fact of existence, not needing to justify it, not needing to explain it, simply being, simply here, simply now. Let the mystery of existence be gentle, not troubling, not demanding, just present, like the darkness, like the silence, like the space between thoughts. Everything that exists is participating in this mystery together. The stars, the galaxies, the atoms in your body, all of it here, all of it now, all of it part of the incomprehensible fact that there is something rather than nothing. And you are part of that. You are existence becoming aware of itself, the universe looking back at itself through your eyes, through your thoughts, through your consciousness. This is worth pausing with, not to understand, just to acknowledge, to recognize. You are the universe experiencing itself, and right now, the experience is one of rest, of letting go, of drifting toward sleep. And that too is part of the mystery, part of the strange, beautiful fact of existence, that consciousness can arise, can wonder, can ask questions, and can, when it's tired, when the day is done, simply release itself back into the darkness, back into the quiet, back into rest. There are moments in the history of science when everything changed, when a single observation shattered what was thought to be certain, when reality revealed itself to be stranger than anyone imagined. In 1054, astronomers in China and Japan recorded a new star appearing in the sky. Bright enough to be visible during the day, it remained visible for weeks before fading. They called it a guest star. We know now that it was a supernova, a massive star exploding. What remains today is the Crab Nebula, an expanding cloud of gas still glowing from the energy released nearly 1,000 years ago. But at the time, it was just a mystery, a light where no light had been before, and then gone again. The heavens were supposed to be unchanging, eternal, perfect. The appearance of a new star challenged this, suggested that even the cosmos was subject to change, to creation and destruction. It would take centuries for this understanding to fully develop, for us to recognize that stars are born, live, and die, that the universe has a history, that nothing, not even the heavens themselves, is permanent. And there have been other moments like this, other observations that forced us to revise our understanding. In 1610, Galileo turned his telescope toward Jupiter and saw moons orbiting it. Not everything in the cosmos revolved around Earth. There were other centers, other systems. This was a profound shift, a step toward recognizing that Earth is not special, not central, just one world among many. In 1929, Edwin Hubble measured the light from distant galaxies and found that they were moving away from us. The farther away they were, the faster they receded. The universe was expanding. This, too, was revolutionary. The cosmos was not static, not eternal and unchanging. It had a history, a beginning. It was growing, evolving. Each of these discoveries opened new mysteries, new questions we couldn't have asked before because we didn't have the concepts. And this pattern continues. Every answer leads to deeper questions. Every solution reveals new problems. We've discovered dark matter and dark energy, but we don't know what they are. We've detected gravitational waves, but we're still learning what they can tell us about the universe. We've found thousands of exoplanets, but we don't know if any harbor life. The frontier of knowledge keeps expanding. The horizon keeps receding. No matter how much we learn, there is always more beyond, more to discover, more to wonder about. And this is not a flaw, not a failure. This is the nature of inquiry, of curiosity, of the endless human drive to understand. We are finite beings in an infinite universe. We will never know everything, never answer every question, never solve every mystery. But we keep trying, keep looking, keep wondering, because this is what we are. This is what consciousness does. It reaches out, it seeks, it questions. And in the seeking, we find meaning, not in the answers necessarily, but in the process itself, in the journey, in the act of wondering. You don't need to reach any destination tonight. Don't need to arrive at any understanding. The questions can remain open. The mysteries can remain unsolved, because the value is not in the solution. It's in the wondering itself, in the quiet contemplation of things larger than ourselves, things that stretch our minds, that remind us we are small, that there is so much we don't know. This is humbling, and in that humility there is peace. Let your body settle even more deeply now. Notice any remaining points of tension. Your forehead, your shoulders, your hands, and gently release them, not through effort, just through awareness. Just by noticing, the muscles often soften on their own, as though they were waiting for permission, for acknowledgement. And you can give that permission now. Let go. Let the tension drain away. Let gravity pull gently on every part of you. We're moving toward the end of our journey now, toward a place of rest, where the questions fade, where the mind becomes quieter, where sleep waits patiently, ready to receive you. But before we arrive there are a few more thoughts to carry with you, a few more quiet recognitions. The universe is vast, far larger than we can truly comprehend. The distances are too great, the numbers too large, the timescales too long, and yet you are here, part of it, made of the same atoms, subject to the same laws, connected to everything through gravity, through space-time, through the fact of existence itself. Every atom in your body was forged in a star. Carbon, oxygen, nitrogen, iron, all of them created through nuclear fusion in stellar cores, released when those stars died, scattered through space, eventually gathering into clouds, into planets, into life. You are made of stardust. This is not metaphor. It is literal truth. The material of your body came from stars that died billions of years ago, before the sun existed, before Earth formed. And one day, the atoms that currently form your body will return to the cosmos. They will disperse, join other structures, other cycles, perhaps become part of future stars, future planets, future life. Nothing is permanent. Everything flows. Everything changes. Everything is part of a vast, ongoing process of transformation. And in recognizing this, there can be comfort. You are not separate from the universe, not isolated, not alone. You are part of the flow, part of the transformation, part of the ancient, ongoing dance of matter and energy. This is your place, not above nature, not outside it, but within it, part of it, one expression among countless others of the universe's endless creativity. And tonight, as you rest, as you sleep, you can carry that recognition with you. You belong here. You are exactly where you're supposed to be, part of the great mystery, part of the endless unfolding. There is nothing you need to prove, nothing you need to accomplish, nothing you need to understand. You can simply be, simply exist, simply rest. The universe has been unfolding for nearly 14 billion years. It will continue for trillions more. Your rest, your sleep, your brief disappearance into unconsciousness is part of that unfolding, natural, inevitable, right. Let your thoughts become even softer now, even less defined. They don't need to be clear, don't need to make sense. They can drift, dissolve, fade like stars at dawn. There is a rhythm to existence, a pattern, day and night, waking and sleeping, activity and rest. The universe breathes, in and out, expansion and perhaps someday contraction, or perhaps expansion forever, but still a rhythm, still a pattern, and you are part of that rhythm. You wake, you sleep, you engage with the world, you withdraw from it. This alternation is natural, necessary, built into the structure of life itself. You cannot be awake always, cannot be engaged always, cannot be active always. Rest is not optional. It is required, fundamental, as important as waking. And sleep is not absence, not void, not failure to be awake. It is its own state, its own process, with its own purposes, its own value. In sleep, the body repairs itself. Cells divide, tissues heal, the immune system strengthens. Growth hormones are released. All the maintenance that cannot happen during waking occurs in sleep. In sleep, the brain consolidates memories, processes emotions, balances neurotransmitters, clears metabolic waste. All the invisible work that keeps the mind functioning happens in sleep. Sleep is not wasted time. It is essential time. Time when the invisible processes of life do their work. And you are approaching that time now, approaching the threshold where waking ends and sleep begins, where consciousness fades and the deeper processes take over. You might already be crossing that threshold, already drifting, already halfway into sleep, and that's perfectly fine. That's exactly right. There is no wrong way to do this. No test, no requirement. You cannot fail at falling asleep. You can only allow it. Only let it happen. And it will happen. It always does. Eventually, when the body is ready, when the mind has quieted enough, when the conditions are right. All you need to do is continue what you're already doing, lying still, breathing gently, letting your thoughts drift without following them, allowing the darkness to be comfortable. The mysteries we've explored tonight, they'll still be there tomorrow. The universe will still be expanding. Dark matter will still be invisible. Black holes will still hold their secrets. The questions will wait. They've waited billions of years. They can wait through your sleep. They can wait through 1,000 sleeps, 10,000, a lifetime of sleeps. There is no urgency, no deadline. The mysteries are patient, and so can you be. Your breath is very slow now, so slow you might not even notice it. Just a gentle rise and fall, barely perceptible, like waves on a calm sea. Small, rhythmic, peaceful, and your body is heavy, sinking into whatever surface supports you, every part of you resting, every muscle released, nothing to hold up, nothing to maintain, just gravity, gentle and constant, pulling softly, reminding you that you can let go, that you are supported, that you can trust the earth to hold you, and around you, silence, or perhaps soft sounds, but nothing demanding attention, nothing requiring response, just the ambient presence of the world continuing, patient, ongoing, indifferent to whether you're awake or asleep. The world will continue without your attention, without your awareness. It has before. It will again. This is comforting. You don't need to maintain anything. Don't need to hold anything together. Everything will be fine. Tomorrow will come, whether you're thinking about it or not. The sun will rise, the universe will expand, the mysteries will remain mysterious, all of it continuing, all of it ongoing. And you can rest in that continuity, can release yourself into it, can trust that when you wake, whenever you wake, everything will still be here. Changed, perhaps, slightly different, as everything always is, but fundamentally the same. Still here, still ongoing, still part of the great, mysterious unfolding. You are safe. You are held. You are part of something so much larger than yourself that your individual concerns, your individual thoughts, your individual awareness can fade without consequence. The universe doesn't need you to be awake, doesn't need you to be conscious. It continues regardless. And this is a gift, a release, permission to let go. So let go now, if you haven't already. If you're still holding on to anything, any thought, any awareness, any sense that you need to remain present, let it go. Let it fade. Let it drift away like smoke on a breeze. There's nothing left to do, nothing left to think, nothing left to wonder. Just rest now. Just sleep. Just the gentle, inevitable release into darkness, into quiet, into peace, into the mystery of sleep itself. And if you're still here, still aware, still listening, that's fine too. Sleep will come when it comes. You can't force it, can't demand it, can only wait, can only allow. And in the waiting, there is rest. Even without sleep, there is rest. The body lying still, the breath slow and steady, the mind quiet or quieter than before. This is enough. This is valuable. This is what you need right now, sleep or no sleep. Rest is happening. Recovery is happening. The invisible processes are beginning their work. And eventually, without your noticing, without a clear moment of transition, awareness will fade, thoughts will dissolve, and you'll be asleep. Or perhaps you already are. Perhaps these words are reaching you in dreams. Perhaps your consciousness has already released its grip on waking reality. There's no way to know for certain. No clear line between waking and sleeping. Just a gradual transition, a slow fading, a gentle dissolution. And wherever you are in that transition, it's exactly right. Exactly where you're supposed to be. The mysteries of the universe surround you. Dark matter, dark energy, black holes, time, consciousness, existence itself. All of it swirling in the darkness. All of it present. All of it mysterious. And you are part of that mystery. Not separate from it. Not outside looking in, but inside, woven into the fabric. One thread among countless others. Rest now in that recognition, in that belonging, in that connection to everything. Let the universe hold you. Let the darkness be gentle. Let sleep come when it's ready. And know that whatever happens tonight, however you rest, however you sleep, it is enough. You are enough, exactly as you are, exactly where you are, part of the great mystery, part of the endless unfolding. Rest now, sleep now, be now, here, in the quiet, in the dark, in the peace of not knowing. Let the mysteries remain mysterious. Let the questions remain unanswered. Let everything remain exactly as it is. And simply, gently, softly, drift. Drift into whatever comes next. Drift into rest. Drift into sleep. Drift into the quiet mystery of existence itself. There is something profound in accepting that we don't know. For most of human history, the unknown was terrifying. The darkness held dangers. The unexplored was threatening. Mystery meant vulnerability. And so we told stories, created myths, invented explanations. Not because they were true, but because they made the unknown feel manageable, less frightening. Science changed this, not by eliminating mystery, but by embracing it, by saying, we don't know yet, and that's acceptable. That's where we begin. Every scientific discovery starts with uncertainty, with a question, with the recognition that something is not yet understood. And then comes observation, careful measurement, testing, the slow accumulation of evidence, building understanding piece by piece, not leaping to conclusions, not inventing answers, but patiently, methodically, following where the evidence leads. Sometimes this process takes years, decades, centuries. Some questions remain open for generations before enough evidence accumulates to answer them. And some questions may never be answered. Some mysteries may be too deep, too fundamental, beyond the reach of any method we can devise. But this doesn't diminish the value of asking, of wondering, of sitting with uncertainty and being comfortable there. Because wonder is its own reward. Curiosity is its own justification. The act of questioning, of seeking, of exploring is meaningful even when answers remain elusive. And tonight, as you rest here in the darkness, you can carry this recognition that it's okay not to know, that mystery is not a problem to be solved, but a feature of existence, a reminder of how vast and strange reality truly is. You don't need to understand consciousness to experience it. Don't need to explain time to move through it. Don't need to solve the origins of the universe to exist within it. You can simply be present, aware, part of the great unfolding, part of the mystery itself. And in this acceptance, there is deep peace. Your body has been resting for a while now. Perhaps you've noticed how different it feels, how quiet, how still, how removed from the urgency and tension of the day. This is the body in rest. This is what it feels like when nothing is demanded, when no action is required, when you can simply exist without purpose or goal. It's a rare state in modern life. So much of our time is spent doing, accomplishing, moving toward objectives, Even relaxation often has goals. Even rest can become something to achieve. But right now, there is no achievement, no destination, nothing to accomplish. You're not trying to fall asleep. You're not trying to stay awake. You're not trying to think or not think. You're simply here, present, in this moment, in this breath, in this gentle, directionless awareness. And this is enough. This is complete in itself. Whether sleep comes or doesn't come, whether thoughts continue or fade, whether you remember any of this tomorrow or not, right now, in this moment, everything is exactly as it should be. The universe has been unfolding for nearly 14 billion years. Stars have been born and died. Galaxies have formed and collided. Planets have emerged from dust. Life has appeared, evolved, spread across at least one world and perhaps many others. All of this happened without plan, without blueprint, without anyone directing it. The universe simply unfolds according to its nature, following physical laws, responding to conditions, creating complexity from simplicity, order from chaos, consciousness from matter. And you are here, the result of all that unfolding, the descendant of an unbroken chain of ancestors stretching back 4 billion years, the inheritor of atoms forged in stars that died before the sun was born. You carry the entire history of the cosmos in your body, in your bones, in the electrical signals firing through your neurons, in the oxygen you breathe and the carbon that forms your cells. You are the universe looking at itself, thinking about itself, wondering about itself. And right now, you are the universe resting, letting go, preparing to sleep. This too is part of the cosmic story. This quiet moment, this gentle fading, this release from waking consciousness. Stars rest between fusion reactions. Planets rest between geological epochs. Life rests between periods of growth and activity. Everything cycles. Everything alternates. Activity and rest. Waking and sleeping. Being and letting go. And you are following that ancient rhythm now. The same rhythm that has pulsed through reality since the beginning. The same pattern that connects you to everything that has ever existed. Rest is not withdrawal from life. It is part of life, essential, fundamental, as important as any activity, any achievement, any moment of waking consciousness. And sleep, when it comes, is not absence, not emptiness, not less than waking. It is its own state, its own experience, even if not remembered, even if consciousness fades completely. Something continues. The body continues, breathing, heartbeat, blood flowing, cells dividing, neurons firing in dreams or in the deep restorative silence of dreamless sleep. Life continues. Even when awareness pauses, even when you disappear from your own experience. And this is perhaps the deepest mystery of all, that you can vanish, can cease to exist from your own perspective, and yet continue and return, night after night, year after year, a lifetime of these small deaths and rebirths. But these are just thoughts now, just words, and they're beginning to fade, becoming less important, less substantial, like fog burning off in morning sun. There's no need to hold on to them, no need to remember, no need to understand. Just let them go. Let everything go. Let the last threads of waking awareness gently release. Breath, just breath, slow and steady. Not thinking about breathing, just breathing. The body knowing what to do, doing it without instruction, without awareness. And maybe awareness is fading too. Maybe it's already faded. Maybe these words are reaching you through layers of sleep, through the thin boundary between waking and dreaming. Or maybe you're still here, still present, still listening. And that's fine. That's perfectly acceptable. Sleep comes when it comes. You can't control it, can't force it, can only wait, can only rest. And you are resting. Even if sleep hasn't arrived yet, even if thoughts still drift through occasionally, even if awareness still flickers, you are resting, and that is enough. The mysteries will wait. The universe will wait. Everything will wait. Tomorrow is not here yet. Yesterday is gone. There is only now, only this moment, only this breath, only this gentle darkness. And in this darkness, there is no fear, no anxiety, no concern, just peaceful absence, just quiet emptiness, just the simple fact of being here, of existing, of breathing in the dark. You don't need to be anyone right now. Don't need to do anything. Don't need to think or feel or experience anything in particular. You can just be, undefined, unstructured, pure presence, pure awareness. Or not even that, just being. And if that being fades into sleep, into unconsciousness, into the complete absence of experience, that's natural, that's right, that's what should happen. Let it happen. Don't resist. Don't try to stay aware. Don't try to notice the moment of falling asleep. Just let go. Completely. Finally. Absolutely. Let the universe carry you. Let the ancient rhythms take over. Let sleep come in its own time, in its own way, and know that whatever happens, however you rest tonight, it is exactly right, exactly what you need, exactly where you're supposed to be. You are part of the mystery, part of the cosmos, part of the great unfolding, and right now, the unfolding is taking you toward sleep, toward rest, toward the deep, restorative silence where consciousness fades and the body does its invisible work. Go there now, if you haven't already. If you're still holding on to any awareness, any thought, any sense of self, release it. Let it go. Let it dissolve into the darkness. Just darkness. Just silence. Just peace. Nothing more needed. Nothing more required. Just this. Just now. Just rest. Sleep whenever you're ready. However you're ready. In whatever way feels natural. The universe has waited 14 billion years. It can wait for you. It can hold you. It can carry you into sleep. And when you wake, whenever you wake, the mysteries will still be there, still waiting, still unanswered. But right now, there is only this, only quiet, only rest, only the gentle dissolution of awareness into sleep. Let it come, let it be, let it carry you. Sleep now, rest now, be now, in the darkness, in the quiet, in the infinite, mysterious, beautiful unfolding of existence. Sleep, rest, peace, just sleep. And if you're still here, still aware in some small way, know that it's okay. Sleep will find you, eventually, when the time is right. Until then, just rest, just breathe, just be. The mysteries of space surround you. Dark matter invisible, dark energy pushing, black holes holding secrets, stars being born and dying, galaxies spinning through the void, all of it continuing, all of it ongoing, all of it mysterious and beautiful and vast beyond comprehension. And you are part of it. Small but connected, brief but meaningful. One moment in an endless unfolding. Rest in that, sleep in that, be held by that, and let everything else, everything, fade away into the quiet, the dark, the peace. Sleep.